minutes.
Oh, okay, good.
I'm looking on my alarm clock, and this is wrong by 2 minutes. Good. Okay.
No, your chair should be a local person, Ifu Kai. I don't see him yet. He's somewhere.
Still 5 minutes, so yeah. Okay.
Actually, now I will ping him in local WeChat. People in China live using WeChat program. It's no way around.
Okay. Okay, Mike. That.
Yeah, Alexander, if you want, you can check share screen if it's working.
I'll try. You're asking me, okay. No. Good idea. And
It
Siemens
says it
doesn't-
started, and I do not see yet the screen slides.
Yes, somehow it disappeared from my. Strange. Here is resume share. Let's try. Oh, maybe I have to.
Hello, everybody.
Hello.
Hello,
Glad to
Irina.
see you.
Hello.
Oh.
Hello.
Hello.
Okay, I try to share again.
It's in
Okay,
now.
great. I'm happy.
Okay.
It's always so
Perfect.
nerve consuming. Okay, very good. So,
Ravan, did you get my Telegram message?
Yeah, I got it.
mhm.
But anyway, we can wait.
Yes.
Let's see.
No, I mean,
Did you contact through WeChat?
yes, I contacted, yes. What? So our chair is coming.
Great.
I hope so. At least this is what he said me in the messenger.
will he or
Actually,
she?
this is related to local bureaucracy. Local bureaucracy is amazing because sometimes you can get a notice like you have an important meeting, and it can happen literally a few hours before it starts.
Yes, it happens, but I survive only because I ignore many important meetings. Okay, but in Siberia it's cold and people are, well, I think moves more slowly than in hot weather. I don't know, maybe other way around. Okay, anyhow, I'm ready.
Yes, so if you don't mind, we can wait our chair for a couple of minutes, maybe.
No problem at all.
Also, in principle, it would be great to have other speakers, but we can imagine that they will join.
I think so. Well,
Stravan, if Kai will not appear in next minute, I will delegate to you to chair this session.
Okay. Problem.
No, because he kind of promised to join, and he says me that I'm joining, but I don't see him. I don't know. Maybe he's joining. I don't know. Maybe just speed of light forbids him to join from China quickly. It's my only guess for the moment.
Well, Zoom is allowed. You don't need VPN for Zoom.
I mean, I'm the proof by construction. Yes, I do.
Yeah.
I do connect.
maybe speed of light in these conditions is slower than the speed of sound. Does it happens?
It's a good one, by the way. Well, Stravan, so I suggest you to start the session because otherwise it's too much. We should not delay too much.
Okay. In case if he appears for the second talk, so then I will step down.
Then you will step down and delegate him back this, okay?
Okay. Good. Thanks for making me the accidental chair. Okay. Hello, everyone. Welcome for another exciting day. Today, we'll start our session with the talk of Alexander Dolgo. He will tell us about PBH, antimatter, and HST JWST data. Please, Alexander, 45 minutes.
Okay, thank you. I start with my abstract so that everybody present could know what is the talk about and would not wait till the end of the talk. So first I started with the review of the data of Hubble Space Telescope and James Webb Space Telescope. And you know that there was strong contradiction between the canonical lambda CDM cosmology and the observed rich population of the galaxy, of the universe by galaxies, when the age of universe was, roughly speaking, a few 100 million years, and this is unbelievably early. And in standard models, nobody expected this rich population, and not only galaxies, but also black holes, super heavy black holes are present in the early universe. First, it was found by Hubble Space Telescope, and there was some confirmation by James Webb. And next thing is the main statement of my talk, that the galaxy formation is probably seeded by primordial super heavy black holes. And this was first suggested in our paper with Joe Silk in 1903. And there are even a few papers now where the statement was rediscovered. I think 2 or 3 works. Another thing that we predicted in our work, the mass spectrum of primordial black holes, which happen to be very simple log normal spectrum, which is tested by observations and have very good agreement with the data on chirp mass distribution of gravitational wave emitted by coalescence of black hole binaries. And another thing which is rather unusual, even for me, I found that recently, that primordial black holes could make 100% contribution to the density of the cosmological dark matter. Usual limits are something like 10% at most, but I think there are interesting ways out, and I will try to explain. It is not my result, it is a result of some other papers. And the last but not the least, that there was very interesting byproduct of our model, that there could be quite significant population of Milky Way by antimatter, and it seems to be also confirmed by the data, surprisingly, but it seems so. Okay, that's the content of the talk. Now, and this is outline. It's essentially already what I said. And I speak about log normal mass spectrum, black dark matter, gravitational waves, and there are references to our papers. One was Joe Silk of 93, and another with Kawasaki, Masahiro Kawasaki and Nina Kivlishvili. And we have even spoke about cosmic antimatter and expressed that in the title of the talk. Oh, sorry. I pressed the wrong button. So as for Webb Space Telescope data, it was a few months ago, discovery, striking discovery, and that the universe contains too many galaxies, and there was some, I would say, point of possible criticism that the James Webb Telescope works in continuous infrared range, and they are not very good in determination of redshift of the galaxies, because it contains some kind of presumption. But what was really necessary to find confirmation of redshift by spectral line identification. And that was, it happens in this February. There are many papers about that, and now there is absolutely no doubts of the correct measurements of the correct guess of their redshift. Almost everywhere there was very good agreement. So this is the piece of the data which I want to show this one. It is data by Webb Space Telescope, and then this is by the Hubble, and there is a very good agreement between them. So there is really very good support of both groups. And another thing is the data of James Webb. This is these black curves, crosses are James Webb data, and this is predictions of lambda CDM cosmology with some slightly varying parameters. Oh my God. So there are several papers. I simply enumerate them. There are several works of different measurement of different elements, which are indeed very well confirmed I would say, educated guess of James Webb. So I simply just want to flash that there are, I think, at least 5 papers, and so spectroscopic observation, except for one single case, confirms that James Webb had indeed discovery of the early universe at redshift larger than 10 and even up to 15 with beyond any data. There is indeed very, very strong confirmation, judging by the spectrum of known elements. You can always measure with good precision the redshift. As for main idea of my talk, is the possible resolution of the problem is the suggestion about galaxy formation. I would say upside down. Usually it is assumed that black holes are formed inside galaxies as a secondary process. First galaxy is formed, and there was some excess maybe of matter in the center of a galaxy, and because of strong accretion of matter, supermassive black holes would be formed after galaxies formed. Our suggestion was other way around, that supermassive black holes were formed first, and then they seeded galaxy formation. This was the time taken with, at least with some caution, to say the best. And there was a few recent papers there. This statement was rediscovered, that people essentially came to the same conclusion. One was a paper by Leo and Braun, and then they say that structure formation could be accelerated by massive primordial black holes. Oh, excuse me. Okay, and they need about 1 billion solar masses primordial black holes. We can easily supply them. Another paper by Guan Yuan, if I pronounce the name correctly, that there could be collection of black holes with smaller masses, and there is some say weak points because they should gain mass through super Eddington accretion. So it's quite unusual. Normally, it's more or less limit by which black hole mass could rise. And so, as I would say, that if you have prepared supermassive black holes from the early universe, it will be fine. And then there was another thing, that not only galaxies, but also formation of supermassive black holes is really hard to squeeze into narrow frameworks of the standard cosmology. But still we have a great lot of them observed in the early universe, and it was also in the present-day universe as well. So there was indeed very impressive April paper of ultramassive black holes with about, how much is it? Almost 2 billion solar masses. Again, in that case, they say it's enough to accrete near the ending point limits, but it's almost impossible, at least from my point of view, because I have a great lot of wishful thinking. But if there is a primordial black holes, again, there is no problem. The only thing is how to make those, let's say, seed, but we indeed suggested that before all this new troubling data was announced. Another thing that about supermassive black holes announced at very early universe, redshift almost 7, and it's again the problem. And the black hole mass, as you can see here, it is, how much is it? Logarithm is about 7, so it's 10 to the power 7 solar masses, I suspect. Well, okay. And okay, it's essentially repetition. Now, it's indeed very striking observation. Even authors said that observation of those galaxies goes against any reasonable science. As it written is quote from their work, according to the science, it's impossible to create so well-developed galaxies. They have 6 galaxies, which are not early galaxies, but already adult, with well-developed stars and everything like that. And to this end, they need much more time than 500-700 million years. So they say that maybe they are supermassive black holes of the kind never seen before. Probably they mean that it's never of this never seen before kind, that this is a primordial black hole, because traditional astronomers, and I don't know why, is rather reluctant to accept this notion. And we say that they say that might mean a revision of our estimation, of our understanding of black hole. So anyhow, for primordial, we can easily do that. Okay, so another thing that there is a very rich chemistry observed around these early galaxies. So to make dust or other heavy elements, or even just inside the stars on the interstellar medium, a lot of processes are necessary. There could be supernova formed, they must explode, and so enrich interstellar space by heavy elements, and especially of heavy elements with high metallicity, like nickel, iron, and anything like that. So there are several things. High abundances of heavy elements. Maybe, as I said, I didn't mention that, but it's written here that in our model we have bubbles with very large amount of baryons. But the ratio of baryons to photons could be of order of unity, which is approximately a billion times, maybe 10 to the power 9 times larger than the standard one. And in this case, nucleosynthesis, primordial nucleosynthesis, proceeds to very heavy elements, which we calculated some years ago with Japanese group, and later repeated in some later our estimates. So what I want to stress, that the problems which I mentioned about early galaxy formation, early black holes, and also black holes even in the present day universe existed even before James Webb data was published. And there are black holes, quasars, and as I said, overpopulated universe with supernova, gamma bursters, and very dusty, followed from the 10-year work of Hubble Space Telescope. So there was I summarized this data in how many years ago? 5 or 4 years ago, in Russian review paper, Physics Успехи. And so it was only summary of problems and also suggestion to solve it by galaxy seeding. As I said, all the problems are neatly solved if the universe is populated, I repeat, by primordial black holes. And, okay. And now a few words, since not everybody is familiar, it's a kind of popular, about black holes type by formation mechanism. There are so-called astrophysical black holes and so-called normal black holes. If they are created by collapse of the star, which exhausted its nuclear fuel, and the gravity became stronger than the pressure, and if the mass is larger than something like 3 solar masses, a black hole would form. And in fact, there are observations that black holes are has maximum in the spectrum about 10 solar masses, and there are some possible black holes with a mass of 100 solar masses, which is probably observed from the gravitational wave data. And such black hole before was considered that is absolutely impossible to form. So because it's so heavy that instead of forming black holes, I think stars, which is the origin, is the parent of these black holes, exploded and threw away all the matter, and so it was not enough to make any reasonable black holes. But now there are several explanations practically outside of the conventional astrophysics. So there are some exotic mechanisms with black holes considered of mostly of dark matter annihilation. Well, anyway, it's interesting, but it was invented a priori. You know, theorists are clever people. They quite often may find explanation for impossible things. There is another thing, second kind of black holes, which are formed by accretion on the mass excess in the galactic center. And according to the data of the early universe and mostly in present-day universe, in any large galaxy, there exists a supermassive black holes, which varies from a few million solar masses, which mass, for example, in our Milky Way, it is just a very small one, but there are some black holes observed in the present. The universe are billion solar masses, and at least one is about 100 billion solar masses. And as estimate of the necessary time for gain such huge mass was done, for example, for our Milky Way, and they say that the standard accretion mechanism that at least 10 times longer than the universe age is necessary. And if we speak about supermassive black holes in the universe, which is 10 times younger, it may be even more terrible, but not exactly proportional to the age, because maybe the density of matter can be higher, and so process may be faster, but still it is a huge difference of the standard accretion picture and the data. You remember that I mentioned at the beginning that we need maybe some seeds and accretion beyond the standard limit, standard Eddington limit. There, and last not the least, is so-called primordial black holes, which were created in the very early universe before star formation. And the idea of primordial black holes, first idea was put forward by Zeldovich and Novikov. And the idea is quite simple, that we have more or less homogeneous distribution of matter in the early universe. But just by chance, there could be large spike with delta rho over rho of order of unity. And if the size of the spike, characteristic size, it is of order of the cosmological horizon, which is roughly universe H at that time, then all this large density, the piece of space with large density contrast would be inside its own gravitational radius, so it would be black holes. Later on, this idea was elaborated by Hawking quite soon, well, 4 years after that, and there was also, I would say, a very good study, research on the subject by Carr and Hawking in 1974. Next, there is, I would say, there is certain classification of black holes by masses. There are supermassive black holes from million up to 10 billion solar masses, but now black holes which is with the masses almost 100 billion solar masses are discovered. A new term is invented, ultramassive black holes. Then there are black holes with intermediate mass, which is indeed a great surprise because there are so many observed, and their mass range from 100 to 100,000 solar masses. And solar mass black hole with the masses of fraction of solar mass may be up to 100 solar masses. Mostly origin of these black holes is unclear, and except maybe of masses of a few solar masses, which has good chance to be astrophysical. And as for intermediate mass black holes, I would say nobody expected them, and now we have almost avalanche of them coming to observation. And so it's a great tension, but again, if almost, and I really extremists think that all black holes in the universe are primordial, could strongly reduce or even eliminate this tension. Of course, not all of them. There are some can be formed by astrophysical process. And there is more or less summary of what I said, so I can easily skip them, except for there are very strange stars which happen to be, sorry, not older than, they are older than the galaxy, and there is one star which is older than the universe. In our model, it is explained. Of course, it is not older, but they have very many unreached by heavy elements, so it looks older. Another, the problem of creation of so-called MACHO, massive astrophysical compact halo objects, with the mass they absorb through microlensing, with a mass of about 0.5 solar masses, and their origin is absolutely unknown. And another thing, that so-called intermediate mass black holes, which are observed in dwarf and galaxies and globular clusters. And what I want to say in advance, that this was predicted in our paper by Pastnov. We estimated their production if they're seeded by black holes and not produced by the accretion. And this is just to show that there is ultramassive black holes with a mass of 100 million solar masses discovered really recently. Now about the test of the predicted by log normal spectrum, so-called test by experiment, by the distribution of black holes in gravitational wave measurement. So log normal spectrum is extremely simple. This is normalization factor. We don't know that, and if black holes make all dark matter, we can predict its value. Gamma naturally is to be of order of unity, judging by the distribution of black holes with mass of order of solar masses up to 100,000 million solar masses. As for M sub-zero, it could be predicted theoretically, and its value is around 10 solar masses, as was because the formation of those black holes takes place during QCD phase transition, quantum thermodynamic phase transition, and the size of horizon is of order of 10 or 20 solar masses. This is perfectly well agrees with the data. And next is seeding of galaxy formation. In fact, seeding of globular clusters and dwarf galaxies. So I think we analyzed the data. We've analyzed the data with Pasnov, and it's very well agree with the observation. Looking by your face, I see that how much do I have?
You have 15 minutes.
How much?
More than 15 minutes. Yeah.
Okay, I'll try to be. Now, important point that dwarf formation is seeded by primordial black holes, and there are several candidates for that found, well, recent and old publications, which nicely fit this picture. And so that's neat. And so I see that's maybe, I skip many of them. Okay, anyway, there are several candidates of dwarf, which is very difficult to form with huge black hole inside, and there is not enough matter to create this monster inside this dwarfs or globular clusters. They are not massive. Okay, that's, I think, I skip. Now a few words about gravitational waves. It's more or less, maybe not common opinion, but majority thinks that they are primordial, because otherwise it's very difficult to explain their feature. The origin of double system, if, for example, there is collapse of a star, and with small eccentricities, the star requires huge momentum, and so binary is destroyed. And black holes, if they existed from the very beginning, then it is much easier to make black hole binaries. And another thing is low spin of coalescing black holes, which is measured, and mostly spin is parameter A, you know, which describes the spin, which varies from 0 to unity, is of order of 0.1, not more. Okay, now we made together with a group of, mostly group in GAISH, it is Sternberg Institute, Astronomical Institute in Moscow, made comparison of measured chirp mass distribution. This is this mass which is responsible for luminosity in the form of black holes for different events observed by LIGO, Virgo, and Kagra. And this is the paper with big amount of authors. And this is the distribution, the chirp mass distribution, which is measured by observation. We have about 100 events, and there is this blue horizontal lines is experiment, and red line is our predictions. Okay, and here is the same data, and there are a few models of astrophysical black holes, and you see the difference. This is predictions for primordial black holes, and these predictions for astrophysical black holes. So astrophysical black holes seem to be massively favored. Okay, so that was, there was some new analysis, and the results are maybe somewhat different, and at some stage are questionable. So, but it was new analysis by Pasnov and collaborators, and maybe this should be addressed later. Another thing is essential ingredient of our model is application of inflation to form very large masses of black holes. There are some literature on the subject. Just it was first in our paper with Joe Silk, and then a year later by Har, Hilbert, and Leslie. And soon after that, Ivanov, Naselsky, and Novikov. As for these people, also presented model which allows to form very heavy primordial black holes. And the difference is that only in our model we have very simple spectrum of mass spectrum of black holes.
And as for black dark matter, the suggestion was that primordial black holes may be dark matter particles, was put forward by Hawking in 71, and then it was repeated in 75 by Chaplin, also from Cambridge. And they have quite light black holes, which are probably not allowed for, well, they're allowed, but they are not what we see in observations. And next one was our paper with log normal. There is the constraints on the primordial black holes in the review by Carr and Kuhnel, and then you see that the region which I'm interested in is somewhat excluded, at most at 10% level. However, then let me see. There are several works which criticize this bounds, and most important, then there was interesting paper by Rubin, Sakharov, and Khlopov that they say that their primordial black holes, or black holes anyhow, form clusters. In this case, the constraint would be made much weaker. And recent analysis by Yuri Yeroshenko and Stasenko, I don't know, forgot his name, that if we have clusters of those black holes, then the limits could be much weaker. And they used the paper by Sasaki et al. And Nakamura and used the model of those people. And then they share their conclusions that even fraction of primordial black holes with respect to total dark matter between 0.1 and unity is not excluded. I got it. Okay, I think I skip this. The only thing is that the model solves nicely the problems, and another that now I'm inclined to believe that antimatter, which is predicted in our works, should really exist. And what is known that in the galaxy, we obtain very big flux of positrons in famous 0.511 MeV line anti-nuclei and especially anti-stars, which is a great surprise. So if there is a flux of positrons, which is quite high, and in his colloquium in, I think it was 21 by Sam King, he criticized the accepted mechanism that they are produced in magnetic field of pulsar and advocated their primordial origin. Another, as for anti-nuclei, they are absorbed in alpha magnetic spectrometer. There is too much anti-helium-3 and anti-helium-4, and if they are primordial antimatter, then it's possible to explain, and secondary production, especially for anti-helium-4, practically completely excluded. Then I think I skip that. There is an interesting problem that deuterium and anti-helium is more or less at the same in amount. And there is another thing, an observation of anti-stars in the galaxy, and this is the authors of this work, that they say that they found 14 anti-star candidates by excessive gamma ray radiation in the range of about 500 MeV, which corresponds to proton anti-proton annihilation to pi meson, and that's more or less maximum of the spectrum. And this is the photo of that. And there was another possibility discussed in our paper by Bonder and several other co-authors, that there could be another interesting signature, that proton and antiproton do not annihilate with head-on collision. They form a kind of atom like positronium or protonium, and they jump from one level to another. And this can be calculated, and there are very well defined lines in KV range, and so this is possibly can be observed in X-ray service. Okay, so as for anti-stars, I think I can skip. Then there are, we studied ages ago with Bambi, Cosimo Bambi, Sergei Blinnikov, and Konstantin Postnov, bounds of antimatter in the galaxy, and found that they're quite weak. So 15 or 14 anti-star can easily fit this bound, can easily be inside this bound, simply because annihilation proceeds on the surface because of very small mean-free path of proton to antiproton star, and so you can observe it if you by chance just spot this particular star. So there is plenty of room for that. And as for the mechanism of that, it was so-called fusion-motivated baryogenesis, suggested by Affleck-Dine, and this model is very funny baryogenesis scenario. Usually, baryogenesis normally the model predicts baryon asymmetry ratio of baryonic number to the CMB photon number at a level of, we need to explain at the level of 6 times 10 minus 10. And usually we have to increase as much as possible the prediction of the model. In the case of Affleck-Dine mechanism, it should be, efforts should be done to decrease because they can create baryon asymmetry of order of unity. And we did this trick and introduced, to do that in comparison with observation, we introduced new coupling of Affleck-Dine scalar baryon. It is a scalar particle with the baryonic non-zero baryonic number, which is predicted by any kind of supersymmetry. And interacting with the inflaton field, where phi is the inflaton field and phi1 is the value of inflaton field, which is passed during inflation sufficiently long before the end. In this case, it automatically leads to formation of baryonic numbers with high baryonic number density of order of unity, and they mostly form black holes, and we can calculate its mass spectrum using diffusion equation derived for Starobinsky, and we generalized it to complex scalar field kappa. And this result, as I found later, log normal mass spectrum is a general feature of stochastic processes. Okay, so this is more or less some details of this picture. So what we formed a universe like Swiss cheese upside down. So there are bubbles with high density, and the rest baryonic density, and the rest normal small baryon asymmetry. So this is prediction, as now I more or less summarize, that there could be for primordial black holes log normal spectrum, which is strong support of our model because it's confirmed by experiment. There could be compact stellar-like objects, unusual stars. There could be disparate hydrogen and helium and anti-helium and anti-hydrogen bound clouds, but they annihilation there proceeds very strongly, and so they disappear to our time, but there could be some traces of that. And as for baryon asymmetry, it is direction of rotation of field chi in complex chi plane. It could be either positive clockwise or anti-clockwise, and depending on the model, there could be either 50-50 or 10% to 90, something like that. We cannot predict it, but at least order of magnitude ratio of antimatter to matter is allowed. Okay, so, and this I already explained, that the stars older than the universe could exist because of very extremely enriched content with heavy elements. So they are not old, but their old age is mimicked by evolved chemical content. So, okay, I think, oh, it's a repetition. Sorry. So, okay, let me stop here. Yeah, so more data are expected and surely coming, and let's hope that I indicate in the correct direction. Thank you.
Okay, thank you very much, Alexander, for fascinating talk, and you are perfectly in time. So we have time for questions. Please raise your hand. Okay, maybe actually I have a lot of questions to ask. So Maybe let me start the questions. So actually, I heard from the people who are working in the gravitational wave data that not all the dark matter can be explained by primordial black holes. Is it true? Because you mentioned that you can have fraction 0.1 to 1, but can we have
Yes.
one completely?
Yeah, that's is under assumption that black holes are more or less uniformly distributed over the space. What is this? In that case, the result is at a level of 0.1 or something like that, a fraction. It is canonically accepted value, and that was in the review of Karen Kuchen. But what I said, it was the work of Moscow group. There was Khlopov, Rubin, Yeroshenko, and they considered some long time ago, they, according to their calculations, dark matter, especially consisting of heavy black holes, could make clusters. And in this case, the bounds are much weaker. That I mentioned this paper. Here it is. And then, and it was, in fact, there was recent analysis by Yeroshenko and Stasenko that based on the model of Sasaki and Nakamura, in that case, they, if they are in more or less compact cluster, in that case, the standard limit are not applicable. And there is publication recently, quite recently in February of this year, and the basis for theoretical basis for their work is Sasaki and Nakamura, which was published some time ago. So they have essential thing that clusterization of primordial black holes with a mass of order 10 solar masses, something.
Okay. Then I'm curious whether I mean, the galactic rotation curves look almost the same for every galaxy. So, and this why this is kind of advocated as well. It is MOND and dark matter cannot explain this. I mean, there are groups say this because of the success of MOND. Of course, although it is empirical. I'm curious, what would be the role of primordial black holes in a sense of explaining this consistency of rotation curves for every galaxy?
Not much different. It is, they behave like in many respects like cold dark matter. So there is not big deal about that. There are also a few other things, few other problems with cold dark matter, like absence of what is this? Excessive delta rho over Rho galactic center, and also, well, there are a few things. This primordial black holes encounter essentially the same problems as the usual cold dark matter. Maybe somewhat can be somehow improved. I don't know.
Okay, thank you. Well, I have another question, but I would like to ask our audience if anyone have questions. Okay, then I would like, I'm happy to ask another question. And so actually, you mentioned in one of your slides, the primordial black hole formation would be decided by delta rho by rho being of the order of 1. When I read papers, this is basically the criteria in the context of radiation dominated, I mean, if the primordial black holes form in the radiation dominated phase. I'm curious, what would be the criteria in the matter dominated phase? Should there be delta rho by rho should be equal to 1 or of the order of 1? Is it the same criteria or something else?
Well, in fact, there is delta rho over rho of order of unity. It depends upon the expansion regime of the universe. There is same co-order of unities by the order of magnitude. It depends upon expansion regime. It could be somewhat different. And this depends upon the regime. In our model, it's completely different. We formed bubbles with big baryonic number, and delta rho over rho was essentially zero because it was slightly, and then after QCD phase transition, these bubbles acquired huge mass because before it was massless quarks. And after QCD phase transition, they turned into protons and neutrons with mass of order of GeV, while characteristic temperature energy was about 100 MeV. So there was these bubbles with initially delta rho over rho equals 0 or small, suddenly became very massive, and that's became black holes, and this mechanism is very much new, and this is not subject to the standard limits of formation of PBH at MD stage or RD stage. And in our case, it was at radiation domination stage, but inside there happened to be all of a sudden matter domination state, because proton became mass. Inside this bubble, the universe became matter dominated. And with huge.
Is it a recent paper?
What?
You're speaking about your recent paper, where you studied this?
Yes, it was our original work. Later
Okay.
on, it was repeated somewhere, but this idea was in 1903 with Joe Silk, and also 2006 with Kawasaki and Kivalishvili.
Okay, okay. Thank you.
Thank you, too. Mhm.
Okay, so I think it's time to move to the next speaker, and let's thank Alexander Dolgov again.
Okay, so I have somehow to stop share, correct?
Yeah,
Yeah,
yeah.
thank you very much for a very nice talk
Okay, I'll
indeed.
try. Thank you. Oh. Okay, I cannot do that.
Okay, our next speaker is Luca Smaldone. Luca.
Yes.
Yeah, if you can share screen.
Yes. Can you hear me properly?
Yes, yes, yes.
Very good. Okay, I put full screen. Okay. Can you see
Okay.
well?
Yeah, we can see. I think, did you put
Okay.
full screen?
I think yeah. Maybe no. Let me check. No. Yes. Yeah. Now I put full screen.
Okay. Okay.
Okay.
Yeah. Okay, so our next speaker is Luca Smaldone, and he will tell us about quantum black holes as classical space factories. Luca,
Okay.
please. I will just raise my hand before 5 minutes. Okay. 40 plus 5.
Yeah, it's better you interrupt me because I don't think I will see.
Okay, okay. Okay,
Interrupt
sure.
me.
I will interrupt you. Okay.
Thank you very
cool.
much.
Yeah.
So thank you for thank you to the organizers for the opportunity of speaking here. And yeah, I present you this work that I did in collaboration with Professor Iorio from Charles University. And so let's go. Okay, it moves. Let's go to the outline. First of all, I will I will present the motivations of this work, some preliminary facts, the idea of exons that actually I presented to at this conference last year. So the ones of you which were there now maybe remember what I presented last year. And then I will enter more into the technical part, which is let me say, the formal machinery I use in this work, which is the so-called boson method. I will try to give the basic on this method. And then how we applied this boson method to the problem of emergence of space and matter. Let's see. So as you can read from my outline, the idea is that starting from some quantum theory and describe the emergence of space and matter and eventually the emergence of gravity. So this is not quantum gravity theory, but it's emergent gravity more properly, I would say. That's just to fix, in some category what we are doing here. So axons. What are axons? The idea was born looking at Bekenstein bound. So Bekenstein was proposed that it exists an upper bound for entropy, and black hole saturate such bound. Black hole saturate such bound. And this fact has some interesting implication, I would say. The one was pointed out in particular by the group of Carroll and others, but there's also previous work by Toft, which point out and then Hilbert space of a quantum gravity system. Okay, read in a wider sense, should be locally finite dimensional. Okay, so the bound on entropy put a bound on the number of degrees of freedom available for a local quantum system, and then to the dimension of the Hilbert space. And then after this, group of Yorio in Prague proposed that such bound is saturated only by black hole, because in black holes you have some fundamental degrees of freedom. There are some fundamental degrees of freedom which are free in a black hole, and which take into account both for matter and space, basically. And so this finite dimensional Hilbert space count all the degrees of freedom, both relative to geometry and matter. And these modes were such fundamental building blocks were called axons, after Feynman, which proposed this term in the Feynman lectures in physics, talking about analog models. And so in this work, which is the one I presented here last year in Portugal, we assume that we try to propose a concrete at least a toy model of black hole evaporation based on such an idea. So we took these fundamental building blocks as fermions, and then we took these are described in they live on a finite dimensional Hilbert space, and these axons were described to be free, basically, inside a black hole. And so while they interacted, when they interact, they form space and matter out of the black hole. So the black hole evaporation is seen in such model as a process of axons which form initially the black hole, then they start interacting, and so they form the environment, so both matter and space out of the black hole. And so the number of axons inside the free axon inside the black hole is steadily decreases, basically. And that's the picture which we used, and this was formalized by this kind of model. The state of the entire system, both black hole and environment, was described in a second quantized language in this way. So A are, let's say, the environment modes, so the axon modes which interacted to form the environment, and B are the black hole axons, so the one inside the black hole. And sigma is an interpolating parameter, which we showed in the paper could be related to the average number of axons which interact to form the black hole. And so we also found the dimension, we also computed that in such model, the dimension of the Hilbert space is related to the maximal entropy of the system, which is identified with the entropy of with the Bekenstein-Hawking entropy of the initial black hole. Okay, and this is the maximum entropy available to the entire system, both matter and radiation, and so this is forming this particular in this particular system. This permits to formulate the Bekenstein bound, and so this was say, I think, interesting. But the problem of this kind of toy model is that it's a toy model, and the reason is that it's a toy model is that here we did division between A and B modes, this environment black hole mode, which is quite artificial. Why? The idea is that we have just one type of fundamental building blocks, not one for modes inside or outside. This is just a convenience division, you know. And so, but that was done because in this paper we did not describe how the matter and the environment are formed into the black hole, and so we didn't explain the mechanism of interaction and mechanism of formation of space and matter. And the way to solve this problem, we thought, was thinking about condensed matter physics. Actually, it's it's known since a long time that there is a strict relation between a classical theory of defects in crystals and the Einstein-Cartan description of gravity. This was studied, for example, in these beautiful papers of Katanaev and Volovic, and also in other papers by Hagen Kleinert, which formulated the so-called word crystal model about on these ideas. And this was also used in building analog models of gravity in direct materials as graphene, for example. And so now the other ingredients to put together with this this fact is also well known since a long time, is that there's a way in quantum field theory of describing formation of topological defects in a full-fledged quantum field theoretical language, say, not in a classical field theory, how it is usually done sometimes for, you know, classical strings, vortices, but in a full-fledged quantum field theoretical way. And in particular, there were studied also formation of defects in crystal with this method, in these also beautiful papers by Wadati, Matsumoto, and Umezawa, and others. And so the idea we had here was to describe our Exons model as a quantum field theory. That's clearly is an approximation, because I told you that one of the implications of the Bekenstein bound was that we have a finite number of degrees of freedom. Clearly, here we assume we have so many degrees of freedom that in a first approximation we can say are an infinite number of the degrees of freedom, and so we use quantum field theory. So we can use this boson method, which was developed by Umezawa and others, to describe formation of topological defects. And so the emergent description that would be like the one of a crystal with defects is known, is related to Einstein-Cartan gravity. This was done by Kleinert and the others. So we put together, basically we put together these ingredients. This was not trivial, a trivial task, but that's the basic idea and the basic goal we wanted to reach, to put together these two things. So first of all, I think I should describe to you what is the boson method. That is the framework we use in this work. Okay, so that's why that's explained the title. We think that this process happens, for example, in black hole evaporation, Okay, so we have this such fundamental degrees of freedom which interact and form space and matter. And this is done through this mechanism, basically, of defects formation. And then we have an emergent picture, which is the one of quantum matter living on a curved space. I go more into details, but this is what I was saying to you. So from fundamental quantum theory, which in materials, like in solid state physics, in real, let me say, in low energy crystals, is basic theory is the quantum electrodynamics. And then from this, through this boson method, you can describe formation of defects in a crystal. And then we have emergent description, which is the one of crystal gravity. The idea is the same, but applied to our high energy context, basically, from exons to the real gravity. That's the idea. So what is the boson method? To explain this, I must give you some formal definition of quantum field theory. And so let's start with a quantum field theory for field psi. And then this field psi satisfies some field equation. Lambda is a differential operator. And then such equation can be equivalently rewritten in a so-called Young-Feldman form. So that's quite clear. Lambda minus 1 is a green function, really, of lambda. And psi 0 satisfies free field equation. And then now this equation written in this form, it's evident it can be solved by iteration. Iteratively solved, and we will have basically an expression of psi in terms of psi 0 when we do so. And this is called dynamical map or Hag expansion after Rolf Hag. And it's formally written in this way, the equation in the blue box below. And so I want to give you an example to stay concrete. Let's consider a real scalar field. Psi is, in this case, a real scalar field with some potential term V psi. And then lambda is the usual Klein-Gordon operator here. And the Young-Feldman equation can be written in this way if we choose as a psi 0 the incoming asymptotic field. Here we are in relativistic quantum field theory. And then it's known since long time that the formal solution of this equation, it's the one in the blue box below. And this is the dynamical map for this example. So you can see we have psi, and psi is written as a series where in powers of psi in, basically. Okay, we employ normal ordering, but this is a technical, just a technical issue. And the coefficients in this example are truncated, connected, retarded green functions. Okay. So this is, you can find in classic textbooks as this one of Schweber, for example. So this is the dynamical map in this concrete example. So in this case, we have psi as a function of psi in, basically. This expression here is this one for this particular example. So if it's okay, we can go further. And we can do the composition. We will do in the following the composition of psi 0 in terms of some field psi, phi 1, and phi n. We are decomposed in terms of some fields, and it will be clear, I think, in a moment, why I use this notation. I single out this small psi and this phi 1, phi n. Okay, so in this case, the dynamical map can be written in this form. Instead of psi 0, we have a psi of small psi, phi 1, phi n. Now, if phi, as it would be in our examples, are scalar fields, we can perform the following canonical transformation. So we shift these phi fields by C number function fj, and now there's a beautiful theorem which was proved by Umezawa and collaborators a long time ago, that says that if f, okay, or better, if phi f, this transformed field, satisfy the same equation as phi, okay, the non-transformed field, then you perform the following, the boson transformation, this shift inside the dynamical map. What you obtain is still a solution of the original problem. So it's still a solution of our field equation. I just remind you, you see the equation above, lambda psi equal j. And the same holds for psi f, so the transform field, basically, or the field where you transform the scalar field inside. Okay, so this is known as boson transformation theorem in this school because it permits basically to find an entire class of solution of your original problem, starting from a particular solution, which are parameterized by this function f. Okay, and what is good for this theorem? This becomes very interesting when f is a non-Fourier transformable function. For example, when f diverges at infinity, for example, and in this case, it's shown that such kind of solution of psi f describe your original quantum modes interact and together with some classical solution, which are solitons, basically, which are soliton solution. Or in the case we are interested now, other case in which this f is non-Fourier transformable is the case where there is some point which breaks the Schwarz theorem, basically. And so you have non-commuting secondary, non-commuting derivatives on some points. And this is the case which permits to describe formation of topological defects. Okay, this singular function f will be related to topological defects. And in a slide, basically a couple of slides, I will give you a concrete example, quite standard example of this. And so this is interesting because it permits to describe, this is quantum field theory. So psi is an operator acting on a defined on a Hilbert space. So to describe formation of topological defects beyond classical field theory approximation. And so in particular, now we are interested in the case of a theory which is symmetric under the action of some Lie group G. Here we write the Lie algebra generator. And then we have spontaneous, we consider spontaneous symmetry breaking of such system. And so now you can understand the notation I used before, because then for me, psi is basically the field which interpolates psi, at least at the linear order of the dynamical map. Small psi is the field which interpolates capital psi. And the phi 1, phi n will be the Nambu-Goldstone modes. That's why I use this kind of notation. I singled out the small psi. And then in such case, it can be shown that the psi f, the transform field, can be decomposed in this way, in as a product of this U, which is classical gauge transformation of group G, times psi tilde, which is a regular is an operator, but it's a regular function. Okay, so does not contain f, for example, or contain f through some combination which are Fourier transformable, basically. And because U is a classical gauge transformation, which depends on f of the function of the boson transformation, I just show you once more. Okay, function which shifted the field. Then it's natural to define a gauge potential, a mu, and the relative field strength. Okay, and so this a mu, it's clear that this a mu and f mu nu are there because there is f. In particular, these are classical gauge transformation, are not quantized. Okay, the idea is that when you have the formation, the physical idea is that when you have formation of topological defects, then you can describe the effects, basically, of such topological defects through the through some classical gauge potential, basically. And but also this is in other forms is known since a long time. There's the double book of Hagen-Kleinert, for example, of application of gauge fields in condensed matter, where it spends quite long time of description of topological defects through gauge fields, classical gauge fields. So it's nothing revolutionary if you know that condensed matter stuff. Okay, but here is described in a full quantum field theoretical way, which is quite cool for me. Now I give you just an example, which I think is familiar for you, which is the one of psi to fourth theory. So psi is still, as in the previous example, I gave a scalar field, but now it's a complex scalar field. And all we know that this, we all know that this model, when mu square is smaller than 0, there's a spontaneous symmetry breaking of U1 symmetry. Okay, and vacuum expectation value of psi is this one. Now let's decompose psi in a radial part and in a phase, and the equation, the field equation, which are derived from the Lagrangian, can be written in this way as coupled equation. Okay, and so we redefine a couple of parameters. Positive definite mass squared. And now we want to write the dynamical map in order to apply the boson method. And to apply the dynamical map, we have to identify the asymptotic field, which is our psi 0, which now is an incoming field, which satisfies three Klein-Gordon equation with the positive mass square, which was defined below in the slide here. Okay. And then also this field we can decompose in a radial way in rho in a radial part, and chi in, which is the Nambu-Goldstone mode. And such field satisfy coupled field equation. You know, the equation which are above are basically the Klein-Gordon equation for psi in, just written in this decomposed way. With this decomposition, and that's why here, that's what I did here above. You know, I decompose psi in basically in a radial part, which is the small psi, and the Nambu-Goldstone modes. which will be in the phase of the phi 1 and phi n. That's exactly the same, but this is a general notation of what we do in such a particular example. And then it can be proved now I don't enter into details, but that the dynamical map, so psi written as a function of psi in, can be written in this very compact form. Okay, where L int is the interacting Lagrangian in the interaction picture, and P is a time ordering operator, and C is a closed time path, a la Schwinger. If you are familiar with thermal field theory, you you know what I'm saying. If you are not familiar with this, it doesn't matter. It's a formal expression. It's not important to know precisely what is the path. What is important is that now we can use this expression of the dynamical map to perform a boson transformation on the Nambu-Goldstone mode f chi, and so we perform chi, which go in chi minus f. And so you see, because the interaction part in this model does not depend on the Nambu-Goldstone mode, but only on rho, the only effect is that we have a phase, where our field psi f acquires a phase, and now we can from this expression, comparing with this one, you see, when the one in the blue box, you can see that psi tilde is basically, in this example, psi tilde is just psi, while u is e2 minus if. Okay, and as I anticipated, is a gauge transformation of our symmetry group, which was U1. This is a U1 transformation. And then we can define, by using the definition, gauge potential in mu, which is just a gradient of f, and f mu nu, which is the commutator of the second derivative. And clearly, only if f is non-regular in some points, so it satisfies this condition, okay, only in that case we have a non-trivial physical, an interesting physical consequence, because we have a non-trivial field strength, classical field strength. And this, as I told you, it happens when we have some topological defects. Just to give you a concrete example, a vortex, or you can see a relativistic string along the z-axis, is described in this language when f is equal to theta, mean the azimuthal angle in cylindrical coordinates. Okay, so in that case, we have this is a mu is a gradient of theta. Only the spatial part survive. Okay, and f mu nu is a field which is along the z-axis. And so you resemble the situation that you have in Aronoff-Bohm type experiments, basically. Okay, so just to show you that this machinery works, and this is phi-4 theory is a quite familiar example. But this a simple example contains basics of what we did, then what we try to do actually in the context of gravitational physics. And also, just I want to let you know this coupled equation, then applied to our context, will be some coupled equation between the Nambu-Goldstone modes that I will show you in a couple of slides will be in our context the responsible for the emergence of a non-trivial space structure, and rho, which will be some quasi-particle field, so the matter. And so in the spirit, let me say, these are prototypes of quantum gravity equation, you know, that should describe the interaction between matter and space, substantial. Okay, so the matter, which is rho, and the space, let me say like this, is the Nambu-Goldstone mode. So this will be both quantum. If you perform the boson transformation and you take the, for example, the average, the vacuum expectation values, this should be both Einstein equation. That's the hope. We didn't go so far, but this should be Einstein equation and, for example, Dirac equation in a curved space. Okay, that's a
Hi,
prototype.
Luca.
Tell me.
Yeah, you have 5 minutes.
Ah, perfect. Okay, that's, I will go fast, but what I wanted to say, it's all in this. Sorry, so that's I can skip, but I hope I explained the idea. We start from some quantum field theory, which is an approximation of our exo model. And then we have some spontaneous symmetry breaking. In our paper, we assume E3, so a Euclidean group in 3 dimensions, symmetry breaking. There's no time in this this description, as in other quantum gravity scenarios. And then we have formation through the boson method of we can describe of topological defects, and this is perceived as a curved space. Okay, we have also non-trivial torsion in general. Okay, so that's the idea. We have in our case, in this case we have a doublet, which is a spin doublet, and our symmetry group is E3, not U1 as in the previous example. So these are the Nader charges. And then, okay, here there's a technical part. It's quite interesting, but maybe I can go fast, which is how to count Nambu-Goldstone modes. And result is that in order to have 6 Nambu-Goldstone modes, which corresponds to the number of broken generators, if you are breaking E3 till a discrete group, not to a continuous subgroup. And then in order to have 6 Nambu-Goldstone modes, you need a non-trivial action of the spin operator on the vacuum. So the case which is below on the right. Okay. Otherwise, you have a linear if you have S over the vacuum, which is even S annihilate vacuum, basically you have a linear dependence of the Nambu-Goldstone modes for rotation and translation, symmetry breaking, which is the situation you have usually in crystals when you have only 3 Nambu-Goldstone modes, which are the acoustic phonons. Okay, but in general, what we discovered, and this was very non-trivial, took me months to be realized properly, is that if you have non-trivial spin structure, you can have 6 Nambu-Goldstone modes, and you can describe also non-trivial emergent curvature of space. And so we applied all the machinery I described until now. You have some psi and some quasi-particle field, psi 0. Okay, then we do a radial decomposition of psi 0 in terms of small psi and Nambu-Goldstone modes. This is the case in which the spin annihilates the vacuum. And in the simplified case, we have only 3 Nambu-Goldstone modes, so like the acoustic phonons in a crystal. You can perform your boson transformation, so you have some kind of deformation function. And U is it's a gauge transformation of the translation group in this case. And then you, as I've shown in the previous examples, you can define a classical gauge potential, and that now can be identified with the triads, with the field binds. I remind you that there's no time in this approach. And then you can define a metric naturally from this, and you can see that the condition of non-commuting derivatives will lead to a non-trivial field strength, which in this case is a non-trivial torsion. So basically, we showed here that starting with a quantum field theory in which we have formation and topological defects, the boson method permits to describe a formation of a non-trivial torsion of space. If you start from if you are the spontaneous symmetry breaking of the Euclidean group into a discrete group. We can do the same in the general case in which we have S over a non-trivial spin structure in the vacuum. And then in this case, we have 6 Nambu-Goldstone modes. Still, we can perform the boson transformation. And then we have the dynamical map that can be written in this way. And in this case, we have a classical gauge transformation of the entire E3 group. And but now the gauge potential, gauge field contains both triads and spin connection. And the relative field strength that you have in the case of defects formation are curvature and to both curvature and torsion. So a kind of Riemann-Cartan theory. And so, okay, here I gave a concrete example in which we did an ansatz of the decomposition of psi 0, where, as I told you, small psi is basically the radial part, as in the scalar field example, and the Nambu-Goldstone modes appears in the phase. And then, if you use such a decomposition, and in the case in which our differential operator is linear, what we derive, this is not put by hand, basically it's derived, is that small psi satisfy this equation, which is basically the equation of a fermion field on a curved space, basically. Okay. Just this is a these are 2x2 matrices, are not really the Dirac matrices. But the structure of the equation is the same as the Dirac equation in curved space-time, which is, I think it's quite non-trivial. And it's a part of what I was telling you before about the coupled equation in the scalar model. What we get is this result. We are describing both the emergence of quantum matter, which lives on curved space. And so, in conclusion, we said black hole evaporation by Bekenstein bound, we assume can be described in terms of interaction of some fundamental building blocks. And in order to describe such interaction, we use these boson methods in quantum field theory. And this boson method permits to study emergence of a classical geometric tensor like curvature and torsion and non-trivial metric, together with quasi-particle fields living on this curved space, as in such equation below. And okay, this can be equally applied also, we hope, to some condensed matter system. We are working on it, and thank you for the attention. I'm sorry if I was too long.
Thank you very much, Luca, for the very nice talk. Please, any questions from the audience? Please raise your hand. maybe, yeah, we have a question from Marco. Marco, please.
Yeah, hi.
Hi.
Hi, Luca.
Hi, Mark.
Just a, I don't know, clarification.
Mhm.
So you said that in your case, you use fermions with
Yes.
spontaneous symmetry breaking. And in the end, you get this Dirac looking like equation, right?
Yes, but it's a, you know, are actually are just spinors, not bispinors. So gamma
Yeah,
mu.
okay. But this is so if I understood correctly, with the other example you gave, the one with the scalar 5 to the 4 theory,
Yes.
you have two equations, and then you said in the end the goal would be to have one equation representing the equation for matter and the other equation being,
Exactly.
I don't know, the Einstein equation coupled to matter.
Exactly.
So what's the other equation in your case?
In my case, yeah, in my case, the equation I used is actually it's not so easy to to single out one of these two. What I did is I took the equation for psi, like the equation for psi here. You see the Klein-Gordon equation. Okay, and so I inserted the polar decomposition, and I performed the boson transformation. So let me go back. So you take, you start from the equation, where it is, right? I need, you start from the equation for psi, okay? And that linear order, you put psi equal to psi 0, okay? That's just a first order approximation in a dynamical map. And then if you apply gamma mu de mu to psi 0, after you have performed the boson transformation, you apply to psi 0 u theta, the one in the second row, and you take the vacuum expectation value, you derive this equation, basically.
Yeah, okay, this is how you derive the equation in the blue box.
Exactly.
Don't you have the equation for the analog of the Goldstone bosons?
Hey,
Where's
yes.
the Einstein equation?
Exactly, exactly. No, we didn't write. Because your equation, we didn't go far in this sense.
Okay.
This was simpler, basically, but the other task is more complicated, actually.
Okay.
Even because there's, as I told, there's no time here. So in order to derive proper Einstein equation, it's a more difficult task, I would say.
No, okay, but maybe it's, I mean, also this one is not the real Dirac equation, right? But
exactly,
maybe something that start to look like an equation for geometric quantities.
No, it should be the equation of for the Nambu-Goldstone bosons, as you told. You perform the boson transformation, and you take the vacuum average, basically the vacuum expectation value. That should be basically the Einstein equation, because the equation for the Goldstone boson, as in the scalar case, is coupled with the psi field, with the small psi field, and so with matter. But because we don't have a specific model, it's very hard to say much more than this. That's the point.
Yeah, okay, thank you.
Thank you for the question.
Okay, thank you very much. So maybe we will postpone any remaining questions to the discussion session. And then I think it's time to move to the next speaker, Roberto Percacci.
Hi, Slavan.
Hi, Roberto. Good to see you. Yeah. Please share screen. Okay, so our next speaker is Roberto Percacci, and he will tell us about some results on quantum metric affine gravity.
Is it full screen now?
Not yet.
What's this? Maybe I should go full screen before split. I'm not sure how to do that.
Yeah, I still see the.
Okay.
I think yeah, now it's working.
Yeah, now it's full screen. Yeah, great.
Good.
Okay.
So okay. So first, thanks to organizers for inviting me to talk here, and apologies to those of you who have already heard this because I gave similar talks recently elsewhere. But I promise that there will be some new material towards the end. So I'm talking about metric affine gravities, which are theories of gravity where you have independent metric and connection. I will call them MAG in general. And the notation I use is the following. For the independent connection, I use Young-Mills notation. So the coefficients of the connection are denoted A, the covariant derivative is D, and the curvature is F. Whereas for the Levi-Civita connection, which is always there because there's a metric, so you can always construct also Levi-Civita, I use typical general relativistic notation. So the coefficients are called gamma, the covariant derivative is nabla, and the curvature, the Riemann tensor is R. Okay. So these are also called in the literature gauge theories of gravity. And so let me spend a slide here on the question of what is the gauge group. Now, in general, this is not a physically meaningful question because the same theory can be presented in various ways where you can have larger or smaller gauge groups. So we are familiar with two formulations usually, which are the usual metric one, where one uses coordinate frames, and then the gauge transformation are just the diffeomorphisms. And then there's a tetrad formulation where one refers to orthonormal frames. And in this formulation, the gauge group is larger because in addition to diffeomorphisms, it also contains local Lorentz transformations. So one can further actually enlarge the gauge group to having local GL4 transformations. The motivation for this is twofold. The first is that physics does not depend on the choice of frame in the tangent bundle, and so you could choose frames which are neither coordinate frames nor orthonormal, just arbitrary linear frames in the tangent bundle. And then the freedom to rotate these frames, to transform these frames one into the other, corresponds to local GL4 transformation. And the other reason is that in general metric affine gravity, the holonomy of the connection is GL4. And therefore, it makes sense to present the connection as a gauge field for the group GL4. And in order to do that, you have to work with arbitrary frames. So this GL4 formulation is a little bit less familiar. So let me show here a slide where I introduce the fields. In this formulation, you have the frame field theta A mu and the fiber metric GAB, which are independent fields now. So mu nu indices refer to coordinate bases, and AB indices refer to these frame bases. So the relation there's you can reconstruct the metric in the coordinate frame G mu nu from the fiber metric and the frame field by this formula. And the formula here in the bottom of the page. It's important to notice that both the fiber metric GAB and the frame field are actually nonlinear objects because they are subjected to constraints. The metric is subjected to being non-degenerate and having a fixed signature, and the frame field is subjected to the constraint of being non-degenerate. So the metric actually is an object with values in the coset GL4 divided 013, and the frame can be thought of as being an element can be represented by a map from space time into the group itself. So these objects carry nonlinear realizations of the group GL4, and we can think of them as Goldstone bosons. And the group of local GL4 transformations acts on these fields by left multiplication on the frame and by similarity transformation on the fiber metric. And these actions are transitive, which means that I can bring either theta or G to a standard form. This corresponds to two unitary gauges for GL4. If you put theta a mu equal to the Kronecker delta, this means that you are working in coordinate frames, actually. Then there is no longer distinction between Latin and Greek indices. You don't need to talk about that anymore. And this is the standard metric formulation, where GL4 is completely broken. You remain only with diffeomorphisms. On the other hand, you can exploit the second transformation and bring G to a standard form, where G becomes equal to eta. This formula here, where you have eta, tells you that theta is just Hilbein. And so this corresponds to working with orthonormal frames, and the group GL4 has been broken down to local Lorentz only. But importantly, there's not enough freedom to fix both theta and G to a standard form. So there's always one of the two fields that remains even after fixing the gauge. So when you have an independent connection, then you can construct the covariant derivatives of these fields. Now, the exterior covariant derivative of the frame field is called the torsion, and the covariant derivative of the frame with the fiber metric is called the non-metricity Q. And then, of course, you can construct the curvature of the connection A. So you have these three ingredients out of which you can construct your action. And so here you see in this general GL4 formalism, T and Q have to be thought both as covariant derivatives of the Goldstone bosons. So then in this presentation, the action will depend on theta, on the frame field, on the metric, and on the independent connection. And it will contain powers of T, Q, F, and covariant derivatives. So I call this a presentation of the theory the Cartan view of metric affine gravity. As I mentioned already, there's a Levi-Civita connection whose general form is written here in an arbitrary frame. The curvature of the Levi-Civita connection is a Riemann tensor. And now, being given the independent connection and the Levi-Civita, the difference is a tensor that I call phi. This tensor is called the distortion tensor. You can then further decompose algebraically the distortion tensor into two pieces, one of which carries all the non-metricity and one carries all the torsion. And the inverse relations are written down here. Torsion and non-metricity are just different linear combinations of the components of this distortion field. Now, given an action for a metric affine gravity in the Cartan formulation that I gave above, you can now decompose this A into Levi-Civita plus distortion. But Levi-Civita itself is a function of theta and G. And so you can think of this as a new function which depends on theta G and the distortion field. So in this alternative way of looking at the theory, you don't think of the connection as being a new variable, but a distortion. This is just a change of variables, so physics doesn't change. In this new formulation, the action S prime will contain the tensors T, Q, and R, and Levi-Civita covariant derivatives. I call this the Einstein way of looking at metric affine gravity. And in this way, gravity looks like a metric theory, because here you have just basically the metric with a new field phi, which you can think of as a sort of matter field. So every metric affine gravity theory can also be thought of as a metric theory of gravity coupled to some matter field. You can impose kinematic constraints on these theories by declaring some of the fields either T or Q or F to be 0. So if you put T to 0, you have here on this side what we call symmetric mag, because in this case the distortion tensor is symmetric in some indices. If you put Q to 0, the distortion tensor remains antisymmetric in some indices, so we call this antisymmetric mag. If you put both Q and T equal to 0, you are here on this vertex, you have ordinary metric theories. And down on the bottom, if you put F equal to 0, you have teleparallel theories. And in particular, you can have either symmetric or antisymmetric teleparallel theories. This kind of diagram was taken from a paper of Heisenberg and Koivista and others, where they discussed various equivalent reformulations of GR. But this is actually independent of the dynamics. This is purely kinematical. Now, regarding the dynamics, well, there are many. Let me skip this. In the literature, you will find many different possible actions for metric affine gravities, but let's try to be systematic and analyze the possible Lagrangians according to their dimension. So let's discuss all the Lagrangians which contain operators of dimension 2 and 4. I want to spend a little bit of time on this because it's important. The first line contains dimension 2 terms only. So the first one is just the Palatini term. So F is just F mu nu mu nu. And the remaining two, so remember that F is an operator of dimension 2, whereas T and Q have dimension 1. So T squared, TQ, and Q squared are also dimension 2. And the coefficients A here, ATT, ATQ, AQQ, and AF are all of dimension of mass squared. In particular, AF you can think of as a Planck mass squared. And the remaining terms have dimension 4 and have dimensionless coefficients C. So first of all, you can have terms quadratic in the curvature F, but you can also construct other terms that are quadratic in F and T and Q of the form F dt or F dq or dt square or dt dq or dq square. So the terms in these two lines being quadratic in F, T, and Q all affect the propagator of the theory, the propagation of the fields around flat space. Whereas in the last three lines, we have terms cubic in F, T, or in Q. So it's either FTT up to FQQ or TT up to QQ and then which are cubic, and then terms quartic of the type TTTT, and then various mixtures of them up to QQQQ. So there's a large number of terms that one can have in general, as you see. This is written in Cartan variables. There's a similar classification in Einstein variables. The counting of terms is done here. In Einstein variables, the counting is relatively easy. If you wanted, as you see, for example, in antisymmetric mag, you will have 3 terms of the type R square, 9 terms of the type 2 terms of the type R nabla T. So these 3 columns here give you the propagator, and the remaining 3 columns give you vertices. So you see there are 92 terms of dimension 4 in this case, and even more for symmetric mag and for the general mag. Doing the same counting in Cartan variables is very, very tricky because there are more contractions that you can form and many more independent relations. But in the end, then of course, the number of independent terms is the same. Now, in addition to just restricting to symmetric or antisymmetric mag, you can impose further constraints. For example, you can say that torsion vanishes and non-metricity is proportional just to a vector times symmetric. So this will give you theories which correspond, which are essentially Weyl theory, and in Einstein formulation, they're equivalent to metric gravity coupled to a Maxwell field. Now, the dimension 2 terms are essentially, you can give rise to masses for the connection. So if you, in Cartan variables, remember that T and Q are covariant derivatives of the frame and of the metric. But if you expand around, if you assume that the ground state of the theory is flat space with A0, theta is 1, and G is the Minkowski metric, then T and Q are just arbitrary, algebraic combinations of the components of the connection. And so they become just so this first line, expand around flat space, just gives you some mass term for the connection. So this is a form of a Higgs phenomenon, because it is the essence of the Higgs phenomenon is that the kinetic term of the Goldstone bosons, when written in a unitary gauge, is just a mass for the connection. And in general, this mass matrix will be non-degenerate, and so all the components of the connection will be massive. The Palatini term also contributes to this because it contains, the curvature contains a part which is quadratic in A. And so in particular, this gives a Planck mass to some components of the connection. But there can be components which remain much lighter in principle. In the Einstein view, this independently of the choice of gauge and of the background, it is true that torsion and non-metricity are just these linear algebraic combinations of components of the distortion. So T square and Q square are just mass terms for the distortion. So if the mass matrix is non-degenerate, as it would be in general, assuming all the masses are of the same order and that you look at the theory at momenta much lower than that mass, then the dynamics will force the distortion to be zero, and equivalently torsion and non-metricity to be zero, and equivalently the connection will be the Levi-Civita connection. So this can be the fact that we have a Levi-Civita connection in gravity at low energy is a general fact that comes from this kind of phenomenon occurring at some scale. So these conditions, actually T0 at Q0, are analogous to the condition that the covariant derivative of the Goldstone boson is zero in superconductivity, which is the Meissner effect, or similar conditions in the electroweak chiral perturbation theory, which is the theory of electroweak interactions at masses below, at energies below the sufficiently low energies. So then, as I said, there are two scenarios. One is that all the masses are of the order of the Planck mass. And then if you think of this as an effective field theory, it is indistinguishable from the ordinary effective field theory of gravity at low energies, because there are no new states beyond the graviton in the range between 0 and Planck scale. But there may be also some lighter states, in which case the theory would be richer. Now you may ask, what kind of states can we expect? And so the answer is in these two tables. The fluctuation of the frame is an object with two indices, and the fluctuation of the connection or the distortion are objects with three indices. And so a tensor with two indices can be decomposed in its symmetric and antisymmetric parts. And then depending on whether the components are transverse or longitudinal, these give different degrees of freedom, with spin 1, for example, in the antisymmetric case, and spin 2, 1, and 0 in the symmetric case. So this spin 2 plus, so plus and minus indicate the parity instead. So 1 minus is an ordinary vector, 1 plus is a pseudo vector, 2 plus is an ordinary spin 2 field like a graviton, 0 plus are ordinary scalars. Now, the 3 index object carries a lot of structures, and the highest spin that it can carry is a 3, spin 3 object, which will have parity minus. But there are also several spin 2 plus, which are objects which in principle can mix with this graviton contained in the metric. And there are also some strange objects which have spin 2 but negative parity, 2 minus, which are here. To explain this table, TS means totally symmetric. HS is a hook symmetric tensor, which means symmetric in a pair of indices but has 0 totally symmetric parts. HA are hook antisymmetric, and TA are totally antisymmetric. So you see that there are many spin 3, 2, 1, and 0 components here. And in order to deal with these objects, you have the right formalism is the formalism of the spin projectors. This is quite familiar for objects with two indices like the metric, but it's been worked out also for the 3 index fields. In this formulation, once you're given the kinetic term for A and H, so it will be something like A and then some operator A some operator H, and then H some operator acting on H. Then you can rewrite this whole thing in as in this second line, where Pij are the spin projector, Jp are the spins and parities, and these index Ij label the different copies of different replicas of the same spin parity that occur. For example, if we go back here, for spin 2, you see we have 4 copies, which we call 2 plus 1, 2 plus 2, 2 plus 3, and 2 plus 4. And so this 1, 2, 3, 4 is this index I that I use here. And so these spin projectors come with coefficients in front, and these coefficients themselves are matrices. So these are the matrices of kinetic coefficients, which describe the propagation of the fields and eventually the mixing. So in the case of the spin 2 plus, for example, this matrix Aij is a 4x4 matrix, which describes the possible kinetic mixing between all those 4 copies, 4 potential gravitons, of which one we want to be massless, and the others typically will be massive. Okay, so that's the formalism. And with this formalism has been used for the antisymmetric mag by Sezgin and van Nieuwenhuizen in an old paper. This was Sezgin's PhD thesis. And it was used to look for ghost and tachyon-free metric affine gravities. And this has been then generalized to symmetric mags and more general mags in these other papers. Now, let me just give some examples. For example, suppose that you consider a symmetric mag and you impose projective invariance. which means that the Lagrangian has to be invariant under these shifts of the connection by a vector. And let's further impose that there are no spin 3 particle and only one massless spin 2, because we only want one graviton. Then the action boils down to this 5-parameter family of actions. In general, remember if we look at this table here, a general symmetric mag will have 16 plus 4 plus 3, 23 parameters describing the propagator. But here in this case, by these assumptions, we've boiled down to just 5 parameters. So if you're not, so the parameters are C7, C11, and then A0, A6, A7, A8. And if you impose these inequalities on these coefficients, it turns out that the theory will have no ghosts and tachyons. So there are whole families with several parameters of such theories with good propagations, but notice that they are of measure 0 in the big space of all metric affine gravities. So in this case, they have 5 parameters in a space of 23 dimensions. This particular case is interesting because when you put it in Einstein form, it contains no R² terms, which you could say is the reason why in this case, and it's non-renormalizable. You can also do a different thing. You can start from the general theory and impose conditions on the coefficients in such a way that only one type of field is propagated. So I mentioned earlier these strange spin 2 parity minus fields, which are carried by, which must be represented by 3 index tensors. So here it is the contortion K. And if you impose that the mag Lagrangian only propagates this field and nothing else, then you get a lot of relations between the coefficients. So you see that all the terms here have fixed coefficients, except for this overall parameter B1 PT in front. So this is the Lagrangian that, so you see, there's this general field called relativistic equations of motion, you know, like Klein-Gordon, Dirac, Fritz-Pauli, and so on. And this is what gives the relativistic wave equation for spin 2 field with parity minus. Similar exercise for the spin 3 on a symmetric, on a general mag. It gives you, leads to this Lagrangian, which is of the type nabla Q squared. All the coefficients are fixed except for one overall coefficient. And so this just propagates a single massless spin 3 state. When you go to, so if you assume that Q is totally symmetric, then this reduces to these 2 lines, which is just a familiar Fronstal Lagrangian, which is well known in the field of higher spin symmetry, higher spin fields. Okay, so let me say something now, something new. I promised something new about quantum mags. Up to now, there have been very little quantum calculations. So there's been some calculation of beta function in certain theories, but mostly with the Palatini action or in general with terms of dimension 2. And so there's been a recently calculation of a beta function in this Lagrangian that contains also dimension 4 term. L1FF is just FABCD, FABCD. And this was the work of my student Oleg Melichev, who defended his thesis very recently. So I want to say a couple of things about technical issues in the calculation of these beta functions. So the Lagrangian just here in Cartan form just contains these two terms, f square and t square, the simplest possible contractions. When you translate to Einstein form, it is much more complicated because you will have Riemann square and torsion square, but there's also then term Riemann contracted with this divergence of t, and then there are several terms of the type nabla t, and there are several terms of the type r nabla t or tt nabla t or t to the 4 even. Okay, so this is, I don't write the terms in the last line because I mean it's would be too much, but this is the complete thing. Now, when you write the Hessian for this theory, so you expand to second order in a fluctuation, you find something like this. So x here is the fluctuation of the frame field, and z is the fluctuation of the connection. And so there are terms with Laplacian, the first term, but then there are also terms where the covariant derivatives are contracted with the fields outside. They are not contracted among themselves. So these are non-minimal terms complicate a lot the calculation of the trace log. And this type of terms also occurs in Yang-Mills theory and in general relativity. And in those cases, they are removed by choosing the Lorentz gauge or respectively the Donda gauge with a gauge parameter alpha is equal to 1. So this is called usually the Feynman gauge in Yang-Mills and in GR. Now, in the case of this metric affine gravity, if you work if you were to work in the metric formalism, you only have diffeomorphism invariance, and you can choose a gauge for diffeomorphisms by declaring, for example, this fluctuation of the frame field to have a zero divergence. This is a good gauge choice for diffeomorphism. And so if you have a gauge fixing term which is quadratic in nabla x, integrating by parts, it gives you a term of the form x nabla x of this form. And in that way, you can remove this non-minimal term. But then you're stuck with a non-minimal term for z, you see? You don't have any freedom then to further fix the gauge so that this term goes away. So this is why, in reality, it is much more convenient in these theories to work not with the minimal formulation in terms of a metric, but with this larger gauge group. So in this particular case, it's good to work in the tetrad formalism where you have also Lorentz gauge invariance. And so you can gauge fix diffeomorphism with this term, which I already mentioned, and you can fix the local Lorentz invariance with this term, nabla mu z mu. So when you expand it, you see this gives you x nabla x, and this gives you z nabla z, which you can use to cancel the non-minimal terms in the Hessian. Okay, so this is and the cancellation occurs if you choose these gauge parameters alpha d and alpha l to be equal to 1. So this is, again, Feynman gauge for this metric affine theory. I don't know that this will work in general. It works at least for this particular Lagrangian that we have studied. But then in this case, the rescaling the fields, the kinetic operator becomes this matrix. So you see you have a Laplacian term. You don't have non-minimal terms. You will have a term linear in derivatives and then terms without derivatives. And well, from the gauge fixing, you also have to derive the ghost action, which is contains diffeomorphism ghosts C, and the Lorentz ghosts sigma, and the anti-ghosts. And the Faraday-Popov operator is again a matrix. LL is a Lorentz Faraday-Popov operator, is written here. DD is a diffeomorphism Faraday-Popov operator, and then there are these mixed ones. Anyway, all the operators occurring are of the type Laplacian plus term linear in derivatives plus W, and we know that the logarithmically divergent part of such an operator is given by this formula, which is all in function of V and W. And omega mu are the curvatures of the connection. And so you just have to plug in the explicit forms and patiently work out the result. So these are the log divergences in Einstein form. And then actually we are more interested in the ones in the original Cartan form. So I've used a somewhat synthetic notation here. So these LFF, the first two lines, are termed quadratic in the curvature. So in particular, L1FF is
Robert, do you have 5 minutes?
Yeah, I'm about to finish. L1FF is just the original term in the action. So that this 76/15 is the coefficient of the logarithmic divergence proportional to that term. This renormalizes that term, and it also gives you the beta function for its coefficient. But you also, unsurprisingly, you also generate all other terms. So these in FF terms are quadratic in curvature, FT are of the form F nabla T, and the TT terms are terms quadratic in derivative of T. And then there are dots because also all the terms of dimension 4 actually get generated in this way, also the cubic and quartic ones. We haven't computed the coefficients of all of them because it's too much. We are mostly interested in the terms that affect the propagation. So the lesson here is that, as I said, unsurprisingly, a single dimension 4 term generates all the others. But in this particular case, you can get rid of all of them by field redefinitions because we have this term A1TT in the Lagrangian. And so if you perform a field redefinition of schematically of the form delta T is nabla nabla T, and you apply this transformation to TT, you will generate T nabla nabla T. And integrating by parts, it becomes nabla T. So in this way, you see, it turns out that you can generate all the terms of this type by these field redefinitions. So all these divergences can actually be reabsorbed by these field redefinitions. This is somewhat similar to what happens in GR. You generate terms of the type Ricci square and R square, and you can absorb them in field definitions. So it will be interesting to study other examples of mags from the point of view of this of its quantum properties. So the summary here is that metric affine gravities are a huge class of modified theories of gravity. And well, since this is a conference also on cosmology, I had just this short remark to make that if these theories offer some explanation for unexplained phenomena in astrophysics and cosmology, I don't know, like rotation curves of galaxies and so on, which is possible in principle, then it doesn't really make much sense to argue whether the solution is a modified gravity or dark matter, because in these theories, as I said, they can be presented in two ways, which in the Cartan form they look like modified gravity theories. In the Einstein form they look like gravity with matter. Well, then there is in these theories there's a kind of Higgs phenomenon that gives mass to the connection and explains why we have the Levi-Civita connection at low energy, which I think is neat. Now you have all these massive components of the connection. If some of those components, well, if all the components have Planck mass, then this is just the same as the effective field theory of gravity at low energy. Whereas if the more interesting situation would be if there are some lighter components of the connection that propagate. So this is of course all. There are many models that one could try to construct of this type. And then, as I said, of course, quantum behavior, we have barely scratched the surface. So there's a lot to be still understood. Thank you very much.
Thank you very much, Roberto, for the very nice talk. We have some time for questions, and after that we will go to discussion session. Please raise your hand. Meanwhile, actually, I have a question to ask. So there are a couple of questions. First of all, you know, in metric theories, the quadratic gravity is renormalizable, but it has ghost problem. Is that can be cured some way in the metric affine theories?
So if you are worried by ghosts, as I said, you can look in this huge parameter space and find subspaces where the theory has no ghost. But I think that what happens in general metric theories will be true also here, namely, if the theory is renormalizable, it will have ghosts. It has no ghost, it will be non-renormalizable. In particular, this model that I just discussed here, it is power counting non-renormalizable. For renormalizability, you need 1 over p to the 4 propagator for the metric, whereas this has purely 1 over p square propagator for the metric.
Okay, well, I'm asking this question, keeping in mind, sometimes I see in the metric affine theories, there are 2 metrics, so-called bimetric theories. I'm curious, instead of having one additional graviton in the metric theory, which happens to be ghost, but can it at all possible to have some bimetric theory, but still somehow you achieve good properties for UV completion?
Well, that's possible, but I don't know, because these metric affine gravities are just one metric and one connection. So if you want to have an additional metric, well, that's you can do it, but it's not contained in my talk.
Okay. We have a question from Ilya.
Roberto, hi. Nice to see you again. So I have the following question. In this last part with the calculations with Oleg, when you say that on shell you can remove all these terms, first of all, this means typically that these terms can be removed by gauge fixing choice. No.
Field redefinition is more general than gauge fixing.
Sure. Not necessary, but it's possible. But another question, did you actually check this? Because it seems that you are based on some dimensional reasons or something like that, or you checked that you can remove all these terms. Because in principle, it might be that the type of the terms you can move, but you cannot remove all of them.
No, in this particular case, you see, since the TT, I start with this TT here, it is just TABC, TABC.
Yeah, I understand.
And here delta T you can put the indices in any way you like. So in this way, you obtain the most general nabla T term. And the same is true for the others. So if this TT had another form, maybe it wouldn't be possible. But with this term, you can get rid of all of them, actually.
Good.
So this,
okay, thank you.
Sorry?
Thank you. Okay, I understand.
Okay, yeah.
Okay. Any more questions? Okay, yeah, we have a question from Alberto. Alberto, please.
So I wanted to ask, so if you impose scale invariance in the system and you work with metric affine gravity, and then you let's say you construct the effective metric theory, how does it look like? Is it just the most general scale invariant metric theory, or what do you get? So I guess in principle you get also some higher spin fields, and do you have some ideas of so if you start from scale invariant metric affine theory?
So the most general scale invariant metric affine theory is the theory that has only dimension 4 terms. So you have to leave out the terms in the first line here. And then I'm not sure what you mean by going to the metric theory, because
what I mean is the following: you write the distortion.
Oh, I mean you mean. Sorry, you mean going to what I call the Einstein form, where instead of using F, you use the Riemann.
Yeah, you write the distortion as a Levi-Civita connection plus a tensor, and then you express everything in terms of the metric, the Levi-Civita.
Yeah. So yeah, you will have in this case. So the most general scale invariant theory of this type will be high derivative gravity, so Riemann square Ricci square R squared.
Mm-hmm.
And then terms of the type R nabla T, R nabla Q, RTT, T nabla T. You will have these instead of the nablas, but you will still have a huge number of terms anyway.
But these terms now, they will contain field plus some spin 2 fields plus some spin 1 field, etc.
Yeah, the counting of degrees of freedom will be the same.
Yeah, but now since everything is massless, can't you exclude some higher spin fields and some spin 2 fields just by these these general theorems that forbid higher spins, massless higher spins?
Yeah, probably. Sure, of course. Then there are headaches with the interactions. So
sorry,
you would, yeah, if you have, for example, the spin 3 field, you will have trouble when you try to construct its interactions. I told you earlier that you can write the propagator for the spin 3 field, for example. But where was it? Here, right? So this is a mag which propagates only the spin 3 field. Imagine that it's linearized around flat space. Then you get a propagator and it's okay. If you now look at the interactions, then you will hit all these problems, which I think I put also a reference down here. Problems about the validity of the range of validity of these higher spin fields as interacting theories.
Yeah. So I was wondering if so if you start from this more general framework and impose scale invariance, and then you go to the metric formulation, if you get let's say scale invariant quadratic gravity and that's it, or you get something else from this consistency?
Well, as I said, you have something else, but whether that something else is a good field theory or a bad one, I can't say.
Okay.
In general, it will have pathologies.
Okay. Right, so
Yeah.
you don't know. Maybe it could be good. Maybe.
Maybe you can look, inside this huge many parameter family. You can find something that is a good quantum field theory. Yeah.
Yes. Okay. Thank you.
Sure.
We have a question from Hongwu.
Oh, sure. So I asked you the question. So the higher spin, as I know, higher spin is not existent in a flat space. What is the mechanism to higher spin exist in this model?
Sorry, you are asking me again if higher spin fields exist in this model?
Higher spin because higher spin because higher spin in a Weber theorem, higher spin in flat space is not exist.
Yeah. So this is.
But this why higher spin exists?
So I should expand what I said to Alberto. In this, so you write this Lagrangian, which seems to be a Lagrangian for a higher spin field, right? Because here this is not only the quadratic part, but this is there's a fully interacting Lagrangian here. So what I said is that the propagator, the 2-point function that you get out of here, is just a normal 2-point function that you get from the quadratic Fronstal Lagrangian. Now, this Fronstal Lagrangian has this higher spin symmetry, which is the shifting S by totally by the derivative of a symmetric tensor, totally symmetrized. And this is what you need in higher spin symmetry. And you have here at the level of the quadratic theory. But this is just an accidental symmetry at the quadratic level. If you look at this Lagrangian, which has interactions, it will not have the higher spin symmetry. And so this is certainly not a good theory for the higher spin fields in general. Although understanding this in detail is something that I still am working out with. I'm working on this with Ergin Seskin. But I think that the conclusion is more or less foregone, that the theory will not be a good theory, because there are theorems, as you said, that forbid such things.
Yeah.
I hope that this was the answer to your question.
Okay.
Any more questions? Okay. Actually, we can go directly into the discussion session.
Yeah. So.
I hope we have all the speakers. Okay, we have Roberto and Luca Smaldoni here. So maybe actually I would like to ask a question to Luca, so which I couldn't ask during his talk.
Yes.
In your talk, you started with writing a state as a direct product state, I mean tensor product state, where system and environment. So basically the interior and exterior of the black hole. Of course, you commented that it is not accurate. You cannot really divide precisely. It is true. It is indeed true. Well, especially if you have black hole evaporations, we have kind of states. If the black hole evaporates, somehow the states in the interior should, the information should come out in some sense. But you are not taking that into account in your study, right? So you're basically treating completely maybe an eternal black hole system.
Yeah, at the end, that was the motivation of the work. Let me say, try to explain how this mechanism, how it works, the interaction between these fundamental building blocks we use, basically. And because as you mentioned, you cannot divide so sharply, between the modes which interact and do not interact. We can say they are weakly interacting, then they will form during the black hole evaporation, the space and matter, and we try to describe this mechanism basically, but clearly we cannot sharply divide. No, it was just mainly a motivation, let me say.
Okay, but I'm curious. Like you have two operators, the creation operators for the interior and the exterior. Do they commute or do not commute?
They anti-commute in this case because are fermion operators.
So the operators in the Hilbert, corresponding to the Hilbert space of the interior, anti-commute with the exterior.
Yeah. Okay, yeah, because they are fermion operators. But the idea is that they are the same, basically. In the sense, the difference between interior and the exterior there is that some of these modes interacted in order to form space and matter out of the black hole. Other modes did not. But during the black hole evaporation, all such modes at the end will interact until the black hole disappeared. It's completely evaporated. That's the idea of the toy model. And so it's just, we just divided in this way. That's the way we were thinking the division between A modes and B modes. That's all. Not that's not something so strange, in a sense that at the end the state I showed you can rewrite as a kind of thermofield state. And this was also was already proposed. A model of black hole evaporation based on thermofield dynamics was done by Israel many years ago, but there are various papers. It's quite reasonable, that kind of structure. I mean, but clearly there's no so strict division in our case. That's why
there is interaction. So because of the interactions, it's not strictly divided, the interior and the exterior. Am I correct?
Exactly, but interior and exterior. The point is that should be emergent concepts. Clearly, at fundamental level, you shouldn't have such kind of. Once you have geometry, basically you can talk about the interior and exterior. And our idea that our also even in the quantum field theory model we use at the beginning we are defining fields over some target space, but clearly that target space has no structure and there's no metric, there's nothing. Basically, it's just are the discrete indices which goes into a continuum label, basically. That's the idea. And so the true geometry and the true structural space in this view, this picture, should emerge after the interaction of these fermion modes, basically. And so the true division between interior and exterior of the black hole are the modes who interacted to form and to form the interior, to form the exterior of the black hole, and the modes which did not interact. That's the division. It's based on the interaction, not on geometric concepts in principle. This should translate into a geometric view, into a geometric picture. And that's what we try to do in this work, starting from a quantum field theory and see how the classical geometry can emerge from quantum field theory. That's the aim of the work.
Okay. And do we have some correction to the entropy?
To the entropy black hole? No. Also because the model is not so advanced, let me say, to do a prediction of that type. I'll say. Actually, we have some parameters in particular in the previous paper, the one you were mentioning. We had some parameters like the number of quantum states available to the black holes and so on. And then we can relate with Bekenstein-Hawking entropy and so on, but it's an identification that we do of the parameters, so you cannot say really there are correction or not, because you cannot, you have to fix the correspondence between these two languages, the space independent, the geometry independent language, and the geometric language. You should map, because we are not in a so advanced state of the research.
But anyway, some correction is expected, so it's surely interesting approach to.
There could be, yes. It actually, if they are, what we did in recent work with Alfredo Iorio and Paolo Castorina from University of Catania, that we were playing with this with these concepts of quantum black holes, and we figured out is that if they are completely free, these modes inside the black hole, then you should have no correction, basically. But still, when you have some kind of spin-spin interaction between these modes, this should lead to some logarithmic corrections, as the one which are predicted in many, quantum gravity theories, basically, called entropy. So it depends if because we logically, I expect they are weakly interacting. Black hole, yeah, I expect some correction.
But what happened with the entanglement entropy of black hole?
In that model, the entanglement entropy is kind of a page. It's a page-like. I mean, start from 0 and ends to 0. Basically, you have no information loss.
Yeah.
It's different when you go to an emergent level. There's a previous work, which by Iorio, Acquavio, and Scholz, where they showed that that was the first paper on this kind of exon model or quasi-particle picture, as you want to. And in that case, they showed that at the level of when you already have division between geometry and geometry and matter, so it's more emergent level. At that level, there are many micro configuration, I mean, at level exon configuration, which corresponds to some macro configuration. I mean, geometry or some matter on some curved space, basically. And so this means this counting on microstates lead to residual entropy. at the end of black hole evaporation. But so you have apparently you have some loss of information. But what we figured out, and that always in this picture clearly, this is just an emergent. You know, it's just some kind of, let me say, macroscopic consequence. But at microscopic level, at this exon level I was showing to you in the first slides, you have no loss of information, and so you have a page-like behavior basically.
The constant boson is in your model, in your theory, is the physical boson or as like Higgs potential.
Can you repeat? Sorry, the question is the physical.
As like standard model. Ghost boson is absorbed by gas boson, but
if there we have a Higgs mechanism in this.
Yeah.
No, because it's not gauge. We have gauge fields
Yeah.
in the game, but are as I mentioned in the talk, are classical gauge fields,
Yeah.
which are related to the condensate function, to the function which describe the condensate of the Goldstone boson. So it's that gauge fields are classical and are useful to describe the interaction of the quasi-particle modes with the defects. Are basically describe a kind of effective potential due to the presence of the topological defects, but are not there in the basic field equation, in the basic Lagrangian. So there's no Higgs mechanism here. That Goldstone boson should be, let me say, the gravitons.
Yeah.
Not in the standard sense, not in the standard sense, because it's not a quantization of the Einstein field, direct quantization on the Einstein field equation. You have it's an emergent gravity theory, but are the quantum modes which are responsible for the classical geometry at low energy. That's in this sense that are kind of gravitons.
This physical Goldstone boson. Yeah.
Yes, physical Goldstone bosons. Yes.
Yeah. In exist there can be a Goldstone, one Goldstone is absorbed by different Goldstone.
So if they can interact with other
effect, inverse effect, yeah, one Goldstone is absorbed by one other.
Sure, we expect that at very high energy, in principle, you can very high energy process, you can they should interact. Trivially, they interact at least with matter, so it should. I mean, their interaction with matter is what at low energy it should be described by Einstein equation. That's the idea. We are not so, you know, we cannot, as I was saying to Marco before, it's we are not at that point of accuracy because we have no specific model. You can say in this, what I showed is an idea how can I say, it's a way of doing, a way of realizing this. We have a formalism which permits to describe these things, and this formalism can be applied eventually to some specific model, but we have not a specific model in this case. Is a set of techniques. How can I say? Is a language.
Yeah.
That should more than. So it's very difficult to say anything very specific in this moment.
Yeah.
The main message is you can start from a quantum field theory of fermions, and with the help of this of the boson method, you can show that you can have an emergent geometric structure, basically, and that you can describe the quasi-particle fields interacting with such effective potential due to the presence of the defects, and that this interaction works like the particle moving on a curved space.
Yeah.
Basically, that's the message. From a basic quantum field theory to a curved space, quantum field theory to a curved space in a curved space time. So where the space or a curved space in this case, because it's three-dimensional. This curved space is emergent. That's what we showed. In principle, it's possible. What is the correct model where this happens? We don't know.
This apply good for holography. Oh,
I don't know if I reply to
holography, IDSFT, DSFT.
Sorry, can you repeat?
This model can apply good for holography, IDSFT.
IDSCFT.
Yeah.
To I don't know if you start from some conformal field theory. No, in principle, yes, I didn't think about connection with the DSCFT, sincerely speaking. I told you the message, I think it's quite sharp. You can build, in principle, you can build a quantum field theory from which you can have an emergent space and matter living on such emergent space. That we show how you can do.
Yeah.
Which kind of model can do it? Is it conformal invariant or not? I don't know. It's it should be done. That's why I wanted to look at condensed matter physics.
Yeah.
Try to apply these ideas to condensed matter physics when you have closer contact with the experiments and more, that was the idea, and eventually try to do the jump eventually to the high energy.
Because I study in IDSFT.
If you formulate a model where you can apply a DSCFT correspondence, I will be very happy to read it. Cite the paper. I will be very happy.
Okay.
Actually, I have a short question. My question to Roberto. I think I'm kind of more or less aware of some experiments dealing which try to measure torsion. But what about non-metricity? Is there any experimental proposal or any experiments really looked into any signature of non-metricity?
Yes, I think there are some bounds that people have put, but off my head, I wouldn't be able to tell you who did this or what the bounds are.
Okay. The bounds with what kind of measurements? Do you remember?
No.
Okay. Yeah. I have okay. I think I will search for this, but it's good to know there are some bounds. So, yeah. I have another question, which is in the metric of n theories. I find it sometimes difficult to understand, for example, space-times. Okay, for example, if you have de Sitter space-time, in the metric theory, you look at the metric and look at the symmetries of the metric, and you can say, well, look at the curvature, and you can say de Sitter space-time. But in the metric of n theory, just the metric itself does not say about the nature of space-time, because you can have torsion and all the other stuff. Am I correct?
Yeah, that's true. But what you would call the de Sitter space in metric affine gravity would be the space where the metric is a de Sitter metric, and the independent connection is equal to the connection of the Levi-Civita connection of the de Sitter metric. At least that's the natural definition.
Okay, okay.
Then you could, on top of this, you could deform the connection in some ways, but I don't know if I would still call that de Sitter space.
Yeah, maybe this something look like a de Sitter from metric point of view, but surely is deformed because of a non-trivial connection. Then I am curious, in such a space-time, do we know how to quantize fields? For example, in the normal de Sitter metric theories, we know there is a Bunch-Davis vacuum. Suppose if you have a de Sitter metric but a non-trivial connection, what kind of vacuum it will be? So,
well, that's a good question. I think you can. You just have a different background now. That's what you mean, and interact. Yeah. Well, I should say that in my talk I just talked about pure gravity. I didn't mention at all how this would interact with matter. So you have all sorts of choices. Like you could decide that some matter is coupled to the independent connection, some matter is coupled directly to the Levi-Civita of the metric. A priori, it's not. You have a lot of freedom.
This question is actually motivated from trying to look for some application of metric affine theories in the context of early universe cosmology. So I'm just trying to see.
You can put a lot of. You see, you have in principle, metric affine gravity contains all these states with spin 0, 1, and so on. And I think that many models of gravity, like scalar tensor gravity, scalar vector tensor gravity, and so on, they could just be reinterpreted as special cases of metric affine gravity. You see what I mean?
Yeah.
Like the vector would be some component of this distortion, for example. You can do such things, and then you can apply to early universe or dark energy problem, whatever. Yeah.
Well, you're saying like any metric affine gravity can be treated as in the metric theory with gravity and the matter.
Yeah.
For me, it's a bit difficult to imagine. For example, in your talk you presented higher curvature metric affine theories. I mean, you have like T, and
yeah, but you can translate all that
by some kind of what kind of transformation? Well, in the metric theory, there is conformal
it's the field redefinition that I gave.
Okay.
The field redefinition where you write the connection A as a Levi-Civita plus distortion. It's all there. With that, you can. Yeah.
Then my naive question is, well, metric at least maybe because I never worked on metric affine theories, but I find it difficult. If it is true that you can always write metric FN theory as metric plus matter, in the metric metric FN theories in the form of metric theories as gravity plus matter, then it's simpler to work, right? I mean, in the metric framework rather than metric.
Yes, it is. I confirm that it is. It is typically simpler to do calculations in that way, because you have because then you have the covariant derivative nabla, the Levi-Civita covariant derivative that has nice properties. Whereas if you work with the independent connection, you have a different covariant derivative, and it becomes complicated to do integrations by parts and things like that.
But then, does metric FN theories give some additional insight of how matter should? Does metric FN theories give any additional insight of how matter should couple to gravity?
No, as I said, you have the freedom of how to couple matter to gravity. You have even more freedom in this case than in ordinary.
Okay.
Yeah. I would say I have a sort of common question to Luca. I talked I talked about this gravitational Higgs phenomenon where there is the GL4 symmetry is broken, and we know how to describe the broken phase. It's a phase where you have a non-degenerate metric, and it's very difficult to discuss the unbroken phase. And it seems to me that what you do is a sort of pre-geometric way where one can actually discuss the broken phase, the phase without metric.
Exactly.
But then I don't understand what role a black hole should play there. It seems to me that the question is independent of, it has nothing to do with black holes. It's a
No,
question.
it was basically, black holes are, the motivation, the previous works were mostly about black hole evaporation, but you're right, this one is inspired by that works. And we expect that some, that formation in black hole evaporation, you have when black hole evaporates, you have a formation of space and matter out of the black hole. That's the picture we had in mind, but clearly this is far more general and in principle has nothing to do with black holes. So no, yeah, you're right. It's pre-geometric. We try to figure out how from the pre-geometric phase you can go to the geometric phase, the emergent geometric phase.
Thanks.
No, thank you.
Okay. If there are any questions from anyone? If not, I think it's a good time to conclude the morning session of today. And let's thank all the speakers. And thanks for the very nice talks and discussions. So we will meet in 1 hour 15 minutes for the second session of the day.
Okay.
Bye. Bye.
Yeah, thanks everyone. It would be great if speakers will send me presentations and I will upload them on the website.
Sure.
Okay.
Yeah, thank you.
Mute and start video.
Ah, hello.
Hi.
Good afternoon. Yes. Good afternoon. Nice to see you. Welcome.
Hi, I'm Helen.
Yes, nice to meet you.
And Roger is
Hello,
here.
I'm right here.
Roger's
Hello.
right here. So
Yes.
shall we share the screen and see if it works for you to see Roger's presentation?
And just a sec. Yes, now you can share. Yes, now you can try to share. Yeah.
Okay. I don't see share screen. Yes, I do. I do see share screen. There we are. Share screen.
Yes.
There we are. Now let me just find. And here is Roger's PowerPoint. So can you see that now?
Yes, sure.
Show that picture. Can we? Yes.
It always does this
It
for a minute.
would be-
It'll come.
Yes.
There we are. Okay.
Yes, now it's a full screen. Yes, absolutely perfect. Yes, great.
Good. Excellent. All right then. So there's no technical issues.
Yes, you can keep it as it is.
Right. Okay. Good. Everything's
Good.
fine. Roger. There
Thank
we
you
are.
very much.
No problem.
How do you know which? This is the thing that always used to floor me. They have a, when you do the, right at the beginning, there's a thing which shows lots of slides that you just choose. You've got to choose the right one.
Well,
And
you
and you do it automatically, which when I do it, I often pick the wrong one. Now, what do you do to do that?
you click on the slides that they don't show up on this screen for you, but
Yes.
they show up here. So you would just literally go along there and click there
Never mind. No,
with your mouse. But ideally, if you go like that, this time it's this way round, Roger. It's
oh, side to side.
yes, side to side
How
this
do I know
time,
which it is?
because you're going, it's that way is forward
No, that's not what I mean.
and then back is that way.
But sometimes it's up or down. Never mind.
I know, it's just the way the presentation.
That's the way of the world. I have to
That's
get
the way
used
of the
to it.
world, yeah. The last one was, you're right, it was up and down.
Well, it's not for me to ask questions about that sort of thing.
No. Ours not to reason why.
Yeah, that's it. Exactly. Yes. Oh dear.
Excellent.
I just check it's the right one.
I'm here anyway, Roger, if you get into trouble.
Yes, okay. You've got a problem like that.
Have you got some, you've got some juice, do you want some more?
Oh, this will be all right.
You sure?
Yeah.
What about a sweet? Have you got any of those?
I have some of this in there.
Let me see if I can find them.
Yeah.
Here they are.
Yeah.
There we are.
Yeah.
I'll put them in your bowl.
Okay, thank you. Yeah.
You can see these pictures today when you come to the Maths Institute. The pictures that arrived.
Pictures, my picture?
Yeah, the ones from the summer exhibition
The
at the
one where
Royal.
they got the wrong god.
Yes, but they're in my office, so you can see them.
Have a look.
And Dara was talking about adding them to the Roger Penrose exhibit.
If you think they haven't got the right god.
Yes, well, you can say if you don't want that one.
must have several of them. Yes, that's right.
I do prefer the one that you
Yeah, no,
have to say. This one. It's clearer somehow as well in what it's saying, but it's
Yeah.
also just a nicer picture.
Yeah, yeah.
Yeah. Oh, there was something hilarious. I always look at the BBC website and I look at, they have the thing of what the papers say, and they've got the picture of the front page of all the newspapers with just a paragraph on what the newspapers are leading on. And today, the Daily Star of Letters fame, it was reporting on how a flat earther spent £20,000 to do this experiment to prove that the earth was flat. And very sadly, he proved that the earth was round. And he's had to come clean and admit this, that his £20,000 was, and he's admitting that sadly, the earth is actually rounder than we thought. It's just hilarious.
So you tried to prove the Earth was flat.
Yeah, and he spent £20,000 on some kind of geoscope, and he was absolutely convinced that he would be able to prove. And there was a whole group following him. I always thought this was
So they're
myth.
still flat Earth. This is a sort of standard joke about flat Earthers.
They could be flown around the orbit of the Earth and come back and say it's flat.
So what time are they starting? It's 1 o'clock. Isn't it?
I think so.
Yeah, I've got still got a quarter of an hour. Is that right?
Yeah, in 15 minutes.
Oh,
15
okay.
minutes, okay. Sorry?
I was going to mute us for a bit, but it doesn't.
Oh, I see. Oops. Well, if we're talking politics or something. I don't think anybody can complain about objecting to, well, making fun of flat earth.
No. Oh dear. It did amuse me.
I didn't realize they still were people.
I know, I didn't. I honestly thought it was a myth, that it was something that people invented as an example of
Yes.
utter idiocy, that there couldn't possibly be anyone. But no, there are societies.
Really?
Yeah. And a couple of years ago, a man created a rocket in his garden, and he was going to go into space to prove that, and he got badly injured when he literally launched this rocket. He didn't get very far, and he did live, I think. He wasn't killed, but he was quite badly injured.
There was a time when, of course, they would have laughed at the spherical Earth people.
Well, yes, there's a
But that was
wonderful,
a while back.
yeah. There's a really nice bit in Derek Jarman's film Wittgenstein. And in it, Wittgenstein is teaching at Cambridge, a group of undergraduates.
Mm.
And he says to them, why did people believe that the sun went round the earth? And they were all trying to work out what he was getting at. In the end, his answer was quite simply because that is what it looks like.
Yeah.
And
Yeah, you just see it very well. Don't you?
yeah, that is what it looks like.
Yes.
And it is not what it seems, because you have to have a different perspective than what we see.
Yeah.
And it's just a brilliant moment.
But there is a subtle thing about it, which is, and it's the Galileo thing. The thing is, why don't you, if we are going around the sun, you would think you would feel it somehow,
Yeah.
grabbing onto this thing and
Absolutely.
speed.
Yeah.
I think,
Why don't we fall off?
why don't you actually feel the velocity?
Yeah.
And the thing is that, that's principle of equivalence. Principle of
It's so
equivalence is-
big, isn't it?
Yes.
It's so big we wouldn't feel it.
Well, you don't feel the velocity. I mean, we used to think if you could go, you can be sitting in a tube train, going through a tunnel, and you just, well, it may jiggle a bit, but you don't feel the velocity.
No.
Because if there was a different theory of dynamics, you might feel the velocity. So it's
Well,
like
those fairground rides that go so fast that they literally push you, the centrifugal ones that actually push you against the wall.
that's because you're going not in a straight line. Yeah, you're going curve. There's an acceleration, and then you do feel it. Whereas the velocity, you don't feel it. It's quite a subtle thing if you don't know anything.
Exactly.
Yeah.
Exactly. And I think, prehistoric man was quite sensible to worship the sun. That makes sense as a religion.
Yes. Oh, yes.
And so would rain worship as well.
Rain worship.
Rain worship.
Gosh, I never heard of that.
Well,
Alexey Alexandrovich, nice to see you around.
Is something happening here?
Somebody else arrived. I think we better be quiet.
Hi, Alexei.
My plot here. Took a little while.
Good afternoon.
I am. Good afternoon.
It is still 10 minutes.
Yes, sure.
Before your talk.
Yeah.
Can you hear me?
Yes, we hear you. Yes.
For example, Ravan.
Hi, Alexei. I can hear you.
Oh,
hello.
I
Great to see you.
Okay.
Hello, nice to see you here.
No. Oh, I see. This is the title for the University of Surrey talk.
Oh dear, we should have. Never mind, too late now. We should have changed the title.
Yes, yes. It's got the wrong date too. Got February the 20th.
It doesn't matter. Right.
Did I get
It's
exactly?
only up there for.
Sorry?
It's only up there.
But I don't need to show the title.
No. You can go to
It's
the
left and right, isn't it?
Yeah.
Yes.
Can you hear me now?
Yes.
Yes, we hear you. We hear you very well.
It was exactly the same title, was it?
Yeah.
The story talk.
Alexi, yesterday we were speaking with Irina, so it was your birthday yesterday. Happy birthday.
No, I couldn't just remove the thing at the top.
We'd have to.
We can hear you, Alexi.
No.
Can you hear us?
Just put it on the second slide, Roger.
I can flash it on quickly so people don't have time to read it.
Just put it onto the second slide.
That one.
Okay, so you can hear me, but
Can you hear us?
no, I don't hear you.
Okay, maybe did you mute your speaker in your laptop? Maybe try to increase the sound.
Okay, let me try once more. Can you hear me now?
Yes.
Yes.
Yes,
And
we
you?
can hear you. What about you? Can you hear us? Hello.
But I don't hear you.
Oh, which is strange.
Is it possible that your sound is muted on your computer somehow?
Hello, you're not talking to me. Can you hear me?
Oh, we are, yeah, we can hear you. We are talking to Alexei Stravinsky.
Okay.
Okay.
Now it's okay. It's
Okay.
no.
Now it's
Okay.
okay, great.
Good afternoon. Oh, Roger.
Hello.
Good afternoon.
Yes,
Nice to meet you.
good to see you.
Okay. We still have 3 minutes.
Okay.
Okay, let's begin our session 2. And I have the great pleasure to announce the first talk by Professor Roger Penrose, the second law of thermodynamics, from black hole singularities to conformal cyclic cosmology. Please, Roger. Oh, Roger.
Okay, you ready?
Yes.
Right. I can't move it. Why can't I move it?
It's okay, because what do you want to do? Go back to the.
Well, I want to move it at all. It won't move.
It will.
Oh, that's all right. I can show that. Will that move now?
Yeah.
Okay. Yes. Well, that's the title of my talk. It's actually not quite this presentation, but never mind. This is a picture taken from the paper, which eventually apparently won a Nobel Prize. It was published in 1965. This is a space-time picture of a collapse, which you can think of as the Oppenheimer-Snyder collapse. This was in 1939 when Oppenheimer and Snyder wrote a paper considering the spherical collapse of a dust cloud. And this is basically the sort of picture they had, where this dust cloud, it's called dust, that means it has no pressure, and it's exactly spherically symmetrical. So everything is focused towards the center, and it's not surprising that in that case you get a singularity, where the density becomes infinite. But people thought, well, that's very special. And if you have a genuine collapse, this was when the quasars were discovered in the early 1960s. And these were these very strong radio signals which seemed to be coming, and they were redshifted, and they were clearly enormous events which indicated there was something of the nature of a collapse of material to the Schwarzschild radius of that body. But however, since you're seeing signals and you're seeing things coming out of it, this means it can't be the picture that we have here, which we refer to as a black hole now, because you have irregularities. And I suppose the view was that if you have irregularities and things are not focused towards the center, then they will swish around in complicated ways and come swirling out again. So the argument here was to try to show that even if you have irregularities, you still don't get out of the problem. So the point here is, first of all, we think about this spherically symmetrical case, which I'm indicating here. And I should say a little bit about the little cones that you can see in the picture. Those are light cones or null cones, if you consider them locally. And usually I draw them with both a future and a past part. In that picture, it just has the future parts indicated. And this indicates how light would travel. So if you're having a world line within that cone, that's what an ordinary particle could do. If it was going with the speed of light, it would have to have its world line along the cones. And if it was going faster than light, it would be going sort of horizontally or something like that. Okay, now in general, the cones will be rather complicated arrangements. They won't just be uniformly distributed. So we have a picture here of the sort of thing. Now, I want to consider in this picture again, the future of this little ring in the middle. You can see that. That's what's called a trapped surface. You have to bear in mind, of course, that the picture is only looks as though you're thinking of a three-dimensional situation. In other words, two space dimensions and one time dimension, whereas really we should have three space dimensions and one time dimension. So we were short of a dimension in the picture. The little ring in the middle is actually a sphere, topologically a sphere. It's a two-dimensional thing. And the future of that sphere is indicated by the shaded region. I'm going to be concerned with the future. That sphere is what I call a trapped surface. That means that the light rays coming from it are converging inwards. You see, in an ordinary, if you have an ordinary surface and you have a flash of light on that surface, then you can have the light going in one direction or the other. If that surface is curved, then you would expect the concave part, the light will be going inwards, decreasing in spatial dimension. On the convex side, it will diverge. But if you have a particular situation here, it's not so, there's nothing peculiar about it with regard to the local situation, because the intersection of two past light cones will have the property that this surface is something where the light rays in both directions will be converging. What's peculiar about the black hole is that you have a compact surface, which is this trapped surface, the little ring in the middle, which is closed up, and then it's closed up and you have this focusing on both sides with the light rays converging on both sides. And that's the peculiar feature that you have in this exact model here. And if you perturb that, suppose you imagine it wiggling it a little bit, then you will not destroy that particular feature. So the thing is to show that this particular feature leads you into trouble. And the future of that region is the shaded region here. And I'm looking at the boundary of the future of the region. And the boundaries of futures have interesting properties. In general, they'll cross over. So this is in the general case, you will have things like this, where you have crossing regions and caustics and very complicated looking. But if you're looking at the boundary of the future, all that complicated stuff is not on the boundary. What's on the boundary, it's not smooth because the light rays cross each other, but it's a topological surface. And the thing, you don't have to worry about all the caustics and the crossings over. You have a surface, and that surface is compact, and then you can show, I won't go into the details of that because it's not the point of this talk, but you can show, I should indicate here, we do need this feature. This is a feature of light rays, and it's the two types of curvature that we have in space-time. One of these types of curvature is the Ricci part, which has to do with the light rays being focused inwards. If you imagine you could have the sun in the middle, and if the sun was transparent, and I don't mean material transparent, just imagine you could see through the light rays going through the sun. Since the sun is matter, that means that you have the Ricci curvature there. And the Ricci, I think I'll go to the next picture to show. You see, if you're looking back, and if you look through curvature, which is Ricci curvature, then that will be focusing like a positive lens. It's like a magnifying lens, and the light rays will be bent inwards. The Weil curvature is the other part of the curvature, and the Weil curvature is distortion. That's like an astigmatic lens. So there's as much inward focusing as outward focusing. So you split it into those two. There's also the scalar curvature, which doesn't affect the light rays. So we don't need to worry about that, at least for the moment. We'll go back to the previous picture. So if you're looking through the sun acts as a positive lens because it's matter. And so that would be magnify if you could see through it, it would magnify the star field behind it. So it would push it outwards. So this means that the whole star field is pushed outwards. And if you look at on the top right-hand part of the picture, you see what a circular pattern of stars would be distorted because the radial direction, the distortion gets less and less the further you go out. Well, the radial distortion is a squashing inwards, and the transverse is a stretching outwards, because as it moves outwards, it has to stretch further. So you see that the circular pattern will get distorted into an elliptical pattern. So you're seeing the effect of Weyl curvature outside the sun. And if you could see through the sun, you would see the effect of Ricci curvature. So these are the two types of curvature which I'm indicated here. Now, the point about Weyl curvature is, although it doesn't focus inwards, it's still, if you have complicated Weyl curvature in and out, and also if it's not just, yeah, I mean, if you have a lot of it going on, then there is a residual, which is an inward focusing, so that you always get a net, as far as the focusing altogether, it's always inwards, either directly because of Ricci curvature or indirectly because an effect you'd call the Riccaduri effect, that you again get inward focusing when there's a lot of Weyl curvature around. You see the energy density into the gravitational field is non-local. The energy density in matter is local, and the local energy density causes an inward focusing. As far as the non-local focusing of the vacuum, this is something you can only see. You don't see it immediately because the Weyl curvature doesn't cause inward focusing. Anyway, that's the key point that you have to consider about. And one was able to show, let me just go back a bit. One was able to show that if you had just inward focusing, and so that would mean that as you follow your light rays, either they will they'll start crossing each other, or they will go inwards. And what happens is that you have a compact region, and that compact region leads you into a contradiction with the. Go back to the picture we just had here. I've lost it. That picture. Yes. So it shows that you have the boundary of the shaded region is still compact, even if it's not spherically symmetrical, but complicated. And this leads you to a contradiction with the initial non-compact initial surface. You can follow backwards along along time-like curves, and you can see that you have a contradiction. I won't go into the details of that, but that's the point of the argument. Okay, now I had given a talk at King's College, London in 1964, I think it was. And when Dennis Sharma heard about this talk, and he decided he'd like me to give a repeat of the talk in Cambridge. And Stephen Hawking was present at my repeat talk, not at the original one, despite what the movie says. He was present at the talk I gave in Cambridge. And we had a private session with Stephen and excuse me, and another chap who was also there. Anyway, and I talked about the details of the argument, and Stephen very quickly picked up on this and showed how you can apply these types. He generalized the arguments in various ways to show that you could apply them also in a cosmological situation when you might have a compact universe, so you couldn't quite use my argument, but you could, with generalizing it, you could do that. And then we got together and produced a theorem in the Royal Society, which more or less encompassed all the other arguments. Anyway, the key point is that if you have you can't imagine that there was a sort of bounce that people considered that you could have. I should have explained that at the time when I was doing my theorem, a little bit earlier than that, there was a paper due to two Russians, Lifshitz and Khalatnikov, and they seem to have got a proof that you in the general case, you would not get singularities. There was an error in their argument, which I had a look at the paper. I just didn't think the arguments were sufficiently convincing, and so I just thought about them on my own terms. But there was actually an error in the paper, which was discovered, I think, by Belinsky. And anyway, he collaborated with the Russians in an improved paper, and they considered the sorts of complicated singularities that you would get. I want to come back to that sort of thing in a moment, but let's consider the situation of a universe. And instead of having a trapped surface or something, you've got an expanding universe. And the question is, could that rise from a bounce? Could you have a previous collapsing universe which went through some complicated non-singular configuration and then came swirling out again? So I think this was the kind of picture that people had, and maybe from the paper by Lifshitz and Kalatnikov seemed to indicate that you would get some kind of a swirling around and coming out again. But the argument here is that that's not what happens. And Stephen's arguments, and then the arguments that we both had in the final paper in the Royal Society, he had 3 papers prior to that. And you could show that these singularities were a generic feature. Now, I want to consider another question about all this, which is really what I'm talking about in this talk, not the details of the theorems, but what happens in the future? You see, suppose you have a collapsing universe. This is just the same slide I had before, but turned upside down. And in a collapsing universe, again, you would expect you to get a singularity in a generic case. But it's really very different, because in general, you will have black holes forming, and these black holes will form local singularities, and these singularities will congeal with each other as the black holes collide with each other, and in the collapse will be a very complicated situation. It will look like a great mess like this, and it will not be the nice, smooth situation that we seem to see in the Big Bang. And the question is, why don't we get, in the past, this much more probable situation? When I say more probable, you can think about it in terms of entropy. You see, according to the Bekenstein-Hawking formula for the entropy in a black hole, the entropy is proportional to the surface area of the black hole. Now, when you have very big black holes, galactic clusters, and in fact, the black holes we already see in the universe now, the total entropy is enormously in those black holes, and not anything we do locally is chicken feed compared with black holes. And the black holes are really where the entropy is. And as they collide, the entropy goes up enormously, and it gets larger and larger. And this is the sort of picture that, as I was trying to indicate in the previous slide here, you get a great mess. And that is representing, as time progresses, you're having the second law of thermodynamics, as you might expect it to operate, with the entropy increasing enormously as time goes on. But in the Big Bang, you have a very special, you don't have this situation. You have something very special. Well, otherwise we wouldn't have a second law of thermodynamics. But what does the Big Bang look like? Now, I've got here, in order to talk about what people normally regard as maybe the explanation for why the Big Bang was very uniform, is this feature called inflation. And you need a very powerful magnifying glass to see inflation. And if you could see it, you would see, according to the theory, an exponential expansion again, but on a much, much tinier scale. So this is the picture that inflation is supposed to produce. But it doesn't really answer the question, because the inflaton field that you put in here is time symmetric, like all the other physics, basically is time symmetric in this consideration. And so why do we not have that complicated mess, which I just indicated before? That complicated mess is not eliminated by inflation. Inflation doesn't even get a look in. There's not, the situation you need for inflation just doesn't occur here. It's just too complicated, and it's not even anything like it. So inflation is not the answer. Let me turn to something else now. When we look back into the universe, what is the earliest thing we see? The earliest thing we see is the microwave background. And the microwave background, this I think is the Kobe satellite, which was the first satellite looking at the microwave background. And this feature was noticed of the microwave background, a very nice curve, which you see here. This is the intensity is upwards and the frequency is left to right. So increasing frequency as you go from left to right. Now, what you're seeing here, and the error bars, I should point out, are magnified by a factor of 500. So if you actually drew the actual error bars in this picture, they would be smaller than, even the worst ones on the far right would be smaller than much smaller than the thickness of the incline. So you have a very, very perfect Planck spectrum. What is the curve then it's trying to follow? It's the Planck curve. This is the Planck curve, which is what Max Planck found as a description of thermal equilibrium. This is supposed to be a maximum entropy state. A maximum entropy state? I've always found this very puzzling, because what you look back at the earliest thing you see in the universe, you seem to see maximum entropy. But you ought to be seeing a small entropy in the very early universe. You shouldn't be seeing maximum entropy. Of course, you're seeing it looking at an expanding universe, so maybe that is the answer to that question, but it's not the answer, because we know that black holes come in and you get this great mess, which I was just showing you previously. The sort of mess that you see in the picture here, and that would be the situation. I mean, the entropy goes up when black holes form, and you would have a great mess like this. Why do we get this very uniform situation? Well, the answer really lies in the following three pictures. The top three pictures represent a gas in a box, or something in a box. And I'm imagining that, first of all, you have a little box, and all the gas is tucked up in that little box. Then you open up the box, and the gas spreads out through the whole box. And that is, from left to right, we now have entropy increasing, and we also have time increasing. So as time increases, the entropy increases, as with the second law of thermodynamics. That's exactly what you'd expect. But now in the bottom three pictures, I'm considering a galactic scale box, and these little points are not molecules or something, they are meant to be stars. So we have stars, and what you tend to see is that they will start to clump, so that the gravitational the effect of gravitation is universally attractive, and this means that the uniform situation is not a maximum entropy state. The entropy increases left to right, just as in the top three pictures, but instead of looking like the top, it looks the opposite. The uniform state is low entropy, and you see this particularly with the black holes, because the black holes form a really extreme form of clumping, and the entropy goes shooting up enormously. So we see these two features now. Ordinary matter, from left to right, gets more and more uniform, whereas in gravitational situation, it gets less and less uniform. So what we're seeing in the Planck curve, we're seeing, this is matter and radiation. We are seeing matter and radiation in a high form of entropy, very, very, more or less maximum entropy. But as far as gravity is concerned, you'll see a very non-uniform distribution, and it's low in the gravity. So that's really what is special about the early state in the universe, is that the gravitational degrees of freedom seem not to have been activated. Now, here we have a picture in detail how this works. This was actually due to Schrödinger in his book, What is Life? And he explained this, and a lot of people didn't appreciate what he was saying. What he was saying, basically, well, you see here in the top picture, we have the sun, and people say, well, what do we get from the sun? And they say, well, we get energy from the sun. But that's completely wrong, because in the daytime, sure, we get energy from the sun, but in the nighttime, that energy just all goes swirling back out again into the dark sky. Of course, there's a little bit doesn't get out because of global warming, but that is, although a very important effect, it's very, very tiny compared with what happens from night to day. So that's not what we're talking about here. What we're talking about is in the daytime, the sun is a hot spot in a dark sky. So the sky is dark and the sun is dark and cold, and the sun is bright and hot. And it's the non-uniformity of the temperature distribution in the sky which is important. And what is it that we get from the sun? We get energy which is much more energetic. The individual photons are higher frequency than the photons, the infrared ones, which go back into the night sky, whereas these are yellow light photons, basically from the sun, much more energetic individual photons. And by the Planck formula, the energy will be concentrated. The photons, which come from the sun, will individually be much more energetic. And therefore, we have far fewer photons carrying the same amount of energy coming from the sun, and many, many more photons carrying the same amount of energy back into the dark sky. In other words, the energy is distributed amongst much a smaller number of degrees of freedom in the energy coming in, and many, many more degrees of freedom in the energy going out. And so this is telling you what we're gaining from the sun is low entropy. That's the whole point. We don't use the energy because energy in itself, if it was just a random form, wouldn't be any use to us at all. If the whole sky was the temperature of the sun, it would be completely useless. What's useful is the contrast between the bright sun and the dark sky. And the clever plants make use of this by photosynthesis. And the photosynthesis, they use it to build up their structure, and then animals and use that to eat, and they build up their structure, and we eat animals and plants and build up our structure, and that's how we manage to exist. And that's what we get from the sun, this energy in a low entropy form. And that's the key point. Okay, now, what's the difference then about the singularity in the Big Bang and the singularities that we seem to get in black holes? The difference is basically the Weyl curvature in the Big Bang goes to 0, or it's very small, whereas the Weyl curvature in the remote future goes to infinity. So it's the Weyl curvature which somehow extraordinarily constrained in the Big Bang. It's not just any old singularity, it's a singularity in which the Weyl curvature is, well, like I say, it goes to 0. It might just go to some very small factor. It's constrained in this way. Now, I used to think, I just sort of going through my historical views on this, I was certainly very puzzled by this. It seemed to me the Big Bang was very peculiar in this respect. And like everybody else in those days, I thought that in order to understand the Big Bang, since it's a singularity, we have to talk about quantum gravity. The radii of curvature in the early universe would be very, very tiny. And so we're looking maybe at what the physics is going on at the Planck scale, at the scale at which your radii of curvature is what, 10 to the minus 43, well, 10 to the minus 33 centimeters, or something like that, which is a lot smaller than the particle physics, or 10 to the minus 43 in terms of time, something like that, 10 to the minus 43 seconds. Very, very tiny, and you say, okay, that's quantum gravity. But if it's quantum gravity, why is it so asymmetrical in time? Because it doesn't seem to apply in the singularities in the future. They're just going to be generic, very complicated, high entropy. I should say that Belinsky, when he joined Kalatnikov and Lifshitz, they had quite a different picture of what happened in the generic case. And they had Weyl curvature diverging in very complicated ways. And Charlie Misner independently looked at the kind of situation that you get in these generic situations. And you can see that the Weyl curvature doesn't just go to infinity, it oscillates in a very wildly divergent way. And that seems to be the situation which but I don't think there's any general theorem that tells you that's what happens, but it seems to be the situation in a generic collapse. As the Weyl curvature goes wild in this very complicated way. It certainly goes to infinity. Now, if it's quantum gravity, why don't you get this situation, which is much more likely? You see, the black holes are where the entropy is. That's the likely stuff. And the Big Bang seems to be extraordinarily improbable. If it's just a random occurrence, and inflation doesn't help you because it doesn't get you out of these complicated singularities. You have to have something more or less almost Weyl curvature free anyway in order to talk about inflation. It doesn't give you anything in this particular scheme. I mean, it may give you other things, but it doesn't explain why the Weyl curvature is 0. So I used to think, well, quantum gravity must be a very peculiar theory. In fact, I think it must be a very peculiar theory for quite a different reason. I think that the gravity has an effect which explains things about quantum mechanics that we don't understand. And what I mean particularly is the collapse of the wave function. Quantum theory doesn't explain why the wave function collapses, why the Schrödinger equation does not describe the evolution of the universe. You have something else coming in. And the view I have is that that is quantum gravity or something, whatever, gravitational quantum mechanics or something. But it doesn't really help us with regard to this Weyl curvature problem. So I just postulated, I just said, well, this is the Weyl curvature hypothesis, that the Weyl curvature goes to 0 in the Big Bang, and for what reason we don't know. But then my graduate student, I'm not sure whether he was still a graduate student at the time, I can't remember, but Paul Todd had a different way of talking about the early universe, which was much better than my way. I had thought about it a little bit before, but I hadn't really thought about it seriously. He actually did equations, he worked it out and postulated this way. What is his way of looking at it? I'll come back to this in a minute. His way of looking at it was that, described in this picture here, which is that if you stretch the Big Bang out conformally, then you get a smooth initial state. This doesn't make the Weyl curvature 0, but it makes it finite, which is a very strong condition. Let me go back. Now I wanted to talk about this picture. You see, I did talk about the light cones, but when you have just massless things, well, I should say the light cones are 9 out of 10 components of the metric. It's not really like that. They're the 9 independent ratios of the 10 independent components of the metric. So you have 9 independent ratios. So there are 9 numbers to define the light cone and 10 numbers to define the metric. So what is the extra number, which gives you the metric itself rather than just the light cones? Well, this is described in this picture here. I'm considering, well, at the bottom you see the 2 most famous formulae of 20th century physics. There's Einstein's E equals mc squared, which tells you that energy and mass are equivalent. And the bottom formula is Max Planck's E equals h nu or hf, where this told you that energy and frequency are equivalent. Of course, C and H are constants, and I'm not worrying about the constants. You can scale your dimensions to get rid of the constants if you like. But energy is equivalent to mass, and energy is equivalent to frequency. Put them together, that tells you that mass is equivalent to frequency. That is to say, if you have a massive particle, then it is a clock. It's a very perfect clock. Of course, you have atomic and nuclear clocks now, which are exploiting this feature. You don't actually, the frequency is much too high for an ordinary particle. You'd have to scale it down in some way, which is, of course, what we do for atomic and nuclear clocks. But if you have 2 particles now, I'm imagining 2 identical particles, one of them marked red and the other marked blue, and as they travel along, slower than the speed of light, so they hit these bowl-shaped and hill-shaped surfaces, those tell you what the ticks of the clock would be. So the blue one hits the surfaces and gives you the ticks of that clock, and the red one hits the other surfaces and get the ticks of that clock. And they're equivalent. You can transform one into the other, but this gives you the time dilation and the way that relativity works. Okay, so you need, in addition, this kind of scaling, which gives you these bowl shapes and time if you've got massive particles. But if you don't have massive particles, then let me try and move this thing. Yes. I don't seem to have a picture I want. It's gone disappeared on me. No, let me go ahead. Yes, there it is. Sorry. This is the picture, one of the famous Escher pictures, is circle limits. This is actually a picture of hyperbolic geometry. Don't worry about that. The main point is it's a conformal picture. And it's conformal. That means that the small shapes are preserved. And in particular, you see the eyes of these fish creatures are circles. They're exact circles. And no matter how close to the boundary you get, they remain exact circles. So the squashing in one direction is the same as the squashing in the other direction. And you can incorporate infinity in this picture in the boundary of this disk diagram. And I want to use this feature of representing the boundary in a nice conformal way. We can do that in space-time as well, so that the infinity of hyperbolic geometry is represented as just a nice boundary. And you could imagine if you were a conformal person, you didn't respect the constraints of the metric geometry, then you could step outside the circle and you would get to the region outside the boundary. Of course, the fish are metric creatures, and so they crowd into the boundary and they can't get outside. But what in ordinary physics, we do have conformal things. We have, well, I'm sorry, I thought I had a picture of the light ray, but I didn't seem to have it here. Anyway, going back to what we have here, the light ray will go along the cone, and it doesn't intersect any of these surfaces. So if you have a massless particle, then they're not interested in the boundaries, they're just interested in the light cone, of course. So suppose you imagine that you have, in the two ends of the universe, that's really what I'm thinking about here. In the future end of the universe, well, the universe will be dominated by photons, and photons don't have any mass, and so they don't care about the boundary. And I was sort of sitting and wondering about what the photons do, and the photons, well, they don't care about the boundary. They go shooting off, and they say, well, where are we? We've got out of the universe somehow. So maybe there is some external region that they reach, the photons. What about the Big Bang? Well, the Big Bang is surprisingly similar, but for a different reason. Because it gets so hot near the Big Bang, so hot and dense, that everything is moving around almost with the speed of light, and so that the energy in particles is dominated by their kinetic motion, and the mass part of their energy is trivial. And the further and further you get into the Big Bang, the more like massless particles they behave. So in the limit, the asymptotic limit, as you go back, you consider that they're effectively massless. In the future, there's a bit more to it because there are particles which don't disappear. I mean, electrons and positrons, at least. Protons might decay, we don't know. But electrons and positrons will still be around, and they can't find each other out to annihilate each other. A few of them might do that, but most of them won't. And so you do have some other particles. So I do have a slightly less convincing, perhaps, argument, which is to do with the fact that you really, what you do is you look at the Casimir operators of the Poincare group, which is what physicists usually do when they're talking about particle physics. But if you're thinking about the conformal group, then the Casimir operators, well, the Casimir operators are not conformally invariant, and so that there might be. They're not, so that if you're looking at conformal geometry, you might think that maybe mass is not that mass may not be an absolute constant. That's the point. I'm talking about really when they have a cosmological constant. If you have a cosmological constant, then the Casimir operators are not mass and spin. You don't have mass as a Casimir operator. So you don't have this strong reason to believe that mass is utterly conserved. So I'm trying to argue that mass is not conserved when you have a cosmological constant, or what people call dark energy. Rather bad name, in my opinion, because it's neither energy nor dark. It repels rather than attracts. Ordinary energy attracts, whereas the cosmological constant, which is what I would like to call it, is what people seem to call dark energy these days. I remember going to these conferences often in Texas. They were the Texas conferences. They started to be Texas, but then they went around the world and so on. And I would attend at the end of the meeting, And there'd be some comment about maybe by the time of our next conference, which would have been in 2 years, we will worked out what the value of the cosmological constant is. Well, finally, they did find what the cosmological constant was. It's positive. But rather than saying, oh, this is the value of the cosmological constant, there's, oh, this is this mysterious dark energy that nobody knows what it is. Well, it always seemed to me that it was the Einstein cosmological constant, which is perfectly possibly there in the equations. It's something you wouldn't notice until you have look very far away, very distant future, and so on. But maybe it's there. And so that I was biased against it for quite a long time, but then I got convinced, I think, by Jerry Ostriker that it really, to explain things in the remote future, we really do need this cosmological constant. Okay, so with the cosmological constant, you have infinity is space-like, and the Big Bang tends to be space-like as well. Now, they're very different, you might say, because the remote future is very cold and very rarefied, whereas the Big Bang is very hot and very dense. But when you stretch out something, you see the temperature, the density is it's to do with momentum and energy are conjugate variables to space and time. And so if space and time get squashed, then momentum and energy get increased. So that as you squash infinity down, you would increase this very cold and rarefied remote future would become much hotter and much more dense. And when you stretch out the very hot Big Bang, you get something which is much colder and much more rarefied. So they really are rather similar to each other. As long as you're thinking about conformal geometry, which is the geometry of massless things, and if you're allowed to do that, and the argument would be that you are allowed to do it in these two ends of the universe, then they're very similar. There's nothing really outrageous about this picture. It's perhaps not the one that people used to think about much, but there's nothing outrageous about it. But what is outrageous is that. And I'm saying that the Big Bang was the conformal continuation of a remote future. And this gives you a Big Bang which has to be free of Weyl curvature, because the Weyl curvature is conformally invariant and it goes to 0 in the remote future. There's a little thing about the Weyl curvature, which I don't think I really want to go into here, but it has really two manifestations. It has the manifestation of being the conformal curvature. It also has a manifestation as being the wave function of a spin-2 field. And they look very similar. It's very, when you write things in terms of two-component spinors, you can see this feature brought out, which is not so obvious when you write in tensors. It really does look like a massless spin-2 field in the spinor form, and it has a certain conformal invariance. The massless fields have a conformal invariance for all the different spins, and the conformal invariance that you get for the Weyl curvature when you think of it as the massless spin-2 field is a different factor from when you look at it as the conformal curvature. And it's the factor when you think of it as a massless field which makes it work best in this picture, because it has a finite value in the remote future and a finite value in the past. And these values can match up with each other. It does mean that the Weyl curvature has to be 0 at the Big Bang because of the way the scaling works. And it's, no, I'm so sorry. Have I got it the right way around? Yes, it has to be 0 when you, no, the Weyl curvature is, I have to get it the right way around, I'm sorry. The Weyl curvature goes to 0 in the remote future, whereas the Weyl curvature, when you think of it as the spin-2 field, is finite. And that carries through into the next eon. So you've got something which carries through, even you might think what could carry through. But there is a point here that massless fields do carry through. Photons could carry through, but that's not very helpful usually, because when you get onto the photons in the remote future, as they get onto the other side, they enter a very, very hot region. They just scatter like anything. You could imagine photons getting through if you're thinking about very, very long wavelength photons, namely magnetic fields. So it's an interesting question, and I haven't explored this, but somebody might like to look at this, that if you have magnetic fields, they will carry through into the next eon, and there could be some effects of this sort. I haven't looked at that at all. But what I have thought about is gravitational waves coming through. So gravitational signals can come through, and that is maybe you could see some indication of what's going on in the previous eon, if it did exist. I'm calling it an eon, just going back to the pictures that I was having before. I'm calling each of these.
Roger.
Yes? Hello?
A few minutes, please.
Okay, well, I'm nearly finished. I'm calling each of these sections each as an eon. So the universe is the whole lot of this, and each one of those is an eon. Okay, now gravitational signals can get through. And so what I'm considering is in the previous eon, there might be galactic clusters where black holes run into each other, and they produce signals which could come through. They would interfere with electromagnetic signals, and you would see them as colder or warmer rings in the sky. I won't go into the details of that, but I just show you this picture, which is a picture due to Vahe Gozejan, who actually explored initially, also has a Polish colleagues looked also at this, but they looked in a different way. Let's talk about Vahe's way. He was looking at rings in the sky. That's really the previous picture I had, where you see that the intersection of our past light cone with the future cones of these signals will be two spheres as they meet on the crossover surface, and they will look like rings. So you see, and these are marking the centers of the rings, and the blue ones represent colder points, and the red ones represent hotter points, as it is. That's sort of backwards, but never mind about that. The central ring is the central two sets of squares are removed from the picture. That's the galaxy. But the centers of these points, the centers of the rings are marked as points. And if they're singled out by being low variance, that is to say, the variation of the temperature around the ring is small, and you're looking at 3 concentric rings. That's the whole point, to get a strong enough signal. And what's remarkable about this picture is how clumped it is. And what's also remarkable is that they're clumped in color. And he didn't choose them from color, he chose them from the low variance. But if you now look at the temperature, you see that they are also clumped. So this means that these centers of galactic clusters seem to be very, very clumped in this previous eon, which is very surprising because people think of the universe as being very uniform. The final picture I want to show you has to do with another effect. Now, this effect is something which we also looked at. This I was looking at with my Polish colleagues, Krzysztof Meissner and Paweł Nierowski and Daniel Ann, who is a Korean who now works in the United States. And we sent a paper into the monthly notice of the Royal Astronomical Society, which was published now about 3 years ago, I guess. And we were looking for signals of a different kind. This is the black holes will eventually evaporate away by Hawking evaporation in the very remote future. And then finally they disappear with a pop. This takes about 10 to the 100 years for the biggest black holes. And what do you see? Well, what we seem to see, this picture is in the paper. The bottom horizontal line represents the crossover surface. And you see a black hole coming out there, which is evaporated. All the radiation, the Hawking evaporation radiation, since it happened so late, is squashed into a little point. So all the energy comes bursting through, and it comes bursting through. It spreads out and spreads out until 380,000 years. That's the second horizontal line. That is the microwave background line. And so that spot spreads out, apparently, to about 8 times the diameter of the moon. So you see these regions of heated, and we see them with a confidence level of 99.98% confidence. So extremely high confidence, certainly for cosmology, a very high confidence level that these spots are really there. Now, I don't know of any other explanation for those spots because we see them with this confidence level. and they're a clear prediction of the CCC cosmology. There is a little issue about exactly how big they should be, which people have brought up, but certainly it doesn't make that much difference. The main point is that they're there, and we see them there, and I don't know of any other explanation for these points. Thank you very much.
Thank you, Roger. We have time for one or two questions.
Okay.
Please, Professor Banheim.
Yes, yes. Hello, Roger. I have a question which is somewhat similar to the one I asked you when you gave a talk at one of our gatherings a couple of years ago. The question is whether the universe increases its number of killing vectors as it evolves or decreases them. Now, the one that where you've described, you said the Weyl curvature starts out at 0 and finishes up as infinity. It's really a question of the universe starts out uniform and then grows in homogeneities. And that will happen independent of whether there was a singularity at the beginning or a singularity at the end.
Well, let me just explain the situation. You see, it's true that you get Weyl curvature as you go on, but it disappears in the Hawking points. This is the point, that in the conformal picture, these are little singularities in the crossover. So they actually, because they happen so late, they're actually in the next eon, as they cross over, they are smaller than the Planck scale. So these are sure, you do get these singular points in the crossover. And it's those points are the only place where you may say worrying about killing vectors, because that's the only place where you get any Weyl curvature. It's all squashed into the Hawking points, and they more or less, well, they don't disappear, they're there. So they do represent a deviation from uniformity, if you like.
Yes.
But they're just localized as individual little points.
Yeah, so in a sense, when you say that the Weyl curvature is finite as you go through the crossover,
well, you're
really saying that there's always some form of inhomogeneity, even if it's only this one point.
No, that's actually not quite correct. Sorry, yes, I should explain that. No, it's quite intriguing because the points have it's like a Coulomb field. You see, there is a Coulomb field, a gravitational Coulomb field, which is in the Weyl curvature in the form which is conformally smooth across. You see, you have to use the zero rest mass field form of the Weyl curvature. It's a little bit subtle. And that is finite on the boundary. You see, the conformal curvature is 0, but the zero rest mass field form of the Weyl curvature is non-zero. And it has a finite integral, and that integral gives you the mass of the Hawking point. So you can actually, from the this is something in a paper which hasn't been published yet. I'm writing a paper with Christoph Meisner in which we are going into this very feature. That is to say that the Hawking points, or the galactic clusters, think about it, a galactic cluster, the universe ends up with pretty well individual galactic clusters which separate from each other. Each galactic cluster will have a few black holes swallow each other up. One black hole swallows up the galactic cluster. Basically, you have a black hole. That black hole radiates by Hawking evaporation. That radiation happens so late that it's all squashed into the Hawking point. So you do have Weyl curvature outside the Hawking point, but that Weyl curvature is quite harmless. It's finite, and if you use that Weyl curvature to perform an integral, you could find the mass of the Hawking point. So the Weyl curvature is not 0 as it crosses over.
Okay.
But it's a question of how you say it. The zero rest mass field version of the Weyl curvature is not 0 as you cross over, whereas the conformal curvature version does go to 0. So it goes to infinity in one form and 0 on the other form. But the thing is, that's why you shouldn't look at that part. What you should look at is the zero rest mass field version of the Weyl curvature, and that is completely finite. But it doesn't affect the geometry of the space-time outside the Hawking points. Outside the Hawking points, it's pretty well, as far as I know, I mean, I think it's a postulate, but I would say it is uniform. And the Hawking points.
I'm not sure I've followed everything you've said, but just let me comment.
Yes.
If you take a conformal invariant field theory like the Maxwell equations,
yes.
propagating in a conformal to flat geometry,
yes,
and the geodesics are conformal to straight lines, to Minkowski geodesics.
Okay, that's what's happening here. Yes.
Yeah. But that that would suggest to me that you should get a vanishing Weyl curvature. That's not a non-vanishing one.
Well, it's true. Well, you see, that's Weyl curvature
yes.
As a zero. I mean, it's this kind of puzzle because you've got two. I mentioned the puzzle without really going into it very much. You see, you have two different conformal. You mentioned like the Maxwell equations. Yes. So if you think of the Weyl curvature as a zero S mass field, it's conformally invariant. And that conformally invariant field is non-zero as it crosses the crossover surface. And if you integrate it over a sphere, you can get the mass of the Hawking points. Yes. And you're looking at that in maybe a conformally flat background. I should think that's
what I'm asking, yes.
Yes. I don't know if that's necessary, but it's certainly possible. I think I would certainly say, as a convenient way of looking at it, is that the Weyl curvature, let's just think for a minute. I think if you wanted to conformally match, you're in trouble if it doesn't go to zero.
Well, I think you have somehow you've got to give up conformal to flat geometry. That's what I think is happening at the cross.
I'm sorry. I have to stop this very interesting discussion. But we should
an interesting point. Yes, very interesting point.
Discussion hour at the end of this section. So let me only make a very short comment using my position as a chairman that in my talk tomorrow I shall present another cognitive view. In particular, instead of speaking about Hawking points, I shall speak about inflationary points. Okay, but let's leave it for my talk. So thank you, Roger, once more for your very inspiring talk. And let us go to the second talk by Professor Fabio Scardegli, Planck stars from a scale-dependent gravity theory. And various
Fabio, do you hear us?
Yes, yes.
So
I share my screen. Oh,
yes.
Okay. Yes, please.
Oh, okay.
Okay.
Can you see it?
Yes, it works.
Oh, okay.
So as I said, Planck stars from scale-dependent gravity. Please.
Oh, okay. Okay. So thank you very much to the organizers for the possibility to give a talk here. And
can you put it full screen?
Yes, sorry, full screen. Yeah. 1 second. Is that okay?
Yeah, great. Thank you.
Okay.
So I would like to talk to you about possible metric to derived from a scale-dependent gravity theory for Planck stars. And this is a collaboration with my friend Gaetano Lambiase in Salerno. And a paper on this topic will appear in next month on PRD, Physical Review D. So let me just give a brief general introduction to scale-dependent gravity, or if you want, the subset of asymptotically safe gravity theories. In many quantum gravity approaches, the basic parameters that enter the action, such as Newton constant, electromagnetic coupling, cosmological constant, become scale-dependent quantities. The scale dependence at the level of the effective action is a generic feature of ordinary quantum field theories. A typical scale-dependent effective gravitational action can be written in this way. You see here the standard Einstein-Hilbert action, where the gravitational constant, instead of being a number, is just a quantity depending on the energy or the momentum at which the system is considered, as well as the cosmological constant. In this particular application, I will consider essentially cosmological constant equal to 0, since I'm going to deal with a black hole problem, so local problems. Once you have defined a dimensionless Newton constant through this equation, it is possible to show that that the evolution of these scale-dependent quantities is governed by a differential equation, first-order differential equation, like this, essentially. And if you go to integrate this differential equation, you get a dependence of the gravitational Newton constant of this kind. As you see here, you can see deviation at high energy, in the high energy situation, in which if you push the energy of the system larger and larger, then you get the gravitational constant is going to 0. While on the contrary, in a small energy situation, you recover the classical space-time. As you see, here you have an integration constant, which is omega tilde in this case. I call it omega tilde, which is of course, we integrated the first order differential equations. So the sign of this parameter is crucial for the physics of the theory. Actually, the theory can be properly called the asymptotically safe gravity if this parameter is assumed to be positive. So that, as I said, gravity can be asymptotically safe from divergences. If you allow the parameter to be negative, then you are immediately outside the realm of asymptotically safe gravity, since, for example, you see that the G Newton can diverge, essentially will diverge at for values of the momentum of order the Planckian momentum. So, as I said, for when omega tilde is positive, then you have an ASG theory. When omega tilde is negative, then you should properly talk about, to nominate these as a scale-dependent gravity theory, more general class of theories. A second step in order to obtain a proper description of a black hole system is to introduce a link between the energy scale and the radial coordinate. And usually this link is introduced in this way. You see this equation essentially, if you take the equation for large r, essentially you get the inverse proportionality between the momentum and the space-like coordinate, the radial coordinate. So for large R, essentially these two are just the canonical momentum and space-like radial coordinate. Finally, when you put together these two expressions, then you arrive to a running Newton coupling. Running meaning that it depends on the radial coordinates R, which has an expression like this. Here we have introduced in this connection another numerical constant, which is another parameter, gamma. I will tell you about gamma in a few slides. In any case, this is actually not so crucial for the meaning of the theory. Essentially, can be assumed to be positive. As you see here, the theory is thought to incorporate somehow quantum effects because here you have the appearance of the Planck constant, or if you like, the Planck length squared. Now, what we can in this scale-dependent gravity approach, the classical Newtonian or general relativistic scale-dependent solutions can be obtained by essentially replacing the numerical Newton constant with this running G of R. For example, if we take the standard Schwarzschild metric, we can replace the Newton constant with the previous expression, and we get this scale-dependent Schwarzschild metric here, the lapse of this scale-dependent metric. It's a nice function, this one, since for large R, and this means for low energy, essentially, you recover the standard Schwarzschild behavior. While on the contrary, if you go to the small r, so if you go close to what in Schwarzschild is an essential singularity, actually, in a metric like this, you just see that the singularity, the central singularity, disappear, and you can have a behavior close by to the center of the radial coordinate system, a behavior which could be the Sitter space or the Sitter metric or an anti-de Sitter metric according to the sign of this product omega tilde gamma, or in the worst case, in case gamma is equal to 0, you get in any case a smooth function at the core of the metric. Obviously, we have the problem in general in this kind of theories to determine, to find possible values of the parameters omega tilde and gamma. As for gamma, I will tell you, I already told you essentially it can be assumed to be positive, strictly positive. There are papers of, for fundamental paper of Martin Reuter and Alfio Bonanno of about 20 years ago, where they determine gamma using general relativistic considerations, and they find that the gamma is equal to 9/2. Anyway, can be in general assumed to be a positive parameter. Instead, omega tilde, it's a bit different story because okay, what you do? Okay, you can write down the potential, the Newtonian potential of with this running coupling. You can expand the potential at for large R, and you have this expression here. And then, of course, the corrections to the standard Newtonian potential are quantum correction. You see H bar appearing here. And here the situation is a bit more intriguing, so to say, because until a few years ago, I mean 5 or 6 years ago, in order to fix the value of omega tilde, researcher in ASG community usually compared this potential with the quantum corrected Newtonian potential obtained by John Donoghue and Kriplovich and Shapiro in the model, the theory of general relativity seen as an effective field theory at low energy. Recently, however, recently I mean the last 2 or 3 years, doubts have been risen against this comparability of the two different approaches. So asymptotically safe or scale-dependent approach and the effective field theory, GR as an effective field theory approaches. And this because essentially it can be traced back to the different classes of Feynman diagrams that are probably summed up in the two different approaches in order to get the modified matrix. In any case, if we stay with the comparison with the Donoghue quantum corrected Newtonian potential, which I wrote the expression of the quantum corrections I wrote here, that's the expression obtained, published by Donoghue and collaborators, at least from 20 years now, so from papers from 2003 to today. We see that, well, a very simple comparison fixes omega to be equal to minus 41 over 10 pi. In any case, the important thing, fix omega to be negative. Even just 2 days ago, Ilya Shapiro told us that this coefficient should be 17 over 20 pi, and in this case, omega would be minus 17 over 20 pi. Anyway, the main message here is that this omega tilde should be, or at least could be assumed negative. Of course, once you consider this omega tilde negative, you cannot speak anymore about asymptotically safe gravity. You should be more careful and name your theory as a scale-dependent, generic scale-dependent gravity. But in any case, the interesting thing is going to explore what this negative omega tilde means, because if omega, there were papers of the ASG community until, as I said, a few years ago, in which omega tilde were assumed to be equal to the calculation made by Donoghue in the middle 90s, when this coefficient, the first calculation 94, 95, this coefficient was computed to be negative. So in that case, the omega would be positive, and the positive omega would have been result in a nice kind of black hole matrix, in particular a free singularity-free black hole matrix. However, it seems, at least using the more recent results of the Donoghue community, so to say, it seems that this omega tilde should be negative. So let's have a look what are the consequences of this. As I said, first of all, the G Newton in principle can diverge at the Planck scale. But even more interesting is to explore the structure of the black hole metric when omega tilde is negative. Supposing omega tilde negative, then the lapse has this expression here. Now the denominator can develop zeros, and therefore the metric can have singularities. In particular, it is possible to show that this is just a cubic equation. It is possible to show with a very simple graphical analysis that you always have for any value of positive masses, positive mass m, you always have one single positive solution. Maybe you can have also negative solutions or complex conjugate solution, but we are not interested in that since R is a real variable. And in general, if you go to plot the lapse, you see that for any for the parameters in this range, so R positive, gamma positive, and the mass positive, you have an essential singularity here, as I said, the singular positive zero of this denominator. Now the singularity is the radial coordinate of the singularity is greater than zero instead of being at zero, as for example in Schwarzschild. And you also have always one single positive zero of the lapse in general. So you have an horizon, a black hole horizon, which is on the graphic on this plot is here. And it is also possible to show that the radial coordinate of the singularity is always smaller than the radial coordinate of the horizon, which means that we don't have naked singularity. Singularity is completely covered by the horizon in full accordance with the cosmic censorship conjecture of Roger Penrose. And the interesting thing is going to explore a little bit what these two quantities, the horizon and the singularity, are going to do as a function of the mass of the black hole. If for large masses, the horizon is going to smoothly to the standard Schwarzschild horizon, so Schwarzschild metric is recovered. For vanishing mass, the horizon is going smoothly to essentially to the Planck length, which is from the physical point of view is reasonable, since any length below Planck length is physically meaningless. The singularity for a massless, for vanishing masses, black holes, is going to the Planck length. And on the contrary, when for very large masses, the radial coordinate of the singularities is going to scale as the cubic root of the mass itself, plus corrections. Note that in both limits, so for larger masses or for vanishing masses, we always have R0 smaller than RH. So, as I said, singularity results always to be protected by the horizon. But, well, here I have inserted a plot of the mass functions. The mass function of the horizon is the red line here. The mass function of the singularity is the blue line. And, well, the green line is just the mass function of the Schwarzschild, the standard Schwarzschild metric. You see that the red line approaches smoothly the Schwarzschild, the red line, so the horizon is approaching smoothly the green line of the representing the Schwarzschild horizon. Is also from these graphics, you see immediately that for any value of the mass, essentially the radial coordinate of the red line here is always greater than the radial coordinate of the blue line. So once again, the singularity is protected by the horizon. But it is interesting to focus a bit on the radial coordinate of the singularity. because these suggest the possibility. Suggest the possibility to use this metric as a kind of metric to describe these objects called Planck stars. In fact, what we have here, we have a central hard singularity located at this radial coordinate, instead of being located at r equals 0. The finite size looks actually of quantum origin. If you take a kind of classical limit pushing h bar to 0, you see that r0 goes to 0. So essentially, you recover the standard Schwarzschild. And then you can consider the wall collapsing matter, the wall collapsing mass, as concentrated into this central hard sphere. So now the central singularity is no more a point, a geometrical point of size 0. It's a kind of central hard sphere with a finite positive radius. And you can also compute the non-covariant volume and therefore the density of this matter concentrated at the core of the black hole. Of course, non-covariant volume for an observer at infinity. And the interesting thing is that this density results to be finite. So you don't have a divergence in the density of the matter concentrated at the center of the black hole. It's finite and it's of the order, it's practically equal to the Planck density. So 1 Planck mass for a cubic Planck volume. So essentially, just exploring these metrics suggested by the scale-dependent by a scale-dependent gravity model, and considering this omega tilde negative as suggested by the comparison with quantum corrected Newtonian potential, what we have obtained? We obtained a black hole that has a central hard kernel of finite size with a density which is of the order of the Planck density. And these are exactly the main characteristics, or maybe one of the main characteristics of the so-called Planck stars proposed by Rovelli about 10 years ago on the ground of general qualitative considerations. The finite size of the central core being of pure quantum origin is presumably due to the action of the Heisenberg uncertainty principle, which prevents matter to be arbitrarily concentrated into a geometrical point of size 0. The central kernel can, in principle, keep trace of the information swallowed by the black hole, and perhaps, but this is still a thing that we are studying, or we are exploring. Perhaps this could be a possible way out from the information paradox. Let me make a comparison with a previous proposal for a Planck star metric. Actually, the original educated guess made by Rovelli and collaborators for the metric describing these objects. They considered the Hayward metric. The Hayward metric is a nice metric because it's a singularity-free metric. But actually, there were no particular compelling argument in favor of this metric. And for sure, this metric has at least 2 odds from the point of view of the problem considered here. And the first is the fact that if you expand the metric in R, then you don't get the term 1 over R cube for large R expansion in order to match the quantum corrections to the Schwarzschild metric computed, as I said, by the GR as EFT community. And the second thing not so good is the fact that the Hayward metric is nice, okay, it develops for large masses develops two horizons. One is the outer horizon, which is a very nice horizon approaching smoothly the Schwarzschild horizon. The other one is an inner horizon, which could be a candidate or considered a candidate for the sides of this black core of our black hole. But the problem is that these, even assuming R minus as the size of this are the kernel of a Planck star, certainly such are the kernel does not increase in size when mass is increasing, as instead R0 does. So you see that for large masses, essentially, R minus is going to this constant L, which is usually identified with a Planck length. On the contrary, as I showed you before, the sides of this hard sphere at the center of the black hole should increase if the metric is the one suggested by this scale-dependent gravity theory, should increase as the cubic root of the mass. So something a bit more physical, so to say. To be precise, some of these odds has been cured by hand, but at the price of introducing a much more complicated lapse, essentially constructing a deformation of the standard lapse by hand in order to match in particular this expansion 1 over R cube for large R. So I think I go to my conclusions. This is what I would like to tell you today. The scale-dependent gravity approach suggests a general metric describing quantum effects containing H bar. The matching of this scale-dependent gravity metric with Donahue quantum correction to Schwarzschild metric suggests that these omega tilde parameter should be negative. The fact that omega tilde is negative implies a new geometry for this scale-dependent black hole. And this gives easily a prediction of a finite size singularity at the core of this black hole. The size of this black core describes exactly this main particular property of Planck star, which were introduced years ago via semi-qualitative arguments, while on the contrary, here in this context at least, they appear as a natural consequence of this scale-dependent metric with the omega tilde negative. There is also a potentially rich phenomenology for these objects. I just give some small hints, in particular the black hole evaporation with a final explosion occurring at scales much bigger than the Planck scale. And other possible contact with phenomenology for a short gamma ray burst or fast radio bursts, but today I don't want to speak about this. So I think I can finish here. I don't have anything else to say. Thank you very much for your attention.
Thank you, Fabio, for this very interesting talk. We have time for questions. First is from Dr. Hong Wu.
First, thanks for nice talk. I have a question. You say that this related to this talk related to information paradox. Explain me.
Yeah. Oh, okay. So we actually, this is just a kind of guess that we are trying to explore right now with my collaborators. Since we have this black hole which has a finite size core, so the matter is not totally, does not disappear in a geometrical point, but is contained in a bunch, in a sphere of finite size. So maybe this can save the information, so to say, from being completely crushed, completely destroyed in the gravitational collapse. That's a kind of intuition that we are just exploring now. So I'm not saying anything definitive on this topic.
Okay.
Okay, I have a question to Fabio. As far as I understand, speaking about the value of tilde omega, you consider only what follows from quantized gravity, but there also exist contractions due to quantum matter fields, which are of the same kind, but with different coefficients. What's your what will change if you take these corrections, in particular from efficiency into account?
Well, very nice question. I would like to know. Actually, it's one of the things that we are exploring now. Of course, this is just a pure gravity theory, so to say. We just took a metric with the characteristic that I told you, and see if this can have some attachment with a real, so to say, real model. Of course, it would be very nice to explore what kind of what kind of matter. So setting the metric into the left-hand side of Einstein equation, what kind of energy momentum tensor can generate a metric like that, or and also adding matter, as you said, adding fields, other fields. First of all, maybe electromagnetic fields or something, if this can change or can modify things. As are all avenues, all things, all research line that we are studying right now. So I cannot say anything definitive, so to say, on this.
Okay. Thank you. Any more questions? Okay. Please, Dr. Almeida.
Hi, thank you for the great talk, and sorry for not turning on my video. I'm not camera ready. I just want to ask just a little bit of clarification. You are talking here about a minimum volume, but it's not a singularity, right? You have all finite curvature, finite density. There's no infinite involved here, right?
Wait a second. What we have here actually is a finite volume, at least a non-covariant volume, because the radial coordinate of the singularity is greater than 0. But nevertheless, we have a singularity. I show you the lapse function. As you can see here you have a singularity. So in the singularity, in principle, well, it's a singularity. Instead of being at r equals 0, is at r equal r0 greater than 0. It's it's a spherical singularity, so to say, instead of being a point. So in that case, sorry, maybe you want to finish your question. Sorry, I just.
No, but this singularity is a discontinuity, right? It's not.
Sorry, I don't get it.
It is a discontinuity in the
a discontinuity. Yes, it's a kind of discontinuity. Yeah, exactly.
But this kind of discontinuity is to be expected from the event horizon, for example. We have a discontinuity there. So it's kind of a singularity, but a removable one.
No, I don't think this one is removable because, as I said, if you take the continuum limit, if you take the classical limit, you push h bar to 0, this singularity goes exactly in the standard Schwarzschild, the central singularity. So I don't think you can eliminate that with a change of coordinate, like the horizon singularity that, of course, you can, in this case of Schwarzschild, you can eliminate that passing, for example, to the Kruskal coordinate or whatever. But this one, I think it's an essential singularity.
I see. Thank you very much.
Okay, next question by Dr. Chen Zhelu.
Yes, thank you very much for the talk. I think this is sort of a related question to the previous one. So since this is the singularity, even it has a finite size, but if I remember correctly, the original Planck star hypothesis proposed by Carlo Rovelli is based on loop congruity in which there should be no singularity. And so what really supports the argument that this kind of singular objects can be a Planck star, which is supposed to be non-singular?
Okay, as I said, originally, I agree with you. In the paper of Rovelli, the original paper of Rovelli, Planck stars were considered a kind of non-singular object, and they were supporting this argument using, as I showed you before, the Hayward metric, right, which is a non-singular metric. Okay. Of course, in that the problem of this metric, as I say, is something that, for example, you don't have the matching with the first quantum corrections in h bar of the Newtonian potential of the Schwarzschild metric, and then you have a size of the central core which doesn't scale so nicely. I mean, it seems that if you push matter into a kind of a black hole described by a metric like this, the core of the metric remains of the same size. On the contrary, here you have something scaling in a physical acceptable way, so to say, with a mass. I agree with you that still there is this fact that a metric like the one that we proposed as a singularity, even if this singularity has a finite positive size, what to say? Maybe, okay, you still have a singularity, but at least you have some nice behavior for the density, for the finite density, and so on. Moreover, one thing I would like to point out, the Rovelli model, the initial model of these guys working on Planck stars, they were constructing the models essentially by hand, saying, okay, the matter cannot be compressed at arbitrarily large densities. The greatest density that we can imagine is the Planck density. And I suppose that okay, the collapse stops when the density reaches the Planck density. All this work was done, these kind of considerations were done essentially by intuition, by hand. On the contrary, here you do the calculation, you just ask the matching with the first quantum corrections, and immediately this gives to you that the omega t there should be negative, and therefore there should be a singularity with a size which scales exactly as you would like to have, so to say. So I think that these are nice properties. Maybe it's not the final word. I'm not claiming that this is the final theory of Planck stars, but I think that this model has some nice property.
Thank you very much. Yeah, I understand. Okay.
Okay. Let's thank Fabio once more for his talk, and now we have to go to the next talk by Professor Mariam Bouhmadi Lopez on about the classical and quantum cosmology of the very late universe. So, what is?
Thank you very much. Just share my screen.
Please. Mariam. Okay.
Can you see my slide properly?
Yes, yes.
So, thank you very much for the kind invitation. So, like the previous talk, which was more related to black holes, here I will move to cosmology, okay? And most of my talk will be on classical aspects of cosmology of the light universe, and then at the end of my talk, I will be moving to some quantum aspects. Okay, so the talk is based on several work I did on the last year with several collaborators, and the paper on which I will be talking about will appear on the slides. So first of all, my talk will be mainly about the late universe, as the title shows. So let me mention briefly what we know nowadays about the current state of our universe. So we know it's homogeneous and isotropic on large scales. We know only 5% of what is made of. And by these 5%, I mean the standard matter. The rest, we usually label it as dark, either on the form of dark matter, or then through whatever is induced in the late time acceleration of the universe that can be a cosmological constant, or usually we call it a dark energy component, which its true nature we don't know. Okay, now how do we know that? So this is coming essentially, at least the late time acceleration of the universe is coming from observation of the supernova back on the 90s. And this observation has been backed by several observations ranging from the measurement of the Hubble rates at different redshifts, the baryon acoustic oscillation, and also the cosmic microwave background, and how matter cloud the large current structure, okay, the matter power spectrum, the growth function, and so forth. Now, as I said before, what is the true nature of what is driving the current acceleration of the universe, we don't know. Okay, maybe the simplest case is a cosmological constant. Unfortunately, the lambda CDM, although it seems first ground that it fits everything, it has some problems. So in particular, what is called the H0 problem. So essentially, the Hubble rates that we get from supernova is different from the one that we infer from physics of the earlier universe, the CNV. Okay, so maybe we need something else. And an option could be to consider something that instead of behaving exactly as a cosmological constant, something that behave like W called dark matter. Okay, where W is a constant that describes the equation of states of dark energy. In any case, it's very close to -1, which is the case of a cosmological constant. Well, this is a way, so essentially by modifying the right-hand side of Einstein equation, but there are other ways. in which I will not truly speak about this talk, maybe at the end of the talk if I have time, in which rather than modifying the energy momentum tensor of the matter budget of the universe, we modified somehow the gravitational side. That can be done within the Palatini formalism, or for example, the metric affine formalism that we heard about this morning. Okay. But as I said, for my talk, I will stick to the first approach. So some cosmological constant or some effective dark energy. Now let me go to some equations, simple equations that describe this late time acceleration. So then we go to the Ricciardo equation, which is the one shown here. So if we are having accelerations, essentially this side has to be positive, which means essentially this is the matter side, so this other side that we have here should impose some repulsion, okay, or said in other words, well, the strong energy condition, like happened in inflation, has to be violated, okay? The simplest case, lambda CDM and W Kullback matter. Now, if we want to describe this Friedmann-Lemaitre-Robinson-Walker in an accelerated state, so a possibility to describe it is a cosmographic way, and a very smart way of doing it is by choosing some cosmographic parameter that have been normalized, as in the work by Sahni, Alexei Starovinsky, and Saini, so in which the rescaling of this cosmographic parameter, which is nothing else but Taylor expansion of the scale factor, is done such that it gives exactly one for lambda CDM. So here, what we can see is essentially a term related to the fourth derivative, the scale factor, the fifth derivative of the scale factor, and the third derivative of the scale factor. Well, you would say, well, there is a deviation here from 1, which would be this value over here. And the reason is that here we have included also a tiny amount of radiation. So what happened essentially as we go back, as we go back in the past, so with this line and this line here, so the three models which correspond to W Kullback matter, okay, with a different value of W, so in this one, phantom smaller than the equation state smaller than -1, cosmological constant -1, or a quintessence case. So it's slightly larger than -1. So at the past, dark energy has no influence. So all the model fits, while in the future, they might be, they can be different. In fact, in one case, we will head to the theta, and in other case, we'll be heading to what is known as a big rip singularity. So this from a background point of view. From a from a perturbative point of view, so we can perturb this Friedmann-Lemaitre-Robinson-Walker, and those perturbation, we can decompose them in Fourier modes. And in particular, what we show here is perturbation corresponding to a mode of the order 10 to -3 megaparsec -1, which is slightly smaller than the corresponding Hubble horizon, which will be roughly 10 to -5 megaparsec -1. And here we show essentially three things. So the perturbation on the gravitational side, so if we write the perturbation in terms of the Newtonian metric, okay, so this would be the perturbation on, as I said, on the gravitational side. This one is the perturbation on the matter side, including the Kullback matter. How does it deviate this perturbation respect to lambda CDM? And then finally, the perturbation on the dark energy side. The green line is lambda CDM, and this can be seen clearly. So there will be no perturbation if it will be clearly a lambda CDM. While in the other case, there can be some deviation. So this one would correspond to a phantom model. So an equation states larger than, smaller than -1, and this one a quintessence. While for delta M, there will be slightly some difference, one model or the other. But the most important one, and the one that I wanted to highlight, is this one over here. So what happened is that if we have some phantom energy driving the late-time acceleration of the universe, somehow the perturbation on the gravitational side will flip its sign. And that's the reason essentially of the big rip happening in the future, in the far, far future. Okay, that would be a singularity in the far future. Singularity in the sense that the curvature is not well behaved, and also that the geodesy cannot be extended beyond that point. Okay. Now, these are at the perturbative level. So if we change this mode K, so this line will move. Okay, at the background level, what happened essentially that there would be a singularity anyway in the future. Now, from an observational point of view, it can be seen that this model, W called black matter, defeats the data. So if we look at the F sigma 8, so they more or less defeats the current state. Okay. So this is the simplest case. Now I have been talking about this phantom model, and in some cases they lead to something right in the future. I spoke about the most known one, which is the big group. Okay. But there can be a whole bunch of them. So essentially in this kind of model, what's happened is that the energy conditions are not fulfilled. And in particular, what's happened is that the weak energy condition is not fulfilled. So the pressure and the energy density is negative, although the energy density is positive. Okay. And of course, the strong energy condition is not fulfilled, like happened in inflation. And there can be a whole bunch of possibilities in the asymptotic behavior. Here I will be talking only about a few of them, okay? About just some of the possibilities. Okay, so the first one that I talk about is what is known as about the big rip. Then I will be talking about two other more, the little rip and the little sibling of the big rip, that I will define in a moment. Those can be obtained from some specific equation state or through some scalar field, or also in some other kind of theories. So here is schematically, we see what happens essentially at very large scale factors, some geometrical quantities ranging from the Hubble rates, its time derivative, they could blow up at a finite cosmic time, like is the case of the big rip, or at some infinite cosmic time, like it's the case of the little rip or the little sibling of the big rip. And this is explained better on this table. So could be lambda CDM, so the universe would be asymptotically de Sitter, no singularities, or it could be that, well, the dark energy is so repulsive that at some point in the future, the geometry is not well behaved. Could be something smoother, like the little rip, where these singularity, like in the big rip, they happen, but at an infinite cosmic time. It would take a long, long time for these to happen. Or, like in the little sibling of the big rip, where these things happen, but not all the quantities blows up. But anyway, it would be on the far future and at an infinite cosmic time. There are other kinds of dark energy related singularities that I will not talk about in this talk, and here is the definition, okay, of the different kind. But here I will stick to these three kinds: the big rip, little rip, and little sibling of the big rip. And the difference with respect to this other is that these happen only if we have matter that correspond to phantom matter, which means essentially that violates the dominant energy condition. And of course, in all these models, as we have, as I will show in a moment, and as I showed before with the big rip, defeats the data. Okay, so let's see the fitting of the data for these other two models, the little rip and the little sibling of the big rip. And of course, if there is a singularity in the future or an abrupt effect in the future, that's where the quantum side of my talk ends. That would be by the end. Okay, so in order to fit those models, which are these three that I talked about, the big rip, an equation of state constant and smaller than -1, the little rip, where the equation of state is a deviation with respect to cosmological constant, as I showed here, and that deviation is essentially through this term, which is the square of the energy density of the dark energy. Or then for the little sibling of the big rip, where the deviation is simply by a constant A, which is positive, and this constant V, which is also positive. Okay. Now, if we do the fitting, how we did the fitting, so essentially we consider a bunch of data ranging from supernova, the Pantheon compilation, then some CMB data, the baryon acoustic oscillation, also some data, and H offset. So all these data constrain the background. So essentially they constrain the distances, okay? And for the three models, that we consider was this one, the big rip, the little rip, and the little sibling of the big rip. And as I said, well, here the big rip is a constant equation of state slightly smaller than -1. In this case, a deviation with respect to the cosmological constant, which on the equation of state is encoded on this term, and finally for the little sibling of the big rip is encoded on this other term that I'm highlighting with the mouse. Okay, with my mouse. Now what we have is to constrain this parameter over here, with this WD, this omega LR, and this omega LSER. Okay. So we start with the big grid. So what happened essentially that, well, here the equation of states would be slightly smaller than -1. And well, here there will be essentially, we expect roughly 30% will stay correspond to expected to dark matter. And well, and the Hubble rate slightly smaller of the other 0.7. Okay. Now for the little rip, so what's the equation says, I said, is smaller than -1, and in particular nowadays, and the omega L is rather small. Okay, so the deviation with respect to the cosmological constant is not that much. And finally, for the little sibling of the big rip, what would happen is that, again, this omega LSER, which is the deviation with respect to a cosmological constant, is not too big, it's rather small. Okay, so this is at the background level, right? Well, here are essentially the best fits. So lambda CDM is still the one that fits better, this model. And then the next one that fits better, the data would be the big rip, then the little rip, and finally the little sibling of the big rip. And this can be seen through the reduced chi-square, okay, which take into account already the degrees of freedom that we have, because in these three models, big rip, little rip, and little sibling of the big rip, we have 1/3 degrees of freedom. Okay? Now, these are the background level. What happened at the perturbative level? So at the perturbative level, so we start from our Friedmann, Lemaitre, Robinson, Walker, and then we perturb it, of course, from the gravitational side, the Einstein tensor part, and also from the matter parts. So we have perturbation that involves the dark energy side, the matter side, including the dark matter, and of course the radiation side, because we start our numerical integration well inside the radiation dominated epoch till nowadays. Now for then we need to fix our model for dark energy, which is essentially fixed through the equation of states of that, the perfect, of the model that we are considering, okay? The quantum dark energy we are consider. Once we work out the perturbation, we can find how does the perturbation on the matter side, on the dark matter side, on the dark energy side evolves. And of course, from there, from the matter side, we can get what is known as the matter power spectrum, and also F sigmas. Okay, so far, so good. Now, when we look at the perturbation of dark energy, we have to be careful. And we have to be careful because essentially the strong energy condition is not fulfilled. It's not a matter of that the dominant energy condition is not fulfilled, but the strong energy condition is not fulfilled. So this is general to any model of dark energy described by a perfect flow. So it's not a matter of phantom dark energy. And what happened is essentially that the adiabatic speed of sound, which is essentially related to how does the pressure change with respect to the energy density. The square of this quantity can be negative. And this is always the case if the strong energy condition is not fulfilled. So one way of handling the problem is by invoking some non-adiabatic perturbation, okay? And this is done by including what is known as the speed of sound at the rest frame. So these quantities of light. So usually what is done is to impose that this quantity here is equal to 1, like happening in minimally coupled scalar field, in which this quantity is exactly 1. And there's this other one, the adiabatic one, is coming from the model, the phenomenological model that we are using, okay? But as I said, CSD square is set to 1 as a phenomenological parameter. I will show later on what happened if that CSD square is different from 1, okay? Now we need to impose some initial condition, and the initial condition that we usually impose are the adiabatic one, which means essentially that the three components, radiation, matter, and dark energy, talk to each other. So once the initial conditions are imposed, and these are coming from the inflationary epoch, there's one over here. So once we fix the initial perturbation on the gravitational side, deep side, then we know how does the total perturbation behaves. And once we know the total how does the total perturbation behave, which is the delta ini, the total perturbation with respect to its background value, we know what is the initial value for the radiation parts, the matter parts, and the dark energy parts. Okay. Now, please notice here that the equation of state for dark energy is very close to -1, so one has to be careful with this term. Okay, because sometimes if you have phantom crossing, this term is not what we have. It's not the case for the model I will be talking about here. The same thing happened with the velocity, because when we perturb energy momentum tensor, we will have three quantities: the perturbed energy density, the perturbed pressure, plus the velocities, the off diagonal of that energy momentum tensor. As I said, all these perturbations are fixed through the some initial value that is fixed through the inflation rate. Okay, and I stress this CSD square was set to 1 in a phenomenological way. So this is what happens. So essentially, again, we perturb the different sector, and we decompose them in different modes. So here what we show how does the perturbation, in this case, the perturbation on matter, behaves for different scales. This is what state this case. So K1 is very close to modes that are currently entering the horizon. K6 are those that first exit the horizon back in the radiation dominated. And what we show here is essentially the perturbation on the gravitational sector. So in the past, so essentially they are the same. And then as they enter, so the first one to enter is the red one. So it's the first one to collapse. Then the second one to collapse, they decrease. Then the next one, which is the orange one, the green one, and so forth. Now you would say here what happens. So this zero state for nowadays, this would be the future. So what happened essentially in this kind of model, because they are phantom, essentially the perturbation on the gravitational sector, which is this psi, and then you gauge flip its sign, and that flipping depends on the mode we are considering, on the scale we are considering. So the first to exit, the first to enter the horizon in the past will be the last to experience this flipping on the gravitational potential. Okay. Now here what we show essentially for the for the perturbation on the dark energy sector. So for the matter sector, it's at first order is insensible to the kind of model, dark energy model we are choosing. The dark energy, no, so it depends on which model we are using. So this pink one, or the violet one, this one over here is the little rip, little signal of the big rip, the green one little rip, and the red one is the big rip. Okay. Now you would say, why do we have this big change back in the past? Well, remember that the perturbation on dark energy are, when we fix the initial condition, there is, we divide them by 1 plus W, the value of the equation state in the past. And that value can be different. So if it's a big rip, that big rip is with a constant equation state. So it will be the same for other models. But it's not the case for this other model, because it evolves on time. And now if we do a zoom for the perturbation on the on the gravitational potential for the different modes, zoom in the future. So what happened is the following, essentially what I mentioned before. So here we have again 3 color corresponding to the 3 models. The red one is the big rip, the green one, the little rip, and then finally this violet one, which is the little sibling of the big. So K1 is the smallest mode K, which means essentially are the mode that enter the horizon back in the past, the latest one to enter. And those are the first to experience the flip on the perturbation on the gravitational side. So this is essentially what is stated, is that when we approach the singularity, for example, the big rip, So what happened, this largest structure would be the first to be destroyed, and then smaller structure are the last to be destroyed. So as K grows, which corresponds to smaller structure, notice that this has dimensions of length -1, so the smaller structure are the one that will experience a flip on the change of the gravitational potential later. Okay. What about F sigma 8? So the three models essentially they overlap and they all fit the. Now, I said before that we have set CSD square, the square of the speed of sound of dark energy at the restraint to 1, and this has been done because it's what is usually done in analogy with what happened for minimally coupled scalar field. Now, what happened if we change the CSD square? And we change it for several values. Here I'm showing just what happened on the extreme case in which CSD square equal to 0. So if like it behaves like dark matter or something in between, okay, 0.2. So what happens is that we cannot go all the way to 0 because that would show a clustering of dark energy that we don't observe. So this case is essentially okay, because we would see some clustering of dark energy, but this is not observed. CSD can be small. We can go as small as 0.2, but it's not much more than that. Okay. Now the effect on the perturbation on the gravitational sector is the one I'm showing here. So this one, what happened is the CSD square is 0. So essentially there is a scale at which everything, all the perturbation of gravitational sector will flip its side, while here there is still a hierarchy. And the smaller is CSD, the sooner that's flipped on the gravitational potential. Okay. And well, this is shown for the three model. A is the big rip, B the little rip, and C the little sibling of the big rip. Okay, and here essentially it's a zoom of the same quantity. Okay. Now, what happens if there is interaction between dark energy and dark matter? I think I will have to hurry up a bit. So essentially on that case, so what we were trying is to see by switching on some interaction, some decaying of into dark matter or dark energy, can we remove some of these similarities? It turns out that after doing the fits, what happened is that this lambda is positive. Okay, as I will show in a moment. So if this lambda is positive, so essentially the effect we have is the other way around. There is a decline of dark matter into dark energy, which means that for this type of model, we cannot remove the singularity because instead, because R is the fit will tell us if lambda is positive or negative. And as lambda, it turns out that it's positive. So the decay is happening from dark matter into dark energy. So we don't, it doesn't have much with this. We said the lambda is positive, which at the end translates as there is a decay from dark matter into dark energy. Okay, so as I said here, the lambda is positive. So in the case in which there is an interaction for a big rip model, okay, given that there is a decay from dark matter to dark energy, as you can guess. So if you have a big rip, so what happens is that your big rip will correspond to an equation of states W that is even even smaller. Okay, so what happens is that the big rip will happen slightly before. And this is for, as I said, the fits the lambda is positive. Okay. Again, the decay of dark matter into dark energy. For the little rip, the same thing happened. The fits give us a lambda positive. So again, there is a decay of dark matter into dark energy, which means essentially that rather than having a little rip, what we end up having is a big rip. So lambda, again here, it's positive. Okay. Its best value. There are some in this region over here, a bit negative, but the best value is positive. Okay. Same thing here. And then, well, here essentially we compare with the three cases. So what happens is that even though we have included an interaction between dark energy and dark matter, with the hope to remove some of these singularities and abrupt events, it turns out that after doing the fit, given that that parameter lambda is positive, so what we have is a decay of dark matter into dark energy. So which means that at the end, we end up in all the three models with a big singularity rather than removing it. Okay, will induce a big fit, but that's it's essentially the fits. The lambda turns out to be positive. If we look at the F sigma 8, so essentially what we have is that well, it fits the 4 model or 5 model that's shown over there within the model. So here the interaction big flip, interaction little rip with the signal the big flip, interaction lambda CDM, and the pure lambda CDM. Okay. So this is from within the context of perfect fluid. So we'll briefly mention what happens if we have something more fundamental, and I choose as an example a 3-form field. So if we have a 3-form field, which is the next thing that we can have aside from a scalar field, we have also Kaysen's model as a way of explaining the late time acceleration of the universe. So the next thing, simplest thing that we can have is a 3-form. So let me briefly mention what are these 3 forms. They have been used previously in inflation and also as a mean of invoking a cosmological constant, because in absence of a potential, a 3-form behaves exactly as a cosmological constant. Okay. So 3-form is an antisymmetric tensor, a p-form in general. And in 4 dimension, we can have 0 form, which are scalar field, 1 form, which are vector, 2 forms, and 3 forms. Okay, so I will stick to the case of 3 forms, which is what I'm stating here. Okay, now, unlike vector field, okay, the 3-form can be embedded in an easy way in a Friedmann-Lemaitre-Thomson-Walker. So if we want to keep the symmetry, a homogeneous anisotropic universe, the 3-form make our life simpler. Okay, so is the next thing more complicated than scalar. Now, originally it was introduced because in absence of a potential, as I said, the V here, so this is the action for the 3-form, this its exterior derivative, this F, that's why we cannot have in principle a 4-form in dynamical 4-form in 4-dimensional space-time, because its extrinsic curvature will give us 0. Okay. Now 3-form, this A, so that's 3 forms. In absence of a potential will lead essentially to a cosmological constant. This F will be constant, so effectively it will be as a cosmological constant. So massive 3-form is a cosmological constant, and therefore it's a natural candidate in principle to induce the late time acceleration of the universe. Okay. So for Friedmann-Lemaitre-Thomson-Walker, there is only 1 degree of freedom, and in general for this 3-form, there is only 1 degree of freedom in a 4 dimension with this chi. And this chi, essentially there is a deviation with respect to a minimal coupled scalar field, which is on the kinetic term, this 3h chi. Okay, and what happened is that essentially the right-hand equation, if there is only a 3-form, so we can see easily that it can behave, it can violate the dominant energy condition as long as this term, or it behaves like a phantom matter, if this term over here is negative. Okay. Now, in order to compare the motion of this, or in order to study the motion of this 3-form, it's quite unlikely to rewrite the equation of motion in this way, as was done by Nelson and Tomiko Ivisto, and we use on our work with Sravan, João Marto, Moraes, and Imanol Albarrán. So essentially what's happened is that if you write the 3-form in this way, so you see clearly and easily that there is, aside from a critical point associated to the potential, which is essentially when the derivative, or when there is an extremal point of the potential, there is an additional one, and that additional one is this chi c, which is nothing, is related to the gravitational constants. Okay. Now we have 2 possibilities. Either we have a potential that is growing with the square of the 3 form, or is a decrease in potential with the square of the 3 form. Those are the two possibilities. And that is essentially what is shown on these plots. So if it's a potential that is growing with the square of the 3 form, so what happens essentially that the 3 form arrives, and well, at the end it sticks in this interval, and it stays at the minimum. While on this other case, which is the case that is more interesting on our study, so what happened is that the 3 form goes up, and it ended up either on this point or this point. This green curve is nothing else but the effective potential, okay, that fills the 3 forms. So it's the one that is giving us the dynamic. So it's end up at the minimum here, or in this green case here, or here. Okay, and those points, the second curve over here, those 2 points correspond essentially to a little signal of the big group. From an observational point of view, it can be seen that again this model defeats the data. Okay, so this briefly, and the last, I think, I don't know, 6-7 minutes, I will move to the quantum science. Now, on this model, we had some singularities of abrupt events, which essentially means for the big group that the curvature is not
5 minutes.
Okay, okay. Thank you. As I was saying, the curvature essentially blows up when we approach these points. And in addition, on the case of the big group, what happened is that the geodesics, they cannot be extended. Okay. Now, there is no successful quantum theory of gravity, and here I will use one of the many approaches. I could have used quantum cosmology, but I will rather use the Wheeler-DeWitt approach, which essentially it's an extension of the Schrödinger equation applied to the geometry of the universe. The first person, as far as I know, that started this analysis in dark energy singularities in a quantum framework was Klaus Kiefer and his collaborator. Okay, the first case that I will mention here is a case of scalar field. Okay, so in the case of a scalar field, if it's phantom, it's essentially that its kinetic term flip its sign. So this why we have this minus and minus here. And here I'm showing essentially the case of the little signal of the big group. The same thing can be done for a big group and the little. So because it's phantom, so it's like if you flip the potential. So instead of having the scalar field going down, what happens is that the scalar field goes up the potential. Okay, so that's the main difference. And this means essentially that this kinetic term that we have here is different. And this translates on the fact that the Wheeler-DeWitt equation has a plus here, doesn't have a minus, which is what usually happens with minimum Calvin scalar field with the standard term. So it can be shown, and I will not go, as I did on the previous slide, I will not go into the calculations. It can be shown that there are solutions to this wave function that satisfy the Wheeler-DeWitt equation, such that this wave function, when we approach the singularity, in this case the abrupt events of the little signal of the big group, what happens is that when this wave function vanish. And the fact that this wave function vanish can be interpreted as that the probability of reaching that region of the space-time is 0. Said in other words, that the DeWitt condition is fulfilled, and this can be interpreted as an abrupt event. Of course, the equation cannot be solved exactly, and we had to use some approximation, and the perturbation, and the approximation we use is what is known as the Born-Oppenheimer approximation. Okay, now the same thing can be done with the 3 form that I told you slightly before. The calculations are a bit more involved, but essentially if we rescale the 3 form chi this way, essentially this phi here, so we can diagonalize the Hamiltonian this way. Notice that unlike the scalar field, and that's why I wanted to show this example, there is minus plus. So it's like if we had standard scalar field, but no, it's a 3 form that will mimic the phantom behavior, but then the structure of the kinetic term will be preserved as with respect to a millimeter scale. Okay, we can do the several, we can calculate the Hamiltonian, as I said, we can diagonalize it, blah, 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 blah. And in the end, we arrive to our Wheeler-DeWitt equation over here. And a highlight here, we have a minus. Remember that before we had a plus. This is because we have a minus, we have a 3 form. Okay, so in that case, so what happened? Well, we have our Gaussian potential as we had before, the one that leads to a little drip. And what we see, again, it can be shown for in several approximations that there are always solutions that fulfill the DeWitt condition, which means that this abrupt event is harmless from a quantum point of view, in the sense that the probability of reaching that region is almost 0. Well, this can be done, and there's several approximations. Either we assume that potential is almost constant, which may be essentially we are at the top of the Gaussian potential, linear, so we are essentially in the slope of this Gaussian potential, also quadratic. And when I was typing this talk, I noticed, well, at the end, what we used was a von Oppenheimer approximation, we could have stick to the whole Gaussian potential. That's the result would not change. Okay, so I don't have time to go through what happened in modified theory of gravity, but what I wanted to mention was this: something similar can be done either within the Palatini formalism or also within the metric formalism. Okay, the Wheeler-DeWitt equation will of course change. So if we are in f of r, so the Wheeler-DeWitt equation would be this one. We have 2 degrees of freedom, one related to the size of the Friedmann-Lemaitre-Robertson marker, the scale factor r, the other one the scalaron, or said in other way, the degrees of freedom related to the scalar curvature. And again, it can be shown that for these several singularities, the Wheeler-DeWitt equation contains solution for the wave function that's vanished, which means again that the DeWitt condition is fulfilled. And something similar can be done in some Palatini type of theories, as we did with Pissen-Shen and Zedler-Shen and Imanol Albarran in the ABI theories. Okay, and with this, I move directly to the conclusion. Okay, so 5 minutes, as you told me, Professor Saravinsky. So essentially here, I summarize some models of dark energy, okay, some of them, and some of them, they can induce singularities, and therefore a quantum analysis is required. And then I briefly mentioned what happened in some modified theory of gravity within a metric formalism or within, sorry, let me go to the conclusion, or within a Palatini formalism. And that's it. Thank you for your attention.
Thank you. Thank you, Mariam. Okay, we have time for questions. Okay, Dr. Kumar.
Hi, Mariam. Thanks for the very nice talk. Actually, I'm wondering in quantum cosmology, the no boundary proposal is majorly, at least to my knowledge, majorly discussed in the context of early universe. I'm curious if no boundary proposal is relevant or applicable to the late time singularities.
The no boundary proposal.
Yeah.
Okay. Yes, I thought about this back in the past. I even discussed it with Klaus Schiffer. Now, the no boundary proposal, you have curvature, okay, special curvature. Now, the special curvature, if dark energy dominates, has no role in the future, which means that I essentially don't know how to apply the no boundary proposal. So what I mean essentially, the curvature, the one that will give you that's half a sphere, we will not have it in the future, because 1/a² is subdominant respect to dark energy. And the same thing would apply, and this also I thought about it, if can we apply the tunneling boundary condition? Okay, and the same thing apply. The 1/a² does not, I mean, it's subdominant with respect to the dark energy components. So if dark energy or even a cosmological constant keep going on, okay, so I don't know how to apply these two boundary conditions, the no boundary condition and also the tunneling condition.
Okay.
That's the reason why you usually apply the width condition.
Thank you.
Any more questions? Okay, if there is no questions, let's thank Mariam once more for this very interesting talk. And let's go to the next talk, our last talk today by Professor Robert Brandenberger, Emergent Matrix Space-Time from Matrix Theory.
Great. So, can you see my slides?
Yes, yes, sir.
Okay. And can you see my cursor? It's a small cursor.
Yes.
Okay, so first of all, I would like to thank the organizers for inviting me to speak. And the new work that I'll present is work that I've done in collaboration with Shudo Brahma, who's currently in Edinburgh, and with my excellent student Samuel Laliberté at McGill. So I think you all know that the inflationary scenario is the current paradigm of early universe cosmology, and it is usually analyzed using an effective field theory framework. And later on, I'll say exactly what I mean by this. Now, what I will argue at the beginning of the talk is that there are fundamental conceptual problems for any effective field theory description of an expanding universe, in particular of a rapidly expanding universe. And in light of this, I think if we want to understand the early universe, we have to go beyond an effective field theory description. So I hope to persuade you of these points. And so if you're persuaded by these points, then one needs to look beyond. And I will present to you an approach which is trying to look beyond, and it is matrix theory cosmology, where we are obtaining emergent metric space-time from a particular matrix model, the Banks-Fischler-Schenker-Susskind matrix model, which was proposed in the late 90s as a non-perturbative definition of superstring theory. Now, we're warning, I'm not a string theorist, and so in this last part of the talk, there could be mistakes. But anyway, I hope to persuade you that even if it ends up not being correct, it's still interesting approach. Good, so this is the outline of the talk, and I will begin with the trans-Planckian censorship conjecture, which in the last 3 years got quite a bit of attention. So this is an old slide, which comes from work 20 years ago by Jérôme Martin and myself. And here you see a space-time diagram of inflation. So vertical axis is time, horizontal axis is physical distance. And the period between T sub I and T sub R is the inflationary period, which I drew now as, in this slide, I drew as a period of almost exponential expansion. So in this diagram, I have various length scales. So first of all, I have the horizon, which is the forward light cone of a point on some initial hypersurface. And during inflation, the horizon expands exponentially. The second length scale is the Hubble radius, which is defined as the inverse expansion rate. And the third length scale is the physical length corresponding to fluctuations which we observe currently in the universe. So that's the red curve. And inflation can provide a successful mechanism of structural formation because this red curve emerges from being sub-Hubble at the beginning of inflation. But as we pointed out 20 years ago, if inflation lasts a little bit longer than it has to, then the length scales that we observe today start out with a length smaller than the Planck length. And so we argued back 20 years ago that there's a breakdown of effective field theory, which happens in this zone of ignorance. Now, based on this diagram, Bedroya and Vafa put forward a conjecture. And they said that in no cosmological model, which is consistent with quantum gravity, it can ever happen that trans-Planckian modes exit the Hubble horizon. So if we take a spatially flat metric, the H inverse is a Hubble radius. So the following inequality has to be satisfied. So if we start at any time t sub I with a Planck length and let the scale evolve to any later time t sub r, you have to remain smaller than the Hubble horizon at that later time t sub r. So this boxed equation is a statement of the trans-Planckian censorship conjecture. So now I'll give you 3 arguments in favor of this conjecture, and none of these arguments depend on string theory. So the first is an analogy with Penrose's black hole censorship hypothesis. So we know that general relativity has an effective field theory, has solutions with singularities. So if you take a black hole with charge smaller than the mass, then an observer far away from the black hole, well, there is a singularity at the center, but the observer never sees a singularity. The observer is shielded from the bad stuff by a horizon. Now, the effective field theory of general relativity admits solutions with charge greater than a mass. And for these solutions, the observer far away from the black hole is not shielded from the bad stuff that happens at the horizon. And so Penrose basically postulated the conjecture that in the correct ultraviolet theory, these pathological solutions cannot appear. The external observer has to be shielded from the singularity by a horizon. So let's translate Penrose's hypothesis from position space to momentum space, from black hole physics to cosmology. And this is the translation scheme. So position space becomes momentum space. This black hole singularity becomes the space of trans-Planckian modes. The black hole horizon is replaced by the Hubble horizon. And under this translational scheme, Penrose's black hole censorship conjecture states that an observer measuring super-Hubble horizon modes must be shielded from the trans-Planckian modes. And this is precisely the trans-Planckian censorship conjecture. And the reason why we choose the Hubble horizon to generalize the black hole horizon is that fluctuations only oscillate on sub-Hubble scales, and they freeze out and become squeeze states and classicalize only on super-Hubble scales. So it's the Hubble horizon which differentiates things that classicalize from things from quantum junk. Okay, now the second argument in favor of the trans-Planckian censorship conjecture is a unitarity issue. So by effective field theory, I now mean general relativity coupled to matter, where we expand all matter fields in co-moving oscillator modes, and we quantize each of these co-moving modes like a harmonic oscillator. So that's what I mean by effective field theory. Yeah, very conservative definition. Now, to avoid the Planckian catastrophe, you need an ultraviolet cutoff, and it has to be at a fixed physical scale. And to maintain a fixed physical scale in an expanded universe, you need continuous mode creation, which is non-unitary. So this is an argument that dates back to a paper in 1985 by Nathan Weiss, and which was recently resurrected in the paper by Kotler and Strominger. So if we demand that the classical region be insensitive to the non-unitarity, we again get precisely the trans-Planckian censorship conjecture. Now, this point has an extra consideration. So there's a relationship between the effective field theory problem and the cosmological constant problem. So the quantum aspect of the cosmological constant problem comes precisely by taking all matter fields, expanding in Fourier modes, quantizing each Fourier mode, and taking the ground state energy to be gravitating. So if we have an approach to early universe cosmology in which we never quantize harmonic oscillators, then the cosmological constant problem will take on a completely different light. So this is just a side remark, but I'll come back to this at the very end of the talk. Now, the third and the weakest argument in support of the trans-Planckian censorship conjecture is an entropy argument. So in black hole physics, people talk a lot about entanglement entropy density between sub and super Hubble modes, horizon modes. Let's do the same thing in cosmology. We can compute the entanglement entropy density between sub and super Hubble modes. And if we have a phase of inflationary expansion, the phase space of super Hubble modes is growing, the entanglement entropy density is growing. And if we demand that the entanglement entropy density remains smaller than the post-inflationary thermal entropy, we get the upper bound on the duration of the inflationary expansion, which is exactly the same as what we get from the trans-Planckian censorship conjecture. Okay, so now if we apply the trans-Planckian censorship conjecture to inflation, then we get what I sketch in this graph. So the trans-Planckian censorship conjecture says that the initial Planck length cannot grow to be larger than the Hubble length at the end of inflation. But if you want inflation to be successful, then the current Hubble radius has to originate from inside of the Hubble radius at the beginning of inflation. So upper bound on the duration of inflation, lower bound on the duration of inflation. And obviously, whether these two bounds are consistent or not depends on the location of the Hubble horizon relative to the Planck length. So you do the algebra. This is the upper bound on the duration of inflation coming from the trans-Planckian censorship conjecture. T sub star is the beginning of inflation. This is the lower bound on the duration of inflation coming from demanding that the current Hubble horizon originates inside the Hubble horizon at the initial time. Then you find that the energy scale of inflation has to be smaller than 10 to the 9 GeV. Good. So, fine. There's also implications for dark energy. Dark energy cannot be a bare cosmological constant. Otherwise, at some point in the future, you'll be faced with a trans-Planckian problem, and even quintessence models of dark energy are constrained. Good. So now, the second point that I want to make in this talk is that there are alternatives, that inflation is not the only early universe cosmology which is consistent with observations. And by observations, I mean, for example, we want to reproduce this plot of the anisotropies of the microwave background. So angular scale, amplitude of anisotropies of the cosmic microwave background, black dots, data points from WMAP, and there's some systematic uncertainty on large angular scales, and some statistical errors on small angular scales, which are now much, much smaller. And this red curve is a 6-parameter fit. You fit 6 parameters of late-time cosmology, and then you get this agreement. And the physics that goes into this curve was well understood 10 years before inflation. And this is a plot from the paper by Zeldovich and Zunyaev of 1969, 1970. Vertical axis is time. Horizontal axis is co-moving distance. This is the time of recombination when the microwave background is released. And Zeldovich and Zunyaev argued that given a spectrum of fluctuations on all scales in the early universe, and these are standing waves if the wavelength is larger than the Hubble horizon, which is this curve, which I'm tracing out with my cursor now. So given this initial condition, then you will get the exactly these acoustic oscillations, which I showed here. Now, the way this comes about is the following. The fluctuations are standing waves until they enter the Hubble radius, then they start to oscillate. So the mode that enters the Hubble horizon right at recombination, it has had no time to oscillate. We catch it at maximal amplitude, maximal delta t over t. This mode, which has done 5/4 of an oscillation, we catch it at the local minimum, and so on. So this physics was well understood back in 1970. Okay, so this is what I state here. Now, what was not understood in 1970 is how does one get this scale invariant power spectrum of adiabatic fluctuations on scales which, from the point of view of standard cosmology, look super horizon. This looks rather acausal from the point of view of standard Big Bang cosmology. So let's formulate the criteria for a successful early universe cosmology. So first of all, in order to explain the rough isotropy of the microwave background, the horizon at recombination has to be much, much larger than the Hubble radius at recombination. So that's a criterion in order to solve the horizon problem. Now, in order to have a causal mechanism of structure formation, you need scales that we observe today to originate inside the Hubble radius at early times. Otherwise, you don't have a causal mechanism by which you can locally produce fluctuations. And finally, you need that the mechanism which you invent to solve issue 2, you need that to produce scale invariant spectra of perturbations. So these are the 3 criteria for a successful early universe cosmology. And as Alexei discussed first, inflation is indeed the first scenario based on causal physics in which these 3 criteria are realized. So let me go back to this space-time diagram of inflation. You see, during inflation, the horizon expands exponentially compared to the Hubble radius. So criterion 1 satisfied, the horizon problem is solved. If inflation lasts long enough, scales that we observe today start out sub-Hubble at the beginning. Criterion 2 satisfied. And the fact that the density is approximately constant in this phase leads you to a scale invariant spectrum of curvature perturbations. So among all expanding models, it's specifically models with approximately constant Hubble radius, which give approximately scale invariant spectra of perturbations. Now, the second scenario, in which you can satisfy all 3 criteria, are bouncing cosmologies, certain sets of bouncing cosmologies. So now here I'm imagining that the universe starts out in a phase of contraction. So scale factor is a function of time. There's some new physics that gives you the transition between contraction and expansion. So standard Big Bang-like contraction, standard Big Bang-like expansion. This is the corresponding space-time diagram, co-moving distance versus time, bounce point. So time runs from -infinity to +infinity, no causality problem, no horizon problem. Fluctuations start out sub-Hubble. So second criterion satisfied. And it turns out that there are certain classes of bouncing cosmologies in which initial vacuum perturbations become scale invariant. Not all, but certain classes. But I'm not going to talk about bouncing cosmologies here. The model that I'll present is an emergent universe. And in the emergent universe, you have the following assumption for the scale factor. Scale factor as a function of time. We assume that there's an emergent phase, which can be modeled as approximately quasi-static, and then a phase transition to the phase of expansion, standard Big Bang expansion. So this is the assumption. And this is the resulting space-time diagram. Time, space. Here I plot physical distance. This is the emergent phase, quasi-static. Time runs from -infinity to +infinity, so horizon problem is solved. Fluctuations start out sub-Hubble. And now it turns out that if in this phase you start with thermal fluctuations, with holographic scaling, that then you will get scale invariant spectra of curvature perturbations and gravitational waves. So the bottom line is that they're not just inflationary cosmologies, which are consistent with current data. Now, it's clear that bouncing cosmologies and emergent cosmologies require going beyond effective field theory, because you can get a bounce and you can't get an emergent universe if you stick with Einstein gravity and usual matter satisfying the energy conditions. And now I also tried to argue that if you want inflation, you also should go beyond an effective field theory. in a way that, for example, Gyadvali has been promoting, or in a way that Keshav Dasgupta and his collaborators have been promoting. So all early universe scenarios require going beyond effective field theory. Okay, so hopefully I've persuaded you of this. And so let me give you now an example of an emergent cosmology. And the example of an emergent cosmology is string gas cosmology, which is what Vafa and myself developed back in 1989. So the idea is to make use of symmetries and new degrees of freedom, which differentiate string theory from particle theories. So we have to make the assumption that there's a background of space-time, and we have to assume that space is compact, a 9-dimensional compact torus. Now, the new degrees of freedom, which point particle theories do not have, are oscillatory modes and winding modes. And the oscillatory modes lead to the fact that there's a maximal temperature for a gas of closed strings, called the Hagedorn temperature. And the fact that they're winding modes leads to the fact that there's a new symmetry. And the new symmetry states that physics at large radii is equivalent to physics at small radii. And here's the mathematics. So the symmetry between large radius and small radius, you replace R by 1 over R in string units. You just have to exchange the quantum numbers of momentum modes and winding modes. So that's a new symmetry. So if you get a gas of strings in a box of radius capital R, and you shrink the radius of the box, then the temperature will first rise. But eventually, the temperature will be so high, the energy density will be so high that you can create oscillatory modes of the strings, and the box can shrink without the temperature rising. And once you get below 1 in string units, then the energy can all drift into winding modes and the temperature will decrease. So the assumption that we made back in 1989 is that we start the time evolution in this hot string phase, the Hagedorn phase. And we argue that this might be quasi-static. So this is the Hagedorn phase. This is the post-Hagedorn phase. And this transition is the annihilation of string winding modes into string loops. This gives rise to this. And then what we did is we computed the density perturbations and gravitational waves which result from this scenario. And we proceeded in this way. We computed the matter correlation functions in the Hagedorn phase, energy density perturbations, pressure perturbations. And then we converted them to metric perturbations, length scale by length scale when the scales exit the Hubble horizon. So this all can be computed using the finite temperature correlation function of a gas of strings. And these are the equations. So the curvature perturbations, where did my cursor go? Curvature perturbation phi and the gravitational waves Hij are given by the energy density fluctuations of diagonal pressure fluctuations respectively. So we take the finite temperature partition function of strings, we compute these quantities, and then this gives us the curvature perturbations and gravitational waves. So this is a computation for density perturbations, curvature perturbations. The density perturbations are given by the specific heat capacity. The specific heat capacity for a gas of closed strings has this holographic relationship. So this is a specific heat capacity in a box of radius R. You combine the formulas and you get a scaling invariant spectrum of curvature perturbations whose amplitude is given by Planck length divided by string length to the 4th power. This is scaling invariant, like for inflation. It has a slight red tilt, like for inflation. You compute gravitational waves, you get a scaling invariant spectrum like for inflation, but a slight blue tilt, unlike for inflation. And you get a consistency relation, which says that the tilt of the tensor modes is 1 minus the tilt of the scalar modes. Okay. Good, so this was a toy model. It was a toy model because we didn't have any equations that gave us the emergent phase. Now, Alexei, can you please give me the 5-minute warning? I think I still have 10 minutes. So anyway, so now we will try to
Yes.
we will try to construct a model of emergent space-time and of emergent early universe cosmology coming from a non-perturbative proposal for superstring theory. Okay, and so given that context, we take a conservative point of view because we are taking a matrix model, which was proposed by Banks, Fisher, Schenker, and Susskind. And they propose it because perturbative calculations in this matrix model give the same result as perturbative calculations in string theory. So this this model is a quantum mechanical model of n by n Hermitian matrices, 10 n by n Hermitian matrices. There's no space, therefore no singularities. And this is the Lagrangian of this matrix model. So there are 9 matrices X sub I, n by n Hermitian matrices. There's the first term, which looks a little bit like a kinetic term, the second term, which looks like a potential term. And there's an operator d sub t, which involves both. So it's time derivative plus commutator with a 10th matrix A sub 0. So this is the Lagrangian which was proposed. And again, to get the agreement with string theory, you take the 't Hooft limit. So this is a well-defined model, quantum mechanical model, no space. So now we will consider this matrix model in a high temperature state. And by high temperature, I mean the following. I mean a temperature which is so high that the action is dominated by the 0 modes of the matrices if you expand the matrices in Euclidean time direction. So the Matsubara modes. And then it turns out that the action for the 0 matrices is the action of the IKKT matrix model. And then there are corrections to this IKKT action, which are of the order 1 over t. And the action of the IKKT model, this is a pure matrix action, no space and no time. So this is the action, this is a partition function. So now from this, we want to construct our space and time and our metric. And then eventually we will go back to the BFSS matrix model and take the thermal fluctuations and compute curvature perturbations and gravitational waves. So that's the logic. So these are Hermitian matrices. And so what we can do is we can diagonalize one of them, and we will diagonalize A0, the temporal matrix. And the eigenvalues of this matrix become the values for time. Now, it can be shown that the expectation value of A0 square is of the order kappa n square in the large n limit. And this implies that the maximal eigenvalue scales as square root of n, and therefore the difference between eigenvalues goes as 1 over square root of n. So the limit capital N going to infinity, we get infinite continuous time. Now the eigenvalue is also symmetric about 0, and so our infinite time runs from minus infinity to plus infinity. So this is not new. This is proposal by Nishimura and collaborators. They've been working in the context of this proposal for more than 10 years. So this is our emergent time. So we continue working in this basis, and now we look at these spatial matrices. The AI matrices, these are spatial matrices. And we look at how the matrix elements of these spatial matrices evolve if you go away from the diagonal. And you can show analytically that if you go a distance bigger than n sub c away from the diagonal, where n sub c is given by the square root of n, that then these matrix elements decay rapidly. Whereas if you stay within this band, they are approximately constant. So this fourth line on this slide, there's only numerical evidence, which we borrow from this reference. But line 3 and line 5, you can show using the Riemann-Lebesgue lemma. Okay, so what we will do now is we will construct a time-dependent space. So what we do is we pick a time, which is some location, a distance t down the diagonal. We go the corresponding distance t down the diagonal of the spatial matrices, and we take small n I by small n I subblocks centered at t. So those are our submatrices ai tilde of t. My ni's, they will be the co-moving coordinates. Okay, so now these objects have again been studied by Nishimura and collaborators. They look at what they call extent of space parameter. And they first of all found that in a thermal state, including fermionic matrices, there's spontaneous symmetry breaking. The SO9 symmetry gets broken to SO6 cross SO3 in the sense that only 3 of these extent of space parameters become large, the other 6 remain string scale. 3 become large. That's very interesting. This is exactly what Vafa and I found back in 1989. And we had a good argument for why it's exactly 3. Okay, good. So now what we are going to do is we are going to take this extent of space parameter for a submatrix of size n sub I, and we are going to define this extent of space parameter as the physical length of a curve from n equals 0 to n sub I. So this is a definition. Now, once we have physical length and co-moving coordinates, we immediately have the metric, at least the II component of the metric. So here on this slide, you see how we get the emergent time, sorry, the emergent space, and the spatial part of the emergent metric. And using the properties of these spatial matrices, you can show that the emergent metric, the II components, become independent of n sub I. So you get a spatially flat metric that emerges. Spatially flat metric. Now, thank you. Lorentz invariance is built into the original Lagrangian. Good. So now, in the subspace of matrices that correspond to the 3 large dimensions, you can solve the classical matrix equations at late times, and you find that the scale factor scales as t to the 1/2. So, like in radiation, there's no sign of a cosmological constant, and there shouldn't be because we never quantize any harmonic oscillators. Good. So now, the symmetry breaking, which I was talking about before, was shown for the 0 modes, for the IKKT matrix model. Now, we have shown that there is symmetry breaking also in the BFSS matrix model, although we haven't verified that symmetry breaking takes you to SO3 cross SO6. But the argument, the physical argument that I have immediately would also extend to BFSS. So we assume that the symmetry breaking pattern happens. Now we go back to the BFSS matrix model. We have the action, we have the thermal corrections, we have a thermal state. We can compute thermal correlation functions. We can compute energy density correlation functions, pressure perturbation correlation functions. So these can all be calculated exactly like we calculated them in string gas cosmology. We have a partition function because we have the action, and therefore we can compute partial derivatives of this finite temperature partition function that gives us the density perturbations and the pressure perturbations. So we use exactly the same equations we use in string gas cosmology. And we have to make this crucial assumption that in the infrared, the semi-classical Einstein equations apply. And then you won't be surprised to hear that we get exactly the same results that we got in string gas cosmology. We get a scale-invariant spectrum of curvature perturbations with a Poisson contribution for ultraviolet scales And we get a scale invariant spectrum of gravitational waves without a Poisson contribution on ultraviolet scales. So this BFSS matrix model seems to yield emergent infinite space, emergent infinite time, an emergent spatially flat metric, and an emergent early universe space with thermal fluctuations which lead to scale invariant curvature perturbations and gravitational waves. Now, obviously, there are a huge number of open problems. So a lot of the results, although not the results on the phase transition, but a lot of the results were calculated neglecting the effects of the fermionic matrices, which are part of these matrix models. So we would like to understand the effects of the fermionic matrices. And specifically, I think that will allow us to understand the phase transition better, and that will allow us to calculate the spectral indices. But if we are successful, we would also like to understand the emergence of a low energy effective field theory that describes the world on observable scales today. So to do that, we need to identify strings as excitations of the matrix model, particles as excitations of the matrix model, and to study how they interact in the context of this matrix model, and to see how this is modeled in terms of effective field theory. So there are a huge number of open problems, and obviously the whole program could collapse. And so I would like to end with 2 pages of conclusions, 1 page of robust conclusions. So inflation is not the only scenario of early universe cosmology, which is consistent with current data. And in light of the trans-Planckian censorship conjecture and other conceptual problems, I think effective field theory models of inflation are not viable. You need to go beyond effective field theory. We certainly, and therefore we need to go beyond point particle effective field theory, no matter what early universe scenario you want to implement. So I consider these to be robust, but I know that there are somewhat controversial conclusions. And so if you accept these conclusions, you have to try to do something which is not effective field theory. And so this is what we try to do. And so these are the results that come out of our attempt. And so we started with a well-defined matrix model. It's a well-defined starting point, and we have a prescription of getting emergent time, emergent space, and an emergent metric. And we have a thermal state to start with, so we can compute thermal fluctuations. We get scale invariant spectra of cosmological perturbations and gravitational waves. And there seems to be no cosmological constant. So these are quite exciting conclusions which are exciting to me, but this might be considered a wild attempt. So I'll go back to the previous page and thanks for listening.
Thank you, Robert, for this very inspiring talk. Any questions? We have time for questions. Professor Mannheim?
Yes. Robert, hello again.
Hi.
Hi, I've got a couple of questions. Back on page 16, you gave this little bound, if you can put it back up again, because you've been using it quite a bit. A bit more.
This one?
Yeah, but that's it. Page 16. One page, that's it, yes.
Right. And this comes from this graph.
Yes. What you mentioned at the time was that you assumed that in the trans-Planckian era, the universe was spatially flat.
No. Not here. Not at all.
Oh, well then we'll go back to page 16 a second.
Okay.
I thought that's this relationship, the top relation.
Okay, so you mean the algebra that I did here? There, yes. I did that in the context of spatial flatness. Yes.
Yes. Now,
but I could put in spatial curvature as well, and it wouldn't change the analysis.
Oh, you mean it holds with spatial curvature?
Yeah, we give order 1 factors.
Oh, okay. Okay, that was.
See, the challenge is to get, if you introduce spatial curvature, then you can't introduce too high positive spatial curvature at the beginning, otherwise inflation will not start. So if spatial curvature is there at the beginning of inflation, but inflation starts, then it will soon become irrelevant. And so therefore, these bounds will only change by a factor of order 1.
That's what I was asking. Now, the other comment is, it seems that your matrix model doesn't have a cosmological constant, but when the universe cools down, it'll go through a phase transition and induce one, just as the free energy released in a phase transition.
Sorry, you are violating energy, you are violating fundamental principles when you say that a cosmological constant is induced.
Well, what happens in the phase? Is there a phase transit? Is there an electroweak phase?
Sure, there are many phase transitions.
But what happens?
These phase transitions do not change the underlying cosmological constant. No phase transition changes the underlying cosmological constant.
No, they release free energy. Well, you
but
can call it what
energy
you
is
want.
not a cosmological constant.
Yes, but it's still there, and it's
But
a huge.
it's not a cosmological constant.
Well, it's still a huge contribution to the energy budget.
Yes, but it's something that is divided into radiation and matter.
No.
Sure.
Why should it be?
Well, because that's what happens in a phase transition. You transform potential energy.
Yes.
In the trapped vacuum, you transform that into quanta of particles.
I don't see why it goes into the geometry. It doesn't have to go into particles.
No, it doesn't. That's way subdominant.
Excuse me?
That's not that. I don't agree with this.
Okay, that's fine.
I can add just to this question by Professor Mannheim, that in our usual life, we see many phase transitions with energy increased, but this it does not generate any cosmological constant. So that's why I would say that from the point of condensed matter physics, it just presents us many examples of phase transitions. I don't know, logical constant is generally rated. Okay. Any more questions? Kumar, Dr. Kumar, please.
Hi, Robert. Thanks for the very nice talk. I do not know if I missed somehow. Did you mention any prediction about tensor to scalar ratio from the?
Yes. No, I didn't mention it. So in string gas cosmology, we do have a rough prediction for the tensor to scalar ratio. So in string gas cosmology, the robust consistency relation is NT equals 1 minus NS. And roughly, order of magnitude, the tensor to scalar ratio is 1 minus NS square. But that's just rough.
That 1 minus NS square is almost like the prediction of R plus R square model, right?
Right. So there are many models that predict
of the order of
that.
Yeah.
But so this is why I didn't mention that. Or I mentioned the robust consistency relation.
Okay. I have another question actually. So as you showed in the emergent universe, so you have the standard GR like behavior, GR standard radiation dominated era. I'm curious how the transition from strings to GR happens.
Yes.
And precisely, is there any higher derivative role like R square correction will play some role during this transition or nothing? It is just a jump from strings to GR.
That's right. So this is a question. So the first part of the question we can answer, but not the second one. So namely, so the way that the transition happens is that string winding modes decay into string loops, and string loops behave like radiation. So this is a mechanism of the phase transition. Now, in string gas cosmology, we put in an effective background by hand. At late times, you just put in Einstein gravity by hand. In this matrix cosmology, we need to derive the low energy effective theory that identifies the interaction of point-like excitation of matrices. And there it's very well possible that you get R plus something else.
So, sorry?
There we don't know. We're far from being able to calculate that.
Okay.
Okay, I see the question by Dr. Riva. Anna, please.
Hello, I have a question about the matrix theory and its low energy EFT. Basically, there is an approach to constructions of EFT, it's based on getting constraints on EFTs from unitarity assumptions and some assumptions about the existence of UV completion. So what type of UV completion would be represented by matrix theory? Would it be something looking like string theory or something completely different? And I'm referring mostly to the properties of low energy amplitudes. What should we expect? Which dispersive relations can we use?
Right, so I would definitely expect to get what you have in string theory, because the matrix model was proposed because certain calculations in that matrix model agree with corresponding calculations in string theory. So I would expect the low energy effective field theory to be very similar to what one works with when one talks in effective field theory motivated by string theory.
Okay, thank you.
But it's not necessarily Einstein gravity. And definitely the amplitudes will be constrained by what you said. So all these unitarity arguments that have recently been discussed, they are very relevant to this question of emergence of the low energy effective field theory.
Okay, thank you.
That's a very good question.
Okay, any more questions?
Actually, I see a question in the chat, so maybe.
Yes, okay, then in chat, let me see.
Maybe I stop sharing the screen, then I can look at the chat myself.
Chat. Yes, it is a question from Dr. Pulkit Godarao.
Yeah.
If the conclusions from matrix model and string gas in terms of curvature perturbations are similar, then just to clarify, are we saying that the matrix model is a more appropriate ultraviolet theory?
Definitely, the answer is yes. You can view matrix theory as a ultraviolet realization of string gas cosmology.
Okay. Any more questions? Then, actually, I want to say that I disagree with two main statements in the Robert's talk, namely first about the so-called that exists the so-called Trans-Planckian problem in case of inflation. And second, speaking about alternatives, I have a general negative remark about all what I call genesis models, or I think Robert called them emergent one. But I propose to do this in the following in the following way. Just because we still have more than half an hour for discussion, let us thank Professor Brandenberger for his very inspiring talk, and we close with this part of our second session. Then I shall make my questions to Robert more explicit as a part of discussion. So let's first thank all speakers of the present session. Okay, so we begin now the discussion session. Actually, I see I see that Professor Percacci raised his hand. Maybe Roberto.
No, actually, that is not a raised hand. That is a clapping hand.
I see. Okay. So that's when. So now we are having discussion, and I shall also serve as a chairman of discussion. But let me first make my remarks to Robert's talk more clear. So in case of transplantation problem, so my general remark, which actually it was published more or less at the same time as the original Robert papers, more at that. First, if we assume Lorentz invariance, actually it's a separate question. Is assuming Lorentz invariance is agree or in conflict with effective field theory, but I shall assume it's when there is no problem in considering arbitrary high energies. The only requirement is that in flat space, energy squared minus momentum square, the invariant, where the Lorentz invariant component is small. And more concrete remark, instead of why in all these transplant considerations, people consider only inflation. Let's consider the present stage where exists old consideration of how to quantize field in the expanding space, and if we use the standard 3+1 decomposition, which of course it generally cut variant, but in this decomposition we have just the flow of transplanting modes, flow of modes from transplanting region to the subplanting region at the present time in particular. And so that's why of course at the present time we don't have generation of quasi-classical perturbations, but instead we have an effect of particle creation. And that's why my request to all who assume that something strange happens at the mode, when formally each constant k where k is the moving vector, then each mode crosses the Palankin boundary. Then what is your prediction for creation of particles? In particular, this may be heavy gravitons, or just because energies are actually Planckian, creation of say electrons with E-Planck energy. So what is your prediction? And in particular, the strength of my old paper with Igor Tkachov about 20 years ago was just that the absence of created gravitons with Planck with actually sub-Planckian energies, but created rather recently the absence of large background of this radiation in the form of gravitons or ultra-relativistic particles. It just shows that there is no trans-Planckian effect. Okay, this is the end of my first question. So let's first discuss it.
Right. So in the original work with Jerome Martin, we were taking modified dispersion relations and then arguing that when modes crossed the trans-Planckian region, they might be excited. And then you indeed pointed out that there are problems with that. In fact, there would be so much energy in those modes that you wouldn't even get inflation started. So then your proposal was that you just take the modes to be in their Minkowski ground state when they cross the bubble radius. And this is a good prescription. In my language now, it would be you are giving a particular prescription of going beyond naive effective field theory, because you are giving a particular prescription for this time-dependent Hilbert space. But now in the context of the trans-Planckian censorship conjecture, you see that the conjecture is that there will be no cosmologies in which the trans-Planckian modes ever can classicalize. And so the old problem that we were discussing 20 years ago doesn't arise. So this is my answer to your point.
Once more, that was just the essence of my argument, that existence of classicalization requires that the effective number of particles is large. But this does not. But this is not the you miss the possibility in case the effective number of particles are renormalized, of course, is much less than unity. And in this case we indeed don't have quasi-classical perturbations, but that once more, that we have particles. So more generically, my remark is that the theory of generation of perturbations is only a particular case of a good old theory of particle creation in cosmology.
So I certainly agree with the last sentence that you mentioned, but I would say that this good old problem is suffering from the trans-Planckian censorship issue.
No, well, once more, I can only repeat that in case of invariant case, it is not a problem. And so once more, so it is my proposal. Consider the effects of your models at late times, not at early times, but at late times. Because in particular, even if you say that for some reason you need not only simple expansion, I said that it is expansion sufficient. When you say that you need accelerated expansion, okay, if we have accelerated expansion now, it's another question that you may say that the resulting effect will be very small. Okay, show us.
No. What I'm saying about when it comes to late time, the statement is that the trans-Planckian censorship conjecture says that the late time acceleration is not given by a bare cosmological constant. And if it is given by some quintessence field, there are some constraints. There are still very weak constraints.
Well, once more, for my argument is not important. Is it due to cosmological constant or any model of dark energy? Okay, but once more, I would like to see the exact prediction for a late creation of particles. Not only concentrate on this quasi-classical early quasi-classical perturbations. Okay, but let me now go to my second question. My second question, actually, I shall also repeat it in my talk tomorrow in connection of my own old predictions, but I'm rather skeptical regarding it, because in all cases when you have an unstable system, which at some time, and it is unstable because at some times it begins expansion. My generic remark is for a quantum system, for any unstable quantum system, it's not possible to keep it infinite time. So you have characteristic decay time, and okay, when it's just speaking, say, about the actually existent uranium atoms. Of course, we cannot think that way existed from infinite time, and we actually, what way exist, say, only about 12 formed no more than, let's say, 10 billion years or so ago. So speaking in terms of classical solutions of these equations, this quantum statement is transformed into a statement that you cannot begin with the initial state, which has zero measure in the space of initial conditions. It is unstable.
Yes, I agree. At the classical level, this is, I accept this. So in the context of string gas cosmology, you have to ask the question, how long does this quasi-static phase last? And so your criticism is absolutely appropriate for that. Now, in our matrix model approach, we are starting with a quantum mechanical system in a thermal state. And then we are getting out a emergent space-time with a phase transition. And we don't need that the emergent phase lasts a long time in terms of the duration of the emergent time. So I think that in this matrix model approach, I think we don't have the problem that you just mentioned.
And even if you have the effect that the time itself forms at some moment when you cannot say that you have that this time can be extended up to minus infinity.
Yes, so good. This is a question. This is a good question, Alexei, and we use a lot of results from the numerical work on matrix models by Nishimura and collaborators, and they always pick a particular state, and they have a finite time range, and my suspicion is that if you manage to study that in more detail, you might get something like a bouncing scenario, in which the symmetric phase corresponds to something like a bounce phase. But that's speculation.
Okay. So once more, my remark is only that we still cannot say that our investigation of past is closed just because we have reached time equal to minus infinity. So my statement that this is an
right. I take your point.
Illusion.
Right. Just we do not need a very long emergent phase in order to establish thermal equilibrium. That's a difference in terms of between string gas cosmology and the present model. So okay. I think on a bit we have improved in this respect.
Okay. Thank you, Robert. I'm satisfied by your answers, and I propose to the participants, if you have some interesting topics, we still have about 15 minutes to discuss it. Okay. Any idea?
I have a short question to Robert. Actually, to have string gas cosmology, you need to have complete understanding of Planck scale physics. Am I correct? Then,
well, that's the idea. Yes. So in this recent work on matrix cosmology, we assume that Planck scale physics is the matrix model. So that's the hypothesis that we choose. That's the Lagrangian, and our aim is to get everything out of that.
Okay.
So now this is a particular starting point, and we picked it because this matrix model had some successes.
Okay. Yeah, well, my confusion is about there are so many versions of UV completion. So if the string gas cosmology or emergent universe is common aspect in at least many of the UV completions, are only in a particular scenario or particular framework you are writing.
Right. So everything that I said in the second half of the talk depends on this particular starting point, which I think is well moderated. It's not my starting point. It's a starting point that was it got a lot of attention back in 1996. So let me say one thing. If you consider theories of particles, then we know how particles evolve classically, and we know how particles interact quantum mechanically at leading order. But if you want a consistent relativistic theory and non-perturbative theory, then you have to replace particles by fields.
Yeah.
And the particles are actually excitations of the fields. So let's take string theory. We know how strings evolve classically, and we know how strings scatter. But that's not the full string theory. The full string theory has to be something else. And so the proposal here is that the analog of the fields for point particles is the matrices for string theory. And in the same way that the point particles appear in field theory as excitations of the fields, in string theory, the fundamental strings and the point particles will have to arise as excitations of the matrices.
Okay. And here, do you have the same picture? Here in this string gas cosmology, you have strings and there is some kind of phase transition, you enter into GR like phase or standard radiation dominated universe.
That's what we hope.
Yeah. Yeah, and I'm curious if the reverse happens if in the context of black hole, for example, you have, I mean, before the collapse, so you have perfectly GR, and I don't know. Can you say something about the formation of black hole or evaporation of black hole from this picture?
Yeah, this is a very good question. I cannot. Black holes are too complicated for me. They don't have enough symmetry. Cosmology is much simpler. There's more symmetry.
Okay. Thank you. Actually, I have a very generic question about black holes. Actually, today we have a couple of we have one talk from Fabio on black holes, but surely it is not really related to the talk of Fabio. But in general, in black hole physics, one says that okay, well, unitarity violation happens, but okay, then there is a phase curve, which is everyone acknowledged, and then from the phase curve, it is basically assumed that the unitarity, you get back unitarity after the complete evaporation of black hole. For me, this picture is strange. In the sense, to recover unitarity, I need to wait billions of years. But when you talk about usually quantum theories, they are all about short time scales or short length scales. But when it comes to black holes, especially in the discussion with phase curve, I need to wait billions of years to really recover the unitarity, which is really required concept in quantum theory. Okay, I would like to know if anyone has same feeling as me, or correct me if I'm wrong.
Yeah, can I maybe say something about this? So I don't understand why you say that you need to wait a long time until you see a unitarity being recovered.
Yeah, because the page time involves billions of years.
So you see unitarity violation once the black hole has decayed away. It's only then that you have unitarity violation.
Well, then to get back the pure state at which you will only get after the complete evaporation of the black hole, as many people explain with respect to the page curve. And page time is half of the evaporation time of the black hole, and which is literally billions of years. Even if you take the smallest black hole we have detected.
Okay. Probably someone else should answer that problem.
Please.
On best curve, after best time, entanglement entropy and Bekenstein-Hawking entropy all decrease.
Yeah, and no, surely I understand the arguments about entanglement entropy and it is supposed to decrease and everything, but still, this is not what the typical quantum theories.
Entropy generate is increased. Why?
No, I don't know why, but at least even the expectation that you recover pure state only after billions of years is strange. Another thing which is related to this is in the context of black holes, almost every one expects that like when people talk about S matrix for the black holes, it always involves from the formation to the complete evaporation of black holes. This is again strange because S matrices in quantum theories, at least in the quantum field theory, are always about interactions that happen in short time scales. And I do not really understand what kind of S matrix it is, which involves some kind of process which will last for billions of years. So again, it is a strange concept. I never understood this, and I do not know if someone has a clear comment about this.
Well, maybe I can come back to your first issue.
Mhm.
So before the black hole has evaporated, you have a pure state.
Yeah.
And the state, the way an UNRU detector responds to that state at Scry Plus has some aspects of thermality. So the unitarity problem only occurs once the black hole has evaporated.
Okay. Entanglement entropy after best time is decreased, but as generalized entropy is as entanglement plus as exchange equal to h and plus s bh. Yeah. Okay.
Yeah, I understand what you're saying, but okay, maybe yeah.
But it must to increase. Why?
I have no idea.
If
But
if as then not increased, it's not increased. The second law is violent. The second law of thermodynamics is violent.
I do not know if second law is violated if entanglement. Well, it can be possible that there is no entanglement entropy. It's zero. Then it is fine. You do not have any page curve. So of course, this does not show up in the calculations of Hawking or Page, but surely the simple solution is there is no entanglement.
Yeah, but after best time, all of two things decrease. Yeah, decrease. But as then must to increase. Why?
Can I maybe comment on the second point that you raised, Ravan?
Yeah.
My understanding is that if you do regular field theory, you are computing from time t equals minus infinity to t equals plus infinity. And when it's
that
applied,
is for the expand. I mean, that is for the validity of to make sure the validity of the perturbation theory. But interaction, whatever the interaction in quantum theories, which does not last too long times. I mean, right? Interactions usually we deal in the perturbation theory, and
so the interaction takes place on a time scale which is related to the Compton wavelengths. But
yeah,
similarly,
small
for black holes, you have the Bogoliubov coefficients are generated in a small time interval. So I think there's
you're right.
I think the idea of the S matrix calculation is the same.
So the idea that S matrix for black hole should describe completely from the beginning of collapse to the complete evaporation of the black hole is fine. There's no problem.
Yeah, I think that's in line of what we do in quantum field theory. Hopefully, I'm not saying something wrong.
No. Oh, Robert. Okay, we are already close to the time when our discussion session has to be closed. Are there any more questions from participants? Professor Mannheim, do you want to say anything more?
No, I was just waving my hand to say goodbye.
Okay. Then
Bye.
let us thank all participants, and I close our session.
Thank you very much.
Bye.
Thank you very much. Thanks, everyone.
Thanks to everyone. It would be nice if you can send your presentations. I will upload them to the site.
Okay, I think it refers to all speakers.
It's to everyone. I just repeat it continuously.
Okay. So thank you once more. Goodbye.
Bye.
Thank you,
Thank you.
Alexei.
Bye.
See you tomorrow.
See you tomorrow.
See you tomorrow.